those. Okay, I'll do the quick intro.
Okay.
Great. Welcome, folks, to the second day of the GNU Radio Conference. Thanks so much for showing up early in the morning. I think the room will continue to fill, but we have just a couple of quick notes about how the day will go. So for those who are tracking days of the week, it is indeed Wednesday. And the excessive heat continues. In fact, it continues to build through the day. So please do avail yourselves of the water stations and keep yourselves well hydrated. The Wi-Fi, it should be the same as yesterday, and it's a 48-hour registration. So if you signed up yesterday, it'll continue to work today. Be aware that tomorrow you will need to re-up your registration at some point. In terms of schedule highlights, we have Dr. Balanis starting us off as the keynote speaker. Then we have a review of the status of GNU Radio 3 and an invited talk by Ralph Steinhagen. We have 4 workshops going on today, so it's going to be a busy day. Hopefully you've already kind of found the rooms. La Paz is down the corner, around the corner, and Cochise is around the corner the other direction. Both should be hopefully easy to find. If you have any problems, ask the registration desk. We have our building basic data transmission systems starting at 1 o'clock alongside of the 5G ORAN talk by SRS RAN. The SIGMF workshop begins after those workshops at 3:20, and Introduction to Signal Processing at 3:05. We do have lightning talk slots. So if you were in the room just before lunch yesterday, you would have seen 2 little quick 5-minute talks. They're great fun, and those are open to all. And as you kind of saw yesterday, they bounce around in levels of seriousness. So if you have a small project you want to show off, please do. If you have a question that you want to launch into the audience, that's also very welcome. So please do stop by the registration desk to sign up for that. Low commitment, and please do have fun with it. Speaker slides. If you are speaking at any point during this week, we do very much need to get a copy of your slides to share with people afterwards, but also in the short term, we need to get them so that they can be presented up here. So please do upload them the day before your talk. As early as possible helps us, but we understand that inevitably people are working on slides till close to their talks. The chat server, for those folks here in person, there is good conversation happening there, and certainly after the event, the conversations continue. It's a great resource for getting help with GNU Radio and finding other people interested in SDR and software. So it runs around the year, chat.gnuradio.org. The amateur radio license exams are on Thursday. They're 1 o'clock to 7 o'clock, and anyone currently present in this room could easily pass the first level of the amateur radio test with an hour or 2 of studying. There's a few little logistics and then some very, very, very basic RF theory. All of the exam questions are online, as are all of the answers. So really there's no excuse to passing, and it's a great way to get access to hundreds and hundreds of watts of power on licensed spectrum for free. Well, I think $5 to $15 for the test, but quite cheap. And I think I've run out of slides. So there is a social this evening. Thank you, Martin. So if you want free drinks and good conversation at 6:30, just about 5 minutes, 10 minutes north of here by walking, there's a social being run, the Breakthrough Listen SETI Social. We'll hear more about that in the second to last talk, but please do come along if you can. And that's the end of those slides. If we can switch up to the other slide deck, please. It is a real pleasure for me to be able to invite Dr. Balanis to be our keynote speaker this morning. I have had his textbook, Antenna Theory, on my shelf since my undergraduate course on antenna design. And you know, sometimes you rent the textbook and you flip through it, or maybe you don't even open it, and then you sell it at the end of the semester because those things are a little bit pricey. I did not do that because this textbook has remained one of those just books that you reach to every time you have even the slightest question about antennas, whether it's, does it need to be conductive? Is that a property of an antenna? All the way up to, I need to design, some very fancy multi-stage, parabolic thing fed with a Yagi. Has anyone even considered this, and how would that work? And you start flipping through and you go, okay, well, I may be an idiot, but this textbook is both readable, accessible, and fun. So it's answered all of my questions, and I suspect it'll answer questions that I never have. So that's been a fantastic reference. And when I found out that Dr. Balanis was here at ASU, and actually has been since, was it 1983? 1983. Right. I said, okay, well, we can make space in the schedule, and we have to get this guy on stage. So I'm tremendously excited, and I think many of us will benefit from an introduction to antennas and how to approach them. So I really appreciate you coming, and I look forward to your talk. Thank you.
Am I on? Thank you very much. Thank you for the invitation, and real pleasure to see you all and to welcome you to Arizona in general, and also in particular Arizona State University. I've been here almost 40 years. I was at West Virginia University. I guess we're close to Carnegie Mellon in Pittsburgh. For 13 years, I worked for NASA initially from 64 to 70, and then transitioned into academic position in 1970 at West Virginia University, in 1983 here. So today we're going to talk about the evolution of antenna technology, past, present, and future. Some highlights. I have a lot of slides. We're going to go pretty fast. I think we only have about 45 minutes, although people, they give me a couple of hours anyway, so we can change the schedule as we go along. According to John Krause, who was a pioneer in antenna technology, some of you may be familiar with his textbook, which was published in 1950. It says the antennas are the eyes and ears of a wireless communication system. Just like the eyes and ears to a human being, same thing for the antennas to the wireless communication. So if the antennas, if your eyes and ears don't work very well, you're not very effective. Or same thing with the wireless communication system. If the antenna doesn't work well, no matter how good the communication system is, it will not work. It will not be able to transmit and receive signals, messages efficiently. So very important. So today we want to talk a little bit about how all this technology got started, present, and maybe some suggestions about the future of antenna technology. The past, we're going to memory lane. We're going to outline some time periods, some of the significant developments of antenna technology. And we go back really to Hertz in the 1800s. Was the genesis of radio and antenna engineering. So in 1980s, late 1980s, 86, 87 time period, Hertz put together a wireless communication system where we had a transmitting antenna with dipole, very simple. Nearby had a loop antenna, rectangular in shape, and to the dipole, transmitting dipole, he connected an induction coil. And then he induced a voltage on the induction coil, which created a spark at the feed points of the transmitting dipole. And that in turn created a spark in the receiving antenna. So this was, again, the genesis of transmitting and receiving signals wirelessly. Then the other one, of course, we all heard about Marconi, going back to the early 1900s, in particular around December 1901, when he transmitted a signal from Cornwall, England to Newfoundland, Canada. And this was the genesis of long distance wireless communication. Now, modern technology, antenna technology, really got started in the 1920s. This was probably one of the most well-known antenna system, the Yagi-Uda antenna. A lot of the ham radio operators, they call it the Yagi, and that's a misnomer. Really, it should be the Yagi-Uda. What happened here, it was Yagi and Uda were colleagues in Japan. And Yagi came to the United States in 1920s. He was invited by what is now IEEE. It used to be IRE, the Institute of Radio Engineers. That in 1963 is when we transitioned from IRE to the IEEE. And he presented a paper in a convention of IRE. It was Yagi, only he was the author. And that's what a lot of people say, the Yagi antenna. That's a misnomer. And I don't think it gives credit to his colleague, Uda. So you can see when Yagi in the 1800s to early 1900s, and here's his colleague, Uda. So that was the genesis of modern antenna technology. Now, the Yagi was used for TV, but it was kind of narrowband, only for a few channels, back in the old days. We'll talk about here. But here's what the configuration, about an array of dipoles. So we have one element, which is energized. Okay, that's the feed element, whether you're transmitting or receiving. Then you have a reflector, which kind of pushes the energy in the right, to the right, I should say. And you can use one or two at the very most. And then you have what we refer to as the directors. They're the ones that kind of direct the energy in the forward direction to the right. And create a pattern as shown here. Now the applications, as I already mentioned a little bit, amateur radio, TV antenna, but narrowband, but high gain. We'll compare with another very popular TV antenna in a few minutes. And then frequency ranges, HF, VHF, UHF, those were the frequency ranges. Because it's so popular, so well known, I'm giving you kind of one of the initial designs, which I think is not necessarily the most optimized design. People have since then have optimized the characteristics. Typically, the feed element is slightly less than a half a wavelength to be, in order to be resonant. Okay? A dipole, for example, half a wavelength, you make it a little less than a half a wavelength, it becomes resonant. The reflector is slightly greater than the feed element, slightly greater than a half a wavelength. Reflector or reflectors, as I said, no more than about 2 necessary. The directors, slightly less than a half a wavelength. About 0.4 to 0.45 wavelengths. And then spacing very critical. And what I'm showing here, all those are fixed lengths, fixed separations. To optimize them, you can make them variable, okay? And people have done that. But this is one of the initial director spacing, somewhere between 0.3, 0.4 wavelengths. Again, as I indicated, if you want to optimize the performance, you can vary all those special nowadays with software and things like that. You can optimize you can get another couple of dB in directivity and gain and so forth. So that's one of the initial designs. And here's a typical pattern, as I'm showing over here. This is about 15 elements, about directivity, about 15 dB. And those are the E-plane and H-plane beam widths in the E-plane and in the H-plane. Okay, now here's commercial Yagi-Uda antenna. This is for, obviously not too many people use them today. Everybody uses cable and accommodate many more channels. Back in the older days, some of you were not around. Some of us been around for a long time. We had a channels 2 through 13. Channel 2 about 54 megahertz. Channel 13 about 216 megahertz. And this kind of design was a Weingart company could accommodate the reception for those TV channels decades ago. Okay. Oops, I think I did. So here are kind of the gain for channel 2 and for channel 13. As I indicated, the Yagi antenna got a lot of publicity. In 1984, IEEE published in the Proceedings of the IEEE, which is the journal for all areas of electrical engineering, because IEEE has 39 journals in the different areas of electrical engineering. That's how many societies that we have within IEEE. Okay, antenna propagation is one of them. You have signal processing, communication, power, biomedical. 39 societies, 39 journals and transactions. Well, in the Proceedings of the IEEE is for all societies. So in 1984, they celebrated the 100-year anniversary. They published some of the key and well-known papers in each of the areas of electrical engineering. In antennas of propagation, they published only one, the paper by Yagi in 1928. And this was the initial publication when Yagi came to the United States to present the initial paper. Okay, but he didn't put the name of his colleague. It was only his name. That's why people, they call it the Yagi. Okay, and then let me go over here back again. So you can see the third one there, or the second, I should say, Proceedings of the IEEE 1984. That's a paper that it was published in the Proceedings. Not only that, in 1997, they repeated. They republished that in its original form, the way it was in 1928. So that's how classic of paper it was, and still is, by the way. Okay, another well-known antenna is the helical antenna, or the helix, as some people refer to it. This is attributed to Professor John Krause from the Ohio State University. Got to say the Ohio State University, otherwise alumni from there, or I guess I'm one of them. John Krause, a great person, a gentleman. On the top of that, I had the pleasure to meet him, to host him. Came up with the helical antenna, and here's kind of the configuration, the dimensions. I'm not going to spend too much time because we're going to run out of time. It was published initially in 1947. Now here it has two basic modes. If the circumference of the turns of the helical antenna are smaller than one wavelength, okay, you get what they call the broadside mode. It's like this one here. It's like a dipole has. Okay, the maximum is broadside, as I'm showing here. That's referred to as the normal or the broadside mode. But if you make it to around one wavelength in circumference, you get the axial or the end fire mode, where the maximum is along this direction over here. Very popular again, even in the space program. I had pleasure to work for NASA back in the 60s in one of the tracking stations in Virginia. I think they used to use helical antennas to communicate with the astronauts. Okay, or here's a commercial helical antenna courtesy of CV Engineering Associates. Now this is the other one, popular TV antenna, log periodic antenna. This was attributed primarily to the people from the University of Illinois. That's what Duhamel and Isbell, they were on the staff, on the faculty of University of Illinois in Urbana, Illinois. Now, this is kind of the configuration that what the lengths, the separations between the elements, the diameters, if you really want to go, of the wires, they're all variable. They're not the same, okay? But they all change by the same ratio, as well as the separations at the feed point. Well, this kind of an antenna creates a beam in this direction over here. That's the log periodic. Now, you're going to say, why they call it log periodic? What does it mean? Well, let me show you here in a minute. Here is how the lengths of the elements vary. Those are the separations. Those are the diameters of the wires. This is an ideal design. The variation of the diameter of the wires is not that critical, but the lengths are, the separations are, and ultimately even the gap spacing at the feed point of each one of the dipoles should vary accordingly. But that's, again, not that important, that critical, I should say. And they all vary by the same ratio. Okay. Now, if you were to plot the input impedance of this one, is periodic. It varies periodically. And you can see here that this is the period. But it's periodic if you plot it as a function, not of the frequency, of the log of the frequency. Hence the name what? Logarithmic periodic. That's what log periodic stands for, logarithmic periodic, because the period varies, repeats itself, it's constant as a function of the log of the frequency, not of the frequency. Okay. So hence the name, log periodic. Here's a typical variation of the pattern. We talked about the channels 2 through 13 back in older days. The gain, I think, is about 7 dB, and be able to accommodate both the channel 2 and all the way up to channel 13. You can see the gain kind of stays flat, constant over that frequency range. And just to compare, I mentioned Yagi-Uda antenna was also used as a TV antenna, but the log periodic is much broadband compared to the Yagi antenna. On the contrast, though, the gain or the directivity of the Yagi is much higher, like in this case 15 dB versus about 7 dB for the log periodic antenna. So log periodic, more broadband, lower gain. The Yagi antenna, Yagi-Uda antenna, more narrowband but higher gain. That's what you compare. Okay, the trade-offs between the two of them. Here's a commercial log periodic antenna, and most of the TV antennas were log periodic eventually. All right, now microwave antenna technology. Actually, most of people think it started more during this space program, but I'll give you a little history on that, which goes back even to the days of Hertz in the 1800s, actually. But you can read a lot of this, you can find a lot of the history of an evolution of antenna technology in the book by Silver. This was part of the MIT radiation lab. They had like 30-some books in all areas of electrical engineering that were published. They were developed during World War II. They were kind of classified during that period and then eventually became open to the public. Okay, there were, I think, like almost 30-some books. Well, one of them was in the microwave antenna technology, edited by Samuel Silver. So this was the genesis of microwave antenna technology. Of course, it became very popular during the space program, if you remember that. But if you go back, though, even during the day of Hertz, he created a cylindrical reflector, which was only curved in one plane. Okay, that's what we usually refer to as a cylindrical reflector. In 1988, was it 87, 88 time period. Then later on, in Wheaton, Illinois, there was a gentleman, Reber. He was more of an astronomer. He was also ham radio operator. He built a parabolic reflector, as I'm showing you over here. So you can see that was about 1938. And by the way, 1938, a lot of good things happened. I'll let you, I'll give you something to think about. What else happened in 1938? You're looking at me. I had him in class, and he doesn't know it. He says, what really happened? He never told us that. All right. Now, of course, this is the reflector at Goldstone, California, where it was used, for the space program. It was a 70-meter, about 210-foot diameter reflector. Very popular. In fact, even on the 4th edition of an antenna book, I got permission, obviously, to use it on the cover. That's what we have on the cover of that one. Another very popular microwave antenna is the horn antenna. Now, I think all of us have used it numerous times. I'm showing you only the pyramidal one. There's also a conical one. And this one goes back, again, the inventor, it goes back to 1938. What did I say about 1938? Something happened, right? It was a good year. And this was, I think, invented 38. I think he got patent in 1949. Very popular. I'm not going to spend too much time, again, because of time limitations. What the pattern looks like, three-dimensional. This is the kind of a pattern. Again, I'm trying to publicize the book. Now, in other words, the patterns in the 4th edition, they're in color. Okay, they were in the 4th edition. And this is one of the figures, from the chapter on horn antenna. So you can see three-dimensional variation of the pattern of horn antenna, pyramidal horn antenna, the dimensions, and so forth. And this one has a gain of about 18 dB. Typically, the horn antenna, 15 to 25 dB, somewhere in there. The microwave antennas, microwave horn antennas, somewhere in that range. So this one that we simulated and turns out to be about 19 dB. Here's a commercial one. This had a gain of about 16 dB. This is what we call exponentially tapered. In other words, the transition from the waveguide, the feed point, to the aperture, radiating aperture, is smoothly varying in an exponential manner. There were no discontinuities. Provides much better transition, and you can get a VSWR close to unity, really. If you measure it, 1.01 or something, 1.05, you know what I'm talking about? Almost a perfect match. Microstrip antenna, very, very popular. Basically in the 60s, in the 70s, and some of us lived through this transition period. However, actually, the introduction goes much earlier, and I'll show you that in a minute. You can have a microstrip antenna where the patch is kind of rectangular in shape, or you can have one which the patch is circular in shape, as I'm showing here. Actually, the inventor of this one was George Deschamps, University of Illinois. And this was back in 1953. But he stayed dormant for almost at least 10, 15 years. 1960s, I remember when I used to work for NASA during that time, it was microstrip antenna. But it was actually popularized even more in the 70s. There's another gentleman, Bob Munson. Okay. He's the one published a paper in 1974. And so that's what the microstrip, or people used to a lot of times refer to as the patch antenna. Very popular. He has a lot of attractive characteristics. Here, I'm listing some of them. Low profile, very simple to construct. Okay. Versatile, mechanically robust. Versatile in terms of polarization and resonant frequency. Very easy. Here's a photograph of a 10 by 10. This is courtesy of Ball Aerospace. That's what Bob Munson, that I just referred his name, he worked for. They in Colorado somewhere, they outside the Denver area. Oops, here we go again. All right, next. Now, I know some of you use, I'm told you use the dipoles, biconical antenna. So I put a little bit of information here concerning those just to show you some of them. So the bandwidth of an antenna like a dipole or biconical type of antenna, you can optimize if you can utilize the available space that surrounds that particular antenna. I'll show you here in a minute what I mean by that. So if we can go, for example, to just the classic dipole, which is shown over here, just a plain wire. Now, we have a sphere that encloses that dipole, but just a wire antenna doesn't take much of the space. It doesn't utilize much of the available space. So it's not a very broadband. Now, we can make it more broadband if we go to what? By a conical antenna. By a conical antenna, it takes more of the space within of the sphere, which is surrounds. Okay? But again, we have to truncate it. So, the VSWR may not be as good if you have a smooth tapering transition, I think, from the feed towards the ends of the biconical antenna. So as we go from one to the next one, the bandwidth goes what? Up. Ultimately, even though this may not used as much, you can use 2 half spheres. Takes all the space available within the volume of a sphere that encloses the element. So that's one way of increasing the bandwidth of the antenna. Now, you can also, of course, you can simulate and actually build it. If for example, if you want to mount it, I think, on a pole or somewhere, for example, a body antenna, if it's solid surface, wind resistance, it may be a problem for you. It may be swaying instead of maybe moving. Well, you can approximate a biconical with the wires, as I'm showing over here. And how many of them you use, that's how close to the solid surface it would be. People have done that. Okay. That's one way to minimize the weight, the wind resistance, if you wish, of the antenna. Bow tie, if you take a slice of a biconical antenna, that's very popular, as you can see here. And of course, feeding them, you use what they call balun. Some people call it balloon, but it's actually balun, balanced, unbalanced, because the element itself is a balanced element, and if you use a coaxial line, the coaxial line is an unbalanced line. So to connect the two, provide transition but from a balanced element to unbalanced line, you use this device which we call balun, balanced, unbalanced, okay? Very popular. Now here's if you were to compare a solid biconical antenna with a bow tie, a bow tie with simulation and measurements. You look at the S11, which is basically the reflection coefficient, if you wish. And you can see how well those two, compare, measurements versus simulations. Now here's kind of, if you were to, especially with today's software, you can see where the current density is the maximum, is along the edges. The center part of the bow tie antenna is not that critical. So actually you can remove it, and without really altering that much of the radiation characteristics. And I'll show you that in a minute. Now, here is the solid one, and we can go remove. I'm just showing you, for comparison. The one on the left, you can see where the current density, where it's red. That's where the most intense current density is. So we remove, let's say, if we were to remove the center part and compare one where we have removed the center part versus the solid one to see how well they compare. And here they are. This would be the one where we have removed the center part of it. We call it maybe the outline. The outline would be just a wire type of a bow tie. And here we compare the two of them. The black one is the wire type. The red one is a solid one. So we're plotting the S11 versus frequency, and you can see the difference. Yes, the outline one resonates at a lower frequency because it looks bigger. You know what I mean? Compared to the solid one, electrically it looks bigger, and that's why it resonates. Physically, it looks bigger and resonates at a lower frequency. Another one is, and we had worked with a local company over here. They had a specific type of a substrate, flexible. There is, it's actually a research center of ASU. They're called Flexible Display Center. It's in South Tempe. And they had a particular flexible substrate. They call it PEN, P-E-N, stands for polyethylene naphthalate. We worked closely with them, and they gave us some of that. We built one, as you can see here, that we can bend it. Okay? And actually, this was published in a paper, I think, in 2011 in the IEEE Transactions on Antennas and Propagation. There's a lot more information that we had on that. But anyway, another apparently popular antenna, Vivaldi, I think you guys were talking about, somebody communicated with. Again, this is a slot antenna with a smooth transition, exponential transition, provides a good match, if you wish, from the connector, the connecting transmission line to the element itself. And this is kind of, the first one is kind of a three-dimensional view. The other one is the top view. And of course, the other one is the side view, as we can see. And you can see this, we're plotting the current density on it. you can see the most intense current density is in the transition from, let's say, the feeding transmission line to the, to the aperture of the antenna. Folded dipole, another one for FM broadcast TV antenna. Let's see here. Back in the old days, again, we have array of dipoles. Okay, then we have the TV. The TV wants to 300 ohms. Okay. Now, if we use a cable you typically, let's say, as an approximation, let's say 75 ohms. But the TV wants to see 300 ohms. So we have to use what? Impedance transformer, 4-to-1, to provide the match. However, if you use a folded dipole, instead of using just a regular linear dipole, you use like a very thin rectangular loop, basically. Okay, that's what we call a folded dipole. Well, now then, and we use a twin lead line. Twin lead line is a 300 ohm line, approximately. And you can see that we can adjust the dimensions of the folded dipole to provide a perfect match, or provide an input impedance of about 300 ohms to match the transmission line. And here it is, and I'm not going to go through the details, but this one here shows you a particular design using the dimensions, the diameter, and the spacing of the folded dipole, that you can get an input impedance of 300 ohms. And now you can, this is kind of the equivalent circuit, of the, if you have just a regular dipole, and then of course, if you make a folded dipole, it's like you have an impedance transformer, as we're showing over here, like a 2-to-1 ratio. And then you can put everything, bring everything to the input side of it. And basically, you get a 4-to-1. I mentioned the 4-to-1 impedance ratio. So when you make the length of the folded dipole exactly half a wavelength, the input impedance is 4 times the impedance of the dipole. If the dipole is 75 ohms, 4-to-1, it would give you 300 ohms, perfect match for a 300 ohm line. So today, what are we doing? Well, there are a lot of things happening. As I just give you some of the things that are happening, also some things that we have done here at ASU. I've been, as I indicated, I retired a couple of years ago, and it was 37.5 years at the ASU. Okay, we built a facility, and I will show you that towards the end. Multiband antennas. Nowadays, we have so many different systems that we want to connect with, and you cannot build an antenna for each system that, let's say, you have a mobile device like a cell phone to accommodate everything that we want to receive information from. So can we design an element which is multiband? And the answer is yes. Let's take an example, simple example. I mentioned the microstrip antenna, very popular, very versatile. Okay, so here we've shown you initially, you can see this thing flashing, one frequency. You adjust the dimensions of the patch to accommodate a frequency. Now we want another frequency. That we're going to introduce another patch? The answer, no. We can use the same patch and put a slot. Okay? And this slot will accommodate the second frequency. Then you can put another slot. Okay? Now you can't just go cut slots. You got to do them properly because they become interference. In fact, we had a current density. We have more information because, again, time limitations. I'm not going to go through it. But anyway, you can do something like this. Here is using the same patch, same physical dimensions, but accommodating 3 frequencies. Now you say, well, that's just simulations. No, actually, people build one. Here's one, for example. You can see the slot. This was for GSM, first generation. communication system. And the second slot there is for DCS, digital communication system. Okay, so the same physical dimensions, but accommodating two different frequency ranges. So you got to be creative, okay, how to do that, how to minimize the number of elements that you need, let's say, to use to accommodate what your system wanted to do. Nowadays, I don't know, some of you may have heard about it, they say meta surfaces. What are meta surfaces? Well, those are surfaces which does not exist in nature, but we can actually synthesize such surfaces. I'll show you that. Meta is a Greek word that means beyond. Okay, beyond. It was introduced again by a professor at University of Texas at Austin. Gave the name, came up with the name, meta surfaces. Very popular nowadays. Not only popular, there's a lot of activity. In some societies, like the antenna propagation society, if you're not working in kind of meta surface related technology, you're not doing anything. In other words, you're falling asleep. Okay, so it's very popular. If you look at the transactions and some of the attend some of the conferences, you will see a lot of papers, sessions related to meta surfaces. Now, what are they? Why and why we need them? For example, a dipole, horizontal dipole. If you put it above a metallic surface, by the way, PEC stands for perfect electric conductor. Perfect conductor, okay? Well, conductivity is infinity. You understand what I'm saying? Metal is a good approximation to it. Conductivity, 5.7 times 10 to the 7 Siemens per meter, for example. A very, very good conductor, for example. The height, if the height of the element above that surface is small, it becomes very inefficient. In fact, if you make the height 0, the thing doesn't radiate. Wow. Remember, we use the image to take into account, you know, the presence of the plate, and the image is in the opposite direction. So whatever you get radiation from the actual element, the one in which is reflected from the surface is what? Equal and opposite. They cancel each other out. So 0 radiation. It shorts out, to put it in simple words. So what you need is PMC, perfect magnetic conductor, where the tangential in a PEC, the tangential components of the electric field vanish in boundary conditions. In the PMC, the tangential components of the H field vanish. So in this one, you can bring the element right on this surface to create a conformal type of a configuration, like for, let's say, flying platform. You don't want something sticking out and then creates drag and so forth. You want it to be conformal. But we don't have PMC surfaces. Yes, we do not have. We do have. We can synthesize them. Here's one of the first popular such a surface. So what do we have with a regular substrate? Well, we have the conductor with the, here's the ground plane. We have the dielectric layer. And then we have, we put patches on the top of a substrate. And then we connected the patches to the ground plane using vias. Well, this kind of a surface emulates, okay, approximates a PMC surface. You say, how do you know? Well, we have to prove it, obviously. And here it is, if we plot the phase of the deflection coefficient versus frequency. And this is actually simulations using a very popular software, HFSS, and some design equations and so forth. Here, there is a frequency range over this surface acts like PMC. It's actually an ideal PMC only in one frequency, but there's a bandwidth over, it's very close to a PMC surface, and that's a bandwidth over there. So where the phase of the reflection coefficient varies between plus 90 degrees to minus 90 degrees. And for this particular surface, it's from about 10.35 gigahertz to 14.25 gigahertz. That's where the phase variation is between plus 9 to minus 9. And exactly at the center there, which is about 12 gigahertz, the phase is 0. It's a perfect magnetic conductor. So it simulates, it synthesizes. This is synthesized surface to represent a PMC surface. Now we can put what? A dipole on top of it. Of course, because we have the metallic patches, we can't put them directly on top of them. We got to put some kind of a very thin dielectric layer on there, so the contact won't be there. We have done this. We have built and measured and so forth. All right. So this metal surface, when they interact with, I think we're getting close to we can get very unique and intriguing characteristics. Okay, I'm going to go to applications on the antennas. Here is, for example, I'm going to show you, this is a synthesized PMC surface over here. So we have a loop antenna, but this is circular instead of being rectangular. Here's a loop antenna there on the top of the surface. We actually build one of them. This is work we've done here, my group here at the ASU. Simulations, measurement, we got a 3 dB increase in the gain of the antenna. Okay, then now we used another one. We got another dB and a half. This is the one I just finished showing you. And then we put a PVC collar around it. Metallic, color over here, and it looks like this. The center part is the one like the one I showed you a while ago. This is, we got another dB and a half, 10.5 instead of 9. So they are very, very, very popular, and they have attractive characteristics. Another one is application in visibility to radar, provide low visibility, low RCS, radar cross-section as we refer to it. Okay, that's the parameter that we try to minimize, okay, which represents the visibility of a target to the radar. Okay, we'll be finishing here in a minute. Okay, so if we take a plate, this is basic electromagnetics. If we illuminate it in the side like this, most of the energy goes at an angle where the angle of reflection is equal to the angle of incidence. Snell's law of reflection, as we refer to. Okay, so if you take a flat surface and you illuminate it vertically, where do you expect most of the energy to go? Towards you, towards the direction of the incident field. So this is very highly what? Visible. Ideally, all of it would go in that direction if the plate is infinite. But if we make it finite, you get this kind of a scattering pattern, as we refer to. What I talked about, these surfaces, meta surfaces. If we take the same ground plane, you put patches on top of a different configuration. Okay, we're creating what we refer to as checkerboard type of a surface. You eliminate this surface, different patches. Now again, there's a lot of work, a lot of it that goes behind it. If we illuminate this one perpendicular, guess what? The energy goes in different directions. We're creating 4 lobes away from the direction of where the energy came from. We have lowered the visibility of this surface to the radar. Okay? How is this happening? When you illuminate this surface here with an electromagnetic wave, we're creating current densities on those patches. And the current density is different depending on the patches, how they design. We create an array of patches. We use an array theory from antenna technology, and that's how we control the scattering. Not only create, but direct it away from the receiver. Here's another one, which is hexagon. This creates a pattern 6 lobes instead of 4 lobes like the previous one. Okay. So, future. Integration of this, a lot of devices with the metal surface creates a lot of interesting work for the future. 5G communication, flexible antenna, reconfigurable, all kinds of ultra-wideband, wearable, reflector rays, terahertz antennas. And so there is, as a conclusion, there is today's antenna technology. You know, it used to be back in the old days, you had a TV antenna, you go over there and screw around with it and try to fix it, you know what I'm talking about? Not today. Today is a science, is not an art, if you wish. There's very, very bright future, many challenges. What do we need? We need to, excuse me, to exercise creativity, imagination, science, and so forth. So, obviously, I highly recommend, well, I should. I worked for the damn thing for 56 and a half years. If I don't know when else I'm going to do it. This is a facility that we built here. We got this young man over here. Again, I retired about a couple of years ago. They're using the facility. He's more in the communications area, but we have people also in electromagnetics antennas. They're using it. This was state-of-the-art facility. It was built about mid-1980s, about 85. It's 37 feet in length, about 25 feet in width, 18 feet in height. State-of-the-art. We have a compact range and so forth. It was one of the top 2 such facilities at a university. The only other one at that time was the one at Ohio State University, but they were, you know, in business since the 1950s. Okay, so here I are. If you want to know a little bit more about my background, what I have done, why antennas, why electromagnetics, if you go to the internet, you put legends of electromagnetics. This is just, I was interviewed about a month ago, a little over a month ago. You can go over there, you can, if you have a hard trouble sleeping, this would definitely put you to sleep. It's about 72 minutes. So I'm trying to publicize, you understand? Okay. You don't have to use the link. You can go just put Legends of Electromagnetics. We'll get you there. Thank you very much. And I'm happy to, whatever time we have, to entertain some questions. Thank you again.
I'm afraid.
The only thing we did not do here, we did not negotiate the price of me coming. So this is the time, you know, to do that in a
Bids are opening up.
Bids are opening up.
Thank you very much, Dr. Blanes.
Thank you. My pleasure. Thank you for inviting me.
I'm afraid that we did let you just continue on because we really wanted to hear about the metamaterials and stuff like that. So we have used all of the time for questions, and we need to go on to the next talk. I do apologize, folks.
Not even one question? Maybe something.
One question.
Yeah, one question. Come on over here.
Does anybody have a question they'd like to ask? Oh, okay.
Yeah. Any plans for a 5th edition of Antenna Theory?
I'm sorry?
Any plans for a 5th edition of Antenna Theory?
The answer is a very short answer, no. But I'm in the middle of the 3rd edition of the EM book. Okay, in fact, I'm going through 4 rounds of page proofs. I just finished it over this past weekend, and I think it should appear, you know, my other one is more graduate level, should appear by the end of the year, beginning of the next year. And not only that, but the title has changed a little bit. Even the publisher wanted to put my name on it. So it's Balanis Advanced Engineering Electromagnetics. Is that enough publicity? No, it should come out by the end. So for the antenna right now, no, I think. That's the short answer. That was a good question.
Yeah, it was.
That was very creative.
I promise we didn't plant it.
No.
So thank you very much.
Thank you. My pleasure.
And this is for you.
Oh, thank you. How much is this worth? About $5? I thought I'd get some money.
GNU Radio, free and open source software.
Yeah, it was really, it was really a pleasure. Thank you very much. Thanks for the invitation. Thank
Thank
you.
you very much.
Our pleasure. Thank you.
I'll meet you at the back and take the microphone off in
Okay.
just a moment. So we do have a very quick talk as the next one, both out of necessity and out of I think number of slides. I've seen the deck and it's quite short, single slide. And this will be from Jeff Long about the current status of GNU Radio 3. Jeff, as we're just transitioning over here, stepped up and has been doing an increasing amount of work on basically the maintaining load of GNU Radio. So looking at the GNU Radio 3.10 branch of code and fielding all of the pull requests that have been coming in and helping get those merged and backported onto our maintenance branches. So I know that that's taken a huge load off of Josh, and as he steps up into the president role, I think he said that that was only really possible because of Jeff's work. So thank you very much for that.
Right, and we'll save a couple more minutes because I think Derek did a couple of the things that I was planning on talking already. I was honestly trying to figure out how I was going to fill 15 minutes.
15 minutes?
15 whole minutes, and yeah.
You stole some of my time.
I
You
know.
that?
I would have rather listened to more of yours actually
Well,
than mine.
Me too.
Okay, well that's good. We didn't practice this, by the way. Okay.
I did.
Yeah, we did. Okay. All right. So I'm Jeff Long, the GNU Radio 3.10 maintainer. We previously, Josh and I split this work, and like Derek said, I've been pretty much the button pusher.
Here's a button to push.
There's a button to push, but if I push this, it'll go to a black slide. So I'm not going to push that button. So what is maintenance on GNU Radio? Really, everybody here is the maintainer of GNU Radio. We don't provide GNU Radio to you guys. We help kind of mediate GNU Radio getting provided from you guys to you guys. So I just wanted to make that point that the maintainer role in GNU Radio is not necessarily the developer role. It's the maybe a little bit of quality control, talking with people, making sure that APIs aren't going to get broken. So this talk is a little on the boring side because we're trying to keep 3.10 boring. For excitement, listen to what's coming up next, where people will be talking about how you're going to use GNU Radio potentially to keep things and anti-things colliding inside a collider, which is good because nobody wants to get hit by an anti-thing traveling at the speed of light. But we found when we tried to accelerate our API development, it annoyed a bunch of people. And so for 3.10, really our goal is to make it so that you don't have to worry about the API changing, while at the same time getting some new functionality. And that's really most of the work is getting people to submit things that are useful, that bring in fixes, new functionality, but not break anything. 3.10 will probably be around for another year or two. We don't really have a plan for it, but we also don't have a plan for a 3.11 because we don't want to break the API, and that would be the only reason for doing that. We've been releasing 3.10 quarterly, previous to that 3.9, which terminated, and we're going to keep doing that. It slipped a little bit this time, both because of summer, and we figured we'd give a little extra time for anything that happens during the conference. So I'm just going about a few highlights. One of them, now highlight is like in the architectural sense, it's not going to make your day or anything, but hopefully it makes your life easier if you're using GNU Radio. Logging, Marcus put a lot of effort into making it so blocks log more cleanly, and Python blocks are full up capable of doing logging. So thank you, Marcus, for working on all of that. As Derek mentioned yesterday, one of our GSOC students did some new Qt syncs. Pushed the button to merge the matrix one yesterday, and so we've got a couple others coming after that. Filter Designer had some flaws, and so this is maybe not a tool that people use, but now maybe they'll use it more because it doesn't crash as much. GRC, same thing. There are just a couple of annoying things, like the Libex 11 complaint. Every time you started it, got users worried. Sometimes things wouldn't save correctly. It's just these little things that, if it's more reliable, it gives people more confidence in the software. Testing, it's pretty much invisible once the software is released, but we run continuous integration in the background. I can't take credit for having set that up, but it's great. And we also run CI using Conda. Ryan Voltz has done a lot of work kind of in parallel with the work we do. He does this himself with Haystack, MIT. And so you can run GNU Radio pretty easily on Windows now using Conda or on Linux, of course. And I just haven't tried Mac. How many people run GNU Radio on a Mac? I heard that. Okay. Yeah, I heard a little talk about running on a Mac yesterday. Right. I know Clayton tests GQRX on the Mac and stuff like that. Okay. So just quickly, a couple more things. More blocks do C++ code generation. There was the ability to change the constellation of the constellation encoder decoder that got at runtime that got put in. And I mention this because this was one it seemed like a fairly simple change, but the developer was willing to put up with us saying, no, you got to tweak this. Now you got to do this to make this backward compatible. I have a few changes like this that have taken a lot of time because we want to make sure we don't break the API. Another thing that Marcus worked on. Marcus is a theme here, by the way. We could call Marcus a maintainer just as easily too, because he's fixing lots of problems and does a lot of work behind the scenes. But throttle latency. So if used correctly, the newer version of the throttle can help with things like your Qt syncs freezing up and not updating very often. The ZMQ blocks, for people familiar with the more advanced ZMQ patterns, we had it fixed which side was client, which side was server, and now that's flexible. We can also provide back pressure across ZMQ, which is useful rather than having it just run flat open into nowhere. And I guess that's all I'll mention from specific blocks. We're expecting a lot of activity over the next few months, as Marcus is tasked with going through some of our issues and coming up with some fixes. I'm looking forward to working with him on that. And in the interest of keeping this short, I'm just going to cut it off there and say that always available for discussions on the side. We're always looking for new developers, and show up, learn the way that we do business, or we'll try to learn how to work with you better. And contribute. Always looking for new people. All right, and I'm not going to take any questions. You can catch me. I'll be over in the corner on the table there, and we'll get right into the next speaker. So, thanks for being the users.
Thank you very much, Jeff. So our next speaker, which we'll roll right into, is Ralf Steinhagen, who is coming to us from Germany, the GSI FAIR facility, the facility for anti-proton and ion research. And having seen a bit of his slides, I think I'll pretty much just hand the microphone over with the words that it's been great to work with Ralf over the last year, and I'm very much looking forward to continuing that on. So we have this talk today, and then Ralf is again speaking tomorrow, but I think we'll let you see how that goes. So thank you very much, Ralf.
Thank you, and I guess I first give a small introduction what means accelerating science, how to show a slide deck in one slide, a frame rate of 1 slide per second. But we'll catch up. Please stop me if I'm too fast. I titled Standing on the Shoulders of Giants and GNU Radio 4 usage at FAIR, the Facility for Antiproton Ion Research. We're an accelerator-based particle accelerator-based research facility that operates particle accelerators in order to establish fundamental science, to provide a research platform for fundamental science down to applied sciences like material science and biomedical applications. So how to get people to Mars and back alive and healthy. And what's important is what I present here is not just my work on my own, but it's always a team. And it's a bit like, clicker not working? We have like some other modes of control? Okay. And it's basically I'm but a dwarf standing on the shoulders of giants. And we're all products of those who came before us and nurtured and guided us. And while we provide a platform for research, this is no, in our facility we have to provide the necessary technology, particle accelerators. But in order to do that, you have to build them. And to build them, you need people. So as mentioned, let's say also in the first keynote talk, building accelerators about people, developing people, nurturing them, training them how to do. And this is a certain skill set that we have to train every generation over and over again. This is not something to be granted that if you have developed something 10 or 20, 30 years ago, that this is like on for eternity, but you have every time a new generation that you have to train and not just transfer knowledge, but also understanding from one to the next. And and what's very important, and what's very important that, I present this on behalf of many other people, and I'm very thankful for all the people who came before me, notably Eric Blossom, who's the giant, maybe here in this image, and then, but certainly also Derek and Josh, who are the people sitting on his shoulders, and we would probably the people who are sitting on your shoulders, because you took us in and adopted us for our application. We're providing a facility, and I thought like before, going to a little bit more the meaty nuts and bolts technical things, I thought like I brought like a small introduction video that introduces who we are, what FAIR does, what our mission goal is. And let's hope that this works.
Matter, the stuff the world is made of. Matter was created in the universe, but how exactly did it come into being, and what are its properties? The FAIR Accelerator Facility in Darmstadt. Here, scientists want to unravel the secrets about the structure and evolution of the universe. Giant planets, stars, and stellar explosions subject matter to extreme conditions, such as very high temperatures and pressures, and these extreme conditions can be reproduced at FAIR. FAIR is the universe in the laboratory. FAIR is the only facility of its kind in the world. It consists of a ring accelerator with a circumference of 1,100 meters and a complex system of storage rings and experiments. FAIR will produce beams of ions and antiprotons of the highest quality and intensity. To bring the universe into the laboratory, scientists at FAIR have organized themselves into 4 experiment collaborations. They want to find answers to questions like, how are heavy chemical elements created in stars and stellar explosions? In what form does matter exist in neutron stars, the extremely compact remnants of supernova explosions? How can antimatter help us understand the mass of matter and the strong force? Which fundamental symmetries define our universe? What are the properties of high-density plasmas that occur in the interiors of large planets? How can we use particles to heal diseases? And how can we protect astronauts against cosmic radiation? Can we use ion beams to change specific properties of materials? The collaborations have developed cutting-edge measurement methods and techniques for their research. They will measure the particle collisions generated by the accelerator using detectors, some of which are as tall as a building. Vast amounts of data will be accumulated during the experiments. This data will be saved and evaluated by one of the most energy-efficient computer centers in the world, a new ultra-high performance computer center called Green IT Cube. The FAIR facility is being built at GSI, the Helmholtz Center for Heavy Ion Research, a world-renowned research institute that has more than 40 years of experience in building and operating accelerators. At GSI, scientists have discovered 6 new chemical elements, for example, and developed a tumor treatment that uses heavy ions. FAIR is being built by an international partnership of 9 countries. The biggest contribution is being made by Germany. More than 3,000 scientists from every continent will conduct research here, and they are already preparing the experiments of the future.
One of the greatest things of this laboratory is that it is a unique opportunity for learning. So we have people coming from all over the world, from South Africa to Japan, here to learn not only science, but all sorts of different advanced technologies. And for us, this is a fundamental function of our laboratory, that we provide training and opportunities for growth to young people in science and in engineering, and that this then goes back to society at large, and it's our contribution to the future of the world.
I think I couldn't have better summarized as our director, Paolo Giubilini. Basically, we use a facility, provide the technology and the platform for doing this research. We're based in nearby Frankfurt and Darmstadt, and based on an original national laboratory that will be superseded and extended by FAIR. As you heard, we're like a member organization that comprises of states. So we have 10 member states in the recent edition. And we have the primary stakeholders. We have about 3,000 scientists that are currently visiting us on site from more than 56 countries. These are just counting the scientists that are actually on site at one given point of time per year. There are, of course, lots of other institutes that backing up those scientists and doing the analysis, like in the back office or in the research institutions. The new FAIR facility has a construction cost of about roughly 3 billion euros. This is like in 2005 figures. This is like political speech. So the currency was fixed in 2005 and now is escalated due to price inflation. We plan to do the hardware beam commissioning in 2025 and start operation. And the GSI is established already in 1969, and we're responsible for that. You have to learn 5 new elements in the periodic table, and our annual budget is about 130 million euros. That's the present state of our civil construction effort. So that's a very huge site which quadruples the size of GSI. Most of the accelerators are underground, having a total beamline length of about 4.5 to 5 kilometer length. You see very prominently on the top right the CIS 100, which is our largest accelerator with 1.1 kilometer circumference. And this is like this one of the unique things. We're built within like a nature reserve. So once we're finished construction, everything has to be put back to order as if there wouldn't have been an accelerator in the first place, which is put some challenging constraints in terms of radiation safety and impact on the environment, because basically if you camp on site, you should not be exposed to any radiation above the background radiation you have. And that puts very tight constraints. And this is one of the biggest civil construction projects in Europe, with about 500,000 or 600,000 cubic meters of concrete being used. Just to put this in perspective, that's about a fourth of the Hoover Dam, just for setting up these tunnels. So it's a very large complex with different structures. So what we're trying to do is basically similar to astrophysics or astronomy. We're trying to recreate and understand where is the origin of matter, and rather than pointing our antennas to the sky, we point them towards inside our accelerators, where we have these charged particle beams, and where they basically recreate supernovae-like experiments or microscopic black holes, which then decay, and where we study the properties of matter on a much higher frequency scale. Because if you look at supernovae, you have one every 50 years. And in high energy physics especially, if you measure once, that doesn't count. You have to measure at least a couple of trillion times and make sure that always the outcome is the same. Similarly for nuclear physics, where you need like a very high brightness and intensity repetition of these experiments to look at very, very rare effects. And these very rare effects are not just rare, but also sometimes very faint and hard to detect. So this is like a synoptic view built on the existing facility on the left, which comprises of a linear accelerator, and in the beginning a very powerful particle source that creates these charged particles, because that's one of the key ingredients. If you want to accelerate particles, you first have to strip at least one electron, and as soon as you have charged particles, then you can accelerate them in an electromagnetic field or static voltage and get like higher powers. And what is unique of this facility, of this extension, is that maybe each of the technology on their own exists already, but we're supercharging them by expanding the parameters at least a factor 10 to 100 more beyond whatever has been reached nowadays as state of the art. And this starts with our ion sources. They're basically on a platform that is electrically isolated and provides the highest intensities, and then basically being accelerated in a linear accelerator, which is rather large, so you can sit inside and do like maintenance. The reason for that is because you have a very large frequency swing. They operate at 108 megahertz. Some people who do like telecommunication or like radio or TV might wonder like why 108? The thing is there's an airport nearby, and 108 is actually where most of the Kleistons these days were built for, initially to help planes landing on the strip. So there's basically like the pilot tone where they land on. And when they built this facility, they're like, oh, those RF amplifiers are very cheap to build. Let's build an accelerator around this. And this is maybe also the name of the game. We have lots of RF technologies and synergies with radar applications, vice versa, because we can produce very high, powerful RF waves, but and in need for that equipment that produces this. But at the same time, we build also sources that later on, or techniques that are used in radar applications or sometimes also telecommunications. So this linear accelerator is very versatile, can accelerate basically everything from a proton up to very super heavy elements like uranium and also molecules. And notably also not just the primary stable particles, but also isotopes of them. So we have a garden variety from very light to very heavy. And the specialty of our facility is that we can switch between these particles a la carte. So you come basically to us, and then we can flip out particle species from one day to the next, which is also like a unique feature. And then these particles are further accelerators. In the beginning, you use linear accelerators, but at a given time, you need so many accelerating cavities that the length of these accelerators would become prohibitively long. So you say, in the end, let's use that one cavity, and because the particle beam is charged, you use like electromagnets, like dipole magnets, to bring back the beam to the same cavity. And then every time the beam passes through the cavity, it gets like a small energy boost. And then if you do this often enough, in the SIS-18, you do this about 1 million up to 10 million times per second, you get very quickly from a very low energies up to top energies of 28 giga-electron volt, which is basically the equivalent of 28 billion batteries, AAA batteries put in line. Obviously, okay, that's what you can see on this picture in red are the dipole magnets, and just behind this colleague is one of our RF frequency magnets, which is a bit unique because it generates RF waves in order to accelerate these particles from as low as 100 kilohertz up to 10 megahertz. Because of the particles, as they become faster, they traverse the circumference faster, and then we need to follow and have a synchronous frequency tracking of that. What is special about that we can do this frequency swing in less than 100 milliseconds and with a precision of roughly 10 to minus 5. So this has very high demands on phase stabilities and tracking speeds. And we have to monitor that because if the particles are not synchronously accelerated, we lose them immediately, and then they're lost for physics and science and so on. And then in yellow, we see some focusing magnets. They basically act like lenses. Different to optical lenses, they can focus only in one plane, but if you combine them, you can make the combined lens focus both on horizontal and vertical. And this causes the particles to transcribe vertical oscillations as they traverse around the circular trajectory. This is very important because this creates also some form of stability, but similar to like oscillation, like also very similar to a string on a violin. This is important because you have self-amplifying instabilities. If you don't hit the right tune, the particle oscillations start to grow and become so large that basically the particles will collide with the vacuum pipe and then being lost. Speaking about vacuum, since we sometimes accelerate partially stripped ions, it's very important that these particles are not lost due to rest gas interactions. And for SIS-18, since we're under 100, we have like a residual gas pressure of about 10 to minus 11 millibar. Just to put that perspective, is a very small number, but this is lower on that scale, lower than any vacuum you have elsewhere on Earth. And in nature, probably the only space you will find such a vacuum is on the south pole of the moon, when it's not illuminated by the sun. So it's very low, just to make sure that particles stay in the machine and not interact. And also that's this theme that most of our diagnostics have to be non-invasive, so we can't touch them because anything, ions a bit like elephants, treat them bad and they will never forget and they're lost before they're being put to good use for science. So yeah, one of the big challenges is that we in total have not just one accelerator, but in total 11 that have to be synchronized, that we operate with unprecedented machine and beam parameters, and on the 24/7 parallel operations. So we're not just serving one long-serving experiment, but we have at least 7 large experiments, and then whenever these large experiments can't take beam, we have to slot in others. In order to make optimal use, we have this is a bit like our tube map, or like in US, sorry, it's like subway map, where basically you have the particle source in the top. I omitted the unilinear accelerator, but depending on the use case, we route the signal to different experimental stations, targets, or even like further accelerators where the beams are being collided. And you can see, for example, one of those schedules in yellow. And in this case, if the CIS-100 is not producing beam, we're trying to slot in other use cases. And then once the yellow cycle needs beam again, we stop and then start serving another experiment. And because this is not static, many experiments come and go on a daily basis, so we have to switch between the schedules on a high frequency. Now, in order to have this flexibility, because we have to basically reconfigure our whole facility on a day-to-day basis with very different beam parameters, with different use cases, basically we have to build every day a new machine for catering the individual experiment requirements. And in order to be flexible and to do that, in, let's say, on a 24/7 shift crew basis, we have about 4 to 5 operators that are there on 24/7 case. They can't do operating 11 accelerators just by hand. That's sheer impossible. So you have to give them good tools that guide them and aid them to set up this accelerators quick and efficiently, and also to help them to diagnose failures early on, so that they can make informed decisions, but also call then the experts to tackle some of the more demanding things. And for that, we need to create tools. So my department, our task is basically to deal with the system integration, both vertically, but also laterally, to combine the different aspects that make up an accelerator up, and that is like tool. And this image is a bit like name of the game. If the hammer is the only tool you have, then all problems are nails. But sometimes you don't know what problems you occur. So what we have to do is basically also prepare for the commissioning of the accelerator a certain set of tools that is flexible enough to adjust for the eventualities that you can't foresee. You prepare for a certain extent of variability, but you can't foresee any problem. Some things you have to diagnose ad hoc, and that's basically the part where GNU Radio plays a critical role, where we say, like, we have a statically set up environment and flow graph processing for the facility, but if there's a problem, we also want to give the domain experts that are not necessarily research software engineers tools at hand, so that they can help themselves and make modifications to how the machine behaves without having to become a C++, Java, or Python developer. So core of us is always like we provide a service to the experiments that have certain requirements on energy, and we basically, our deliverable or product is the particle beam with the specific characteristics, and for that we need particle accelerators. Now the big elephant in the room is like, what does this have to do with radios or RF? Do we use GNU Radio just as part of the control system for generic signal processing? Actually, Dr. Balerne said everything about antennas. If you accelerate charged particle beams, they emit radio waves. So they have electromagnetic waves that they drag along. And if you want to measure those particles without interfering with them, you just listen what they do while they're traversing 1 million times around this accelerator. And for that, we built, of course, antennas. This is like a strip line or a patch antenna. Looks very much on the slide what you saw earlier, so I don't have to go into details. But we use also microstrip antennas. We call them strip lines. And we have many, many, many other RF designs, like shoeboxes, slotted waveguides, resonant cavities, wall current monitors. We have also magnetic horns. We have also Yagi antennas and direction finders to make sure that we don't leak any of our RF frequencies out into the wild, not to make any plane land on our site. And sort of rite of passage is for us that you have to, in one of your career, you have to at least build one of those devices as a test and as a rite of passage, that you say, like, yes, I'm an accelerator physicist, I built some stuff and I know how this works from the ground up. Then, because these are antennas, we have a very common post-processing, like analog front-end chains that come into heterodyne or super heterodyne post-processing. In our case, we place antennas bidirectional, so this is a bit like a phased array. You have like 2 antennas, you look at the phase differences and the amplitude, and out of that you can derive information like, what is the intensity of your carrier? That's basically how many particles do you have in the accelerator. What is the position by the imbalance between one antenna to the next? There we use like typically hybrids. This is still like an analog solution. But you also get information on the shape of the beam, which is sometimes very crucial because you want to have them compact in a very high brightness, so you want to put as many particles into a small plot as possible. And as in normal telecommunications, of course, because we have to be flexible, we push a lot of those stack, which was initially very hardware centered and focused and purpose-built. We want to become more flexible. So many of the things are exchangeable or programmable. And then similar to most radios, like going from the right, the software-defined radio toolchain moves more and more towards the left, where this is then replaced from analog with initially DSP-based systems, but now more and more FPGAs, and leaving the analog part just to the most essential part that you still have to treat an analog for conditioning your signals. And yeah, I mentioned about tune. So if the beam oscillates and doesn't have like nice frequencies, it becomes unstable and leaves the beam. So I brought like a more small audio example. Maybe somebody can help me playing that sample. Can somebody click on the top right, please? I brought like a small example. Left 2 channels, left, right is like horizontal and vertical motion. And this is basically some of the frequencies are audible. That doesn't sound good. And if you agree with me, it doesn't sound good, and it's also not good for the beam. This is like an instability that we have. And this can cause massive losses in the accelerator. We have to detect this. On the one hand, you heard about like a bit like this ping, ping, ping noise. This is like a kicker. This is a bit like we're hitting a tuning fork on the beam and making it resonate deliberately, but a teeny tiny amount, by just a few nanometers. And then we listen, is it still in tune? And in this case, it's reasonable. It still moves. It's not flat. That would be a single tone. But then yeah, we hit, one of the frequency hits a resonance, and then beam becomes unstable, and we have to detect that. So first we have to track what is the normal oscillation frequencies or modulation, and then if we see every now and then, because of a variety of reasons, we have like transients that can cause this, and we have to capture that and then store it, log it, analyze it, and find mitigations to improve the performance. This is like another example, if you could play on top, please. Here you can see the same thing, but different cycles, where you can hear that's a multiplexing. So we have a repetitive mode where we schedule different beams one after the other. And then you can see like that sometimes things stay the same, but we're looking from one cycle to the next always on the differences, because they sound similar, a bit like a spaceship or alien. And yeah, here the case is that the machine is mostly doing like periodic things, where you want to monitor is one execution to the next the same, or do you have variations? And for this, I took this as an example because we have multi-user operation, multi-mission, where the same device is not just used for one experiment, but by up to 20, 30 different experimental users at the same time that all have different post-processing needs for the given application. So they all have the same detector, out of which we have sometimes 12, up to 89, or sometimes even 1,001 in accelerators. And they use different combinations and different post-processing strategies for the given experiment that we need to provide on a changing basis. On a second scale, we have to switch from one mode to the next. And that's also the part where we use GNU Radio to make this more flexible, to have like certain common signal processing functionalities available out of the box, but then having this multiplexing concept where we can select, we can quickly reconfigure our SDR based on the individual need. And yeah, the sensitivity, it goes even that down that we can detect single particles. So here you see a Schottky spectrum. This is now around 200 megahertz. So this is basically a higher mode where we look into the shape of the bunch. You can see like 2 lines. The 2 lines are basically 2 different species of ions that are injected. And then you can see some small lines that head onto the second line. This is basically when another species is captured and cooled down. So initially it has like a wrong energy and is dragged by the cooling system onto this new trajectory, and then is operating. And on the right you can see the same thing, that you have something on the bottom left, like do you have a laser pointer here? No. Probably not. But you can imagine like on the left, you have a left trace where you goes up, and then you have like small branching off into the right trace. This is basically where some of the ions decay. So this is like the first sign of nuclear physics. So you store one isotope beam, but then you can monitor the nuclear transformation of one radioactive isotope into another in real time, which normally is very tough because you can't predict when this particle decays, so you have to be ready all the time. And then once you detect this, you have a transient recorder. It's like, please store the last 1 second before and the next 10 seconds afterwards, because often once you have like one radioactive decay, you have like a cascade of other chain reactions. And this is very important because if you want to understand how the super heavy elements are produced, you first have to produce something beyond uranium, and then you look at the decay chains. And the ratio of the decay chains give you information about why we end up with so many heavy elements on Earth like iron and others. And there was also like a paper published early on. This is a very rare two-body nuclear decay that was what has been measured with such systems. And this is like a single particle detection. So in terms of sensitivity, you have, it's quantized, so you can't have something that provides less signal than a single particle. We also do single photon detection. Now the thing is, this is just observation. This is very similar to astronomy and astrophysics. Now the big difference is that we can prepare an experiment. It's not that we just observe randomly occurring effects, but we can also tailor our experiment to be repetitive, to always have basically the exact same outcome. And if the energy is not correct, we can say like, okay, we tune our reaction so that we can have an optimal use of our detectors to see this physics that is occurring on the target or on the beam. But because of environmental influences, this might not always be the perfect conditions. And you have deviations, which is like illustrated here by this deviating beam path. So the important thing is if you measure something, you need to know what are like a transfer function, you need to know what you put in and what comes out. This is just like observing. For that reason, we have like lots of like eyes and ears, which are diagnostic element from, most of them are electromagnetic nature, but some of them are also optical or also intercepting ionization chambers and looking at showers. And this is the part where we're already using GNU radio since probably 2 decades. Maybe not advertising as much, but if you're dealing with RF signals, you want to have a flexible prototyping platform. That's where we used GNU radio since long, because it provides a certain flexibility that you can try out something with students in the university, put it in the lab, trying it out for real, and then deploying it also if it's useful for regular operation. And that's also the part where we got in contact with Derek and Josh, because having a prototype is one thing, but in the end you have to maintain something that runs 24/7 and beyond a length or lifetime of a PhD student, so it has to work more than 3 years. And then long-term maintainability, security, but also other issues become an important issue. But often some of our diagnostics is not just a CISO system like single output, but we have to combine the information of many detectors across the facility. So we have to combine them. But before that, in that case, would be still very simple. So you monitor your state, you compare it with a reference, and then you have a difference. And if you have just an open loop system, like you have in radio astronomy, that's it, what you can do. So you have to adjust your detectors and hope that it stays stable. But the advantage of using a particle accelerator, we can modify this, can look at the difference, and then adjust with a powerful set of corrector magnets and additional RF cavities. We can basically modify the beam particles in a way that the deviation from what we actually want to have and that what we measure with those devices vanish to zero. And that works both in the single input, single output case, but also for the multiple input, multiple output case. And there we use also GNU radio to provide like high-level diagnostics and feedback systems where we aggregate the information from hundreds of devices, do like a smart post-processing, use also like AI-based algorithms that drive basically the difference between the reference state and the actual state to zero, which is then used to feedback onto the machine. And that is something very special, because there comes from us like the requirement that the whole diagnostic part, also the group delay, the feedback path has to be very short, so that you have a stable and fast-running feedback system. So we're talking sometimes feedbacks on the timescales of a few seconds. That's very slow. There we use like chunk-based data processing, but we also have cases where we have like sample-by-sample processing, where we have feedbacks that are running as fast as with group delays of 1 or 2 nanoseconds. And there's like a big gap where now with the new GNU Radio 4.0, we hope that we can maybe achieve something also that covers in the middle for latencies in the order of milliseconds, and maybe with the help of FPGAs, maybe also a few 10 microseconds. So yeah, the main thing what our department does is doing system integration, both of the vertical stack, but also the horizontal stack, and providing basically the orchestrating the setting supply in order to configure all of these devices. And also we have a very powerful nanosecond timing system, White Rabbit, maybe some of you have heard of it. Together with CERN, we are the co-developers of that, and also use it massively to synchronize our SDRs over the facility. And yeah, then we use it for different applications, for monitoring and web type status applications, or also for interactive control and feedback applications, and also for new AI-based research. And our main protocol stack is using OpenCMW, which is 0MQ-based middleware, GNU Radio on top, and yeah, AI typically TensorFlow and this type of things. Now, these are just some examples where I'll glance over very quickly. These are some feedback examples for the orbit and trajectory on the left, which is a bit uncontrolled. On the right, you get a flat line. But we also use it for Schottky monitoring, where we monitor the energy distribution and energy center as a function over long periods of time, and then apply trims to the cavities and magnets in order to bring it back. If you have further detailed question, please ask Alex. That's his baby. He developed this application and also the underlying post-processing framework. Or also we control the particle spill rate, because we have a means of particles are kept in an RF bucket. This is like a separatrix, and if you start shaking the bucket, then some of the particles spill out of the bucket. And by shaking it properly, you can have a linear spill rate. And in order to get this linear, you have to you have to have a very specific form of RF noise that you have to generate, and then you can control this. And this was like a proof of concept on the left, where initially I wanted to do a Dirac pulse, like a flatline and Dirac pulse, but I think this was showing the finger was not something that you could publish. So my colleague said, like, can't you do like a bunny? And so we said, like, okay, let's control the spill rate and make a bunny just because we can. We played the Beethoven's Fifth on an accelerator, that also works. But normally people want to see something on the right where you get a very smooth, flat rate. That helps our experiments to tune their data acquisition system to always have the same constant input beta bandwidth, and then they can write down up to 20 petabytes per year of data. And that's the flatter and the more constant beam delivery we have, this is basically worth in gold. 20% performance means that an experiment effectively runs 20% more, and a day of operation at this 18 alone costs about $80,000 to $90,000. So if you get 20% more performance out over an operation period of 200 days per year, that's a lot of bang for the buck. And sometimes the feedbacks work quite well. Basically, people don't look at the actual parameters anymore, but they just look at the feedback actuator signals and then calculate what would be if it wouldn't be, if you would switch the feedback offs. And there you can see on the right, like a plot for the actual tunes, they're actually flat. But if you unfold it with the actuator signals, then you can see this is a bit like the electric wire. So if you look on the left, all this diagonal lines, as if the beam hits one of those lines, you would lose it instantaneously. And the beam is kept, and then, but we can see what type of resonance we would have had hit if the feedback would have failed. And this is type of the diagnostics that we also derive from our GNU radio integration. And sometimes people don't look actually at the parameter anymore. They just look, is the feedback on? And if not, they call like, oh, your feedback switched off for some safety reasons. Could you please switch it back on? And then it's our task to look what fails. But people then just look on how much work actuator signals the systems had to drive. We have also like something more. This is a bit to my heart. I myself, like also by training an analog RF engineer, we have a program which is AI-based non-intrusive load monitoring. This is very fashionable. This is like how to measure the power consumption in a household, in our case industrial scale, where you just have one power meter. But as you all know, if you have switch mode power supplies, they always reflect a certain part of their energy back into the network, and each of switch mode power supply has a very specific fingerprint. This is known since ages as Van Eyck fracking, or like Tempest, like here in the US. This is like a program since the early 70s. And we thought, like, let's put it to good civilian use. So whenever you connect something to our network, we recognize the fingerprint that is reflected on the network. That, by the way, works also here. If we monitor this here, you would see all the nice notebooks that are connected and see whether they're on, off, or if you go to very high frequencies, you can also reconstruct HDMI signals. But we use it basically to disaggregate and make sure, are the devices consuming the power that we anticipate, and to make a refactoring, or if you see that some device is left on, then we can purposely switch off. But also you can identify malfunctioning or degrading or inefficient equipment, and this we want to use for scheduling preventative maintenance and to induce like mitigating measures. I mean, we have been using this already on the device level, but the new trick is just to have one single detector per network, and then to derive it from at a single location, which is very cost effective, rather than having to roll out an instrumentation of 10,000 devices on their own. So this is a bit like on what we use. We use fairly commodity hardware, In this case, we have a few digitizers that go down to DC, but also some classical SDRs, starting from 100 kilohertz up to 4 gigahertz. And then we package it into this 19-inch rack form, just because it's better for our rack-based environment. And also we added like a double redundant power supply and HMI board, because we're having now more than 200 of those systems that run GNU Radio actively, and we're now building up to 500. And when Josh introduced what is GNU Radio used for, in terms of usage of nodes where GNU Radio is running, you can say like GNU Radio is used for controlling particle accelerators with the co-use of telecommunication applications, unless I'm joking. But we have a massive investment in the usage of GNU Radio, because it helps us to manage a very huge park of different nodes that each have different requirements, and to keep bring order to the chaos. Now this is like just a classical deployment of our facility. On the left you can see the power monitoring that we have, a couple of racks, and on the right you have like one of the more denser deployments where we have instrumentation which basically pick a packed full. The reasons we have like this pizza box format is because these devices are distributed over an area, over a length of particle beams of 4.5 kilometers. And except of those locations, we place them wherever they're needed, because the signal quality is best when you're close to the device as possible. So we said like we need a very small form factor and very independent form factor that we can monitor remotely. And because most of the parts are not accessible during regular beam operation, they had to be robust and reliable. That is one of our key requirements, because we don't have that many staff to run around and replacing digitizers all the time. So we had to make sure, the digitizer hardware has to fail, and if it has to fail safe, that's the reason for the HMI board. They're designed to have an MTBF of 300,000 to 400,000 hours. We can't confirm that yet, because we didn't have yet failures. But with the number of devices, when we go to 500, this is critical, because we can't replace it on a day-by-day basis. So we have to accumulate that. We have replaced them scheduled on a 2-week basis, which is a normal case. It's basically similar to space equipment. Once you put it up into space, then you can't fix it. That's also the reasons why the ESA is coming to GSI in FAIR to test their equipment, because they want to make sure whether their equipment survives the solar wind flares and the conditions you have in the outer space. So if we can't break it with our beams, then they say like, okay, we have fingers crossed, it's a high likeliness that they will also survive going to Mars. Okay, this is like our old integration. We have been using GNU Radio 3.7, where basically we have like 2 types of processing. One is the digitizer handling is done directly by GNU Radio, and the sources and the sample by sample processing. But because some of the signals we have are recurring, are pattern-based, we needed also like a chunk-based data processing. So we passed the data on from the GNU Radio layer up to like another processing layer, which we used for a long time, used the disruptor pattern. And later we also played around with RxCPP. This project unfortunately has been abandoned. And if you look like one of the, why do we do that? Why do we use GNU Radio? It's basically to bridge the gap between like research software engineering and the domain experts. They all have the critical role in operating this facility. Not every research software engineer is a domain expert in RF or the other domains that we have, like cryogenics and magnets and so on. And not every RF expert is necessarily a good research software engineer. But we all have to speak the same language, and using this flow graphs is a good way of communicating the high-level intent, what you want to achieve. And by looking at from the top, from the flow graph topology, and also from the bottom, what it entails on the implementation, this is a good common communication factor and organizing the different processing across the whole facility. Now, just to give like a small example, this is one of the fairly simple flow graphs. I was pleased yesterday to hear that GNU Radio has like a complexity estimator. We cheated a bit, because ours, if we don't do this simplification, we end up with a couple of 10,000 or a million, because these flow graphs have literally thousands of blocks. And then if you think about if you daisy chain lots of blocks, you have a lot of interface problems from one block to the next. If you have a long chain of 10, 20 blocks, then you spend more time transferring data into the buffers and out of the buffers than doing actual work for the signal processing. So that, like most people, I guess, did also in the industry, they use this for prototyping, and when they see like we need like a real high performance application, then they probably redevelop the chain based on what they prototyped. And we realized we can't do that. We did it for a few blocks, but if you scale this up to 500 systems, that you can't maintain. You don't have enough staff to do that. So we, initially, like most other people, so this is just like a topical view of what is inside, so I'm not going into detail. There are many, many, many different blocks that are basically hidden into one of those larger blocks. And yeah, we identified a couple of issues. I mean, like, it worked. It was used in operations, but we have certain industrial constraints for a large setup. I mean, like, we have a certain needs for enhanced safety, reliability, and maintainability. That's an issue with respect to using Python in the field because it's not certifiable from a critical infrastructure point of view, which we are. And also the problem is in terms of maintainability, the life cycle of Python is very short. So basically every other year you need to upgrade and modify your code so that it keeps running. We can't stay behind because if you don't do this critical security updates, we're hackable, and you don't want to read nuclear research facility nearby Darmstadt got hacked, potential leak of radiation is not excluded. You don't want to read this ever in the newspaper, ever. So we have to be careful and have to be safe. And that was a limiting. While Python is very powerful, we have to be able to run this in a pure C++ environment. We use Python still for prototyping. Also, when people use a lab setup or in the universities, they use Python. And there's the GNU Radio flow graph expression in GRC is very powerful and helpful because people can experiment. It's like, oh, that's my flow graph definition. Could you put it in the machine? And then we take the same GRC file, download it into the front end, and then it runs what the people did in the lab or in the university. That's very good. But with the 3.7, there was an absence of compile-time reflection in the central block registry that makes things very hard. And that's the reason why we wrote like this GR flow graph lib. And maybe that was the hook why, because Derek, I guess, randomly Googled and said like, oh, there's some research facility that has some GR, does it have to do something to do with GNU Radio? And he got in contact with us. And yeah, we identified some of the other issues. I'm not going into detail with that. But the game changer was actually when we got adopted by the GNU Radio community in a sort of way by Derek and Josh, because they recognized there's a potential of synergies that we could collaborate. And especially because Josh and others in the other architecture team was in the process of developing the new GNU Radio 4.0, the question was like, could we contribute? Could we maybe share our experience and contribute some of our expertise? Because we have, in terms of high performance computing, we have a very strong expertise in that domain. Could we contribute some of that to the next GNU Radio to make things more agreeable, more easy to use? And then about a year ago, we got first invited to a joint GNU Radio architecture working group meeting and discussed our use cases and some of our issues. I mean, prior to that, Josh, I mean, he's a hero. We were struggling with this GR flow graph because we had to do a lot of workaround implementations, which basically our wraparounds were, it felt more code than the GNU Radio core itself. And Josh approached it in a manner like, how hard can that be? And without further ado, 2 weeks later, he said like, would that work for you? And I apologized that it took him 2 weeks, which for us was like wow. And we tried it and worked out of the box. And I was like, there's something. Let's discuss. And that kicked off the first of many, many, many stones. It was a very, I think until now, seems to be a very, very constructive collaboration, which also on our side was very useful because it attracted a lot of very high performance computing and C++ champions. And there we're talking about the 1%ers. I like the best of the West worldwide. Matthias Kretz and Ivan Kucik both are senior members of the ISO C++ standardization committee, and they know what when they're talking about when they talk about high performance computing and C++ designs. And they said like, hey, that's an interesting problem. We want to modernize anyway in that area. Maybe we could use and trial some of the concept with this new GNU Radio 4.0 and see whether it also works from a user point of view, and maybe polish some rough edges and see that we get the best possible standard out. And yeah, that enabled many innovations and focus improvements that will also flow back into the ISO C++ standard, likely in the C++ 26. But which is already now available as a library, external library feature. And yeah, some of the major technical achievements, we developed a new I/O buffer and out-of-the-box SIMD support, which is about at least multiple orders of magnitude faster than the existing GNU Radio 3.x implementation. We needed to write this actually to in order our chunk-based data processing, because the old GNU Radio buffer only allowed fundamental types, but we wanted to process also accurate types like data sets and vectors. This is now possible. and certain modern C++ features allowed a more efficient design, and I hope a better user experience. The importance I want to make here and stress out, we want to preserve what is good in GNU Radio. We don't want to break with tradition. We want to make the experience and the use for everybody as smooth as possible, and hope that with the proposal that we contributed and that we present tomorrow in a bit more detail for review, that this finds interest, and maybe where you say like, yes, that's perfect, or yes, that's perfect, and could you do this? Or maybe it would be even better if you change this functionality. So I hope for a very lively discussion tomorrow or in the aisle. I put up already the slides so you can have a sneak peek to get a bit of a flavor what we plan to do. Yeah, at FAIR we're fully committed to open hardware and open software. We are signatories of the Public Money, Public Code campaign. Please have a look. That's very worthwhile to sign. You can both sign individually as organization and as if you're a government agency, also as a government agency, as we did. And based on, since 2002, Q3, we started actively modernizing our stack from GNU Radio 3.7 into 4.0, and where we basically embed now GNU Radio in everywhere, from the front ends in the middle tier service that perform the feedbacks up to our user interfaces, so also top-level applications running on WebAssembly. So now you can run GNU Radio also on the web if you like, without having any wrapper or a service infrastructure. So it really runs in the browser. And we aim at a full compatibility with the GNU Radio Companion, and want to further keep strengthening the GNU Radio system, not just because we use it at our facility, but also our users use GNU Radio, and we want to make this transaction or delivering it from prototyping into operational use as smooth as possible and as sustainable and as maintainable as possible, so that this GNU Radio is a versatile tool, not just for prototyping, but also for industrial use. And we're looking for fruitful discussions on these topics. So yeah, we built a lot of tools. Like some final new message, never stop learning new things. Learning and knowledge is about, for each generation has to learn anew, and we have to work and be open for new styles and new things. And I hope that we all stay curious, experiment, don't be afraid to make mistakes, because to err is human, and to learn out of this is what makes us succeed. And this is all part of a continuous learning improvement process. And yeah, thank you, and looking forward to GNU Radio. I overrun, sorry.
That's perfectly fine. Are there any questions?
You have a question? Or do you look for your pitchforks and torches and I should find an exit?
Stunned into silence. We will be having our break in just a few minutes. I think we have a couple of lightning talks first. Is that right? No, that's later. Break is now. Please, yeah, we've already had one round of applause, but please do enjoy the break. Thank you very much, Ralph, again, and come back tomorrow, same time, for much more information about the actual technical content of GR4 after having gotten this motivation. So, thank you very much. get ready, that'd be great. Just for the folks in the room, I did want to ask if anyone, the food has been pretty good. We've been getting compliments on it. Thank you. But if you have any issues or concerns about the food, please do let us know. We're pretty sure that there's 3 or 4 people who may not be getting specifically the dietary items that they had noted on registration, and nobody has come up to us and let us know that that's a problem. If it's a problem, we have potential solutions. So please, if you have any concerns about food, do let us know. Otherwise, Andy, please, we'll get you started.
Yeah. Do you hear me? That's fine. Okay. So, hello. My name is Andrew, and I'm a co-founder of WSDR project. This is the project web-based SDR platform for learning, hacking, prototyping, and collaboration. So previously at the GRCon last year, we presented a new concept, how we can work with the SDR differently. So in a few words, we wanted to change general approach in the workflow because the traditional method requires a lot of effort and have some drawback and obstacles, especially if you're a beginner, it could be a problem. So a year ago, we started to developing a platform that aims to eliminate all the drawback and some limitation, specifically with the SDR hardware. So the idea was pretty simple. Anyone should be able to start using software-defined radio hardware with minimum knowledge. So basically, we want to get rid of the installation, software dependencies, and other distributive issues that may come along the way. So today, I want to share with you some progress in the project and showcase some demo. So yeah, let's go. Surfing on the web, we came across a web USB technology, and since modern web browsers are no longer slow, it enables direct communication between USB device and web browser. So we started to incorporating our own software libraries into hardware support libraries into the web, so making our SDR just plug and play. Along with that, we thought it would be cool to create some basic application and visual tools. So thanks to WebAssembly and mScripting project for that, because now you can write code on C++, C#, Rust, and Go, and port this application into a web. So yeah, right after we developed a few applications, one of our friends said, hey guys, why don't you create something big, like a full autonomous cellular network in a browser? And since we all have a telecom background, we decided to give it a try. And we picked Osmocom stack for that. And it wasn't obviously at all how to put all the components from the Osmocom into the web browser. And here's begin our journey. The complete 2G network from the Osmocom consists of the following components, which each one is a separate Linux process. So firstly, we remove all the GPRS and Edge component, and then the secondary issue was to figure out whether to put all of the components into the web right away or start with the simple step like streaming IQ data directly in the cloud where all other components were running. So, yeah. However, this approach requires you stable internet connection and predictable latency. The next step was compile Osmo TRX, and this was the significant task because because the threads responsible for DSP function were pipelining data in a small fraction, like 2 milliseconds, and this works okay with the Node.js, but completely not with the Chrome. And the main problem was in unpredictable latency between OSMO-TRX component and OSMO-BTS component. So we resolved this issue by putting both component on dedicated web worker within a web browser. And then this is eventually how we were able to make it happen and finally make our network stable. Even the smartphone can become a base station. So yeah, let's move to the demo. Here's the WSDR main window application. I always logged in my account. And here's the Silver Network app. I have my SDR right here. So let me plug it in. Okay. Sorry. Got small space here. Now. Yeah. Got it. Yeah, it has recognized. So basically, how it works from the end user perspective. Here's the source. We choose as a source our WebSDR, connect. Then we set configuration, which is RFCN for the base station. We pick like any configuration and hit run. That's it. This is how we making base station out of the laptop. So here's a simple phone. It's running on my phones. Oh. And they usually, yeah, you could see on the log that the phones has been already registered. But usually you can go just to settings, network, and choose the network manually, and there's going to be like an OSMOCOM. So this is how the network works. And since I know my numbers of this phone, I can easily like call from this phone to this phone. And you can see on the log that call is processing. Zoom it? What do you mean? No. I mean, like, there's so many, like, there's so small space, so basically, I mean, like, I don't want to break anything. Yeah. Hello. I mean, like, anybody can, like, come over and test it if it. So yeah, basically, the base station processing happening in the browser, while the core network itself in the cloud. So with all that being said, you can deploy open source private network like worldwide easily and make a call like between all of them like easily because your laptop is becoming your base station. So yeah, this is the 2G call based on OSMOCOM stack, available online and working from the web. Sorry. Okay, so let's get to the platform. The platform, the platform itself is an extensible framework upon you can run a different application. So far, we developed 12 ready-to-use applications, such as a spectrum monitor, signal analyzer, AM and FM receiver, and even AI signal detector. So yeah, let me just click on there. So since like machine learning is gaining a lot of like attention nowadays in our industry, so we were curious too. And as far as I know, the TensorFlow GS with the GPU accelerator became available in web GPU within the browser. So we took our own like a simple approach with using a convolutional neural network on IQ diagram to detect signal. So basically, here's the pretty much same thing. I'm picking my device and hit run. Oh, yeah, sometimes it can reload the application. yeah, this is what happened when you do not upgrade your platform before the talk. So yeah. Yeah, like you see, this is the AI analyzer lock, and it's detecting my mouse. So Bluetooth, and yeah, the proof of concept working great. But however, you need to learn this algorithm to get more detection. Okay, so what's next? Yeah, another great thing is a shared device and receive the signal remotely, because since the application receives data directly from the hardware, you can receive remote streams over WebSocket, as well as you can share your device like within as easy as just sharing the link. You can see right here, this is the link. This is the link to my device. If I would like to share the stream with anybody, I just send this link to the person who would like to get access to my recordings. And now we just recently did a great showcase with a friend of mine. He's like in Georgia at Tbilisi right now. Georgia is a country, and he's streaming local radio station, and we can receive the stream like pretty much the same process. So just instead of the hardware on the source dialog box, we're choosing the streams, which has already been set up in the streams in the main window. Anyway, so basically, yeah. This is the radio station coming from the Tbilisi, from the Georgia. So also you can highlight the specific area. It's worked pretty well when you do the FM receiver with the different parameters. So yeah, Lo-Fi chill. So another great feature we implemented is a simple storage, the file storage to record, to store and record all your signals. So let me. Oh, right. So far we can add like storage type as our own internal storage, WSDR storage, or we can use a third-party Azure so far. So we're working to get like more providers of the storage in our platform, but it works pretty much like the same. So we pick the type of the storage, we set the container. So if it's shared container, you can pass like here a link from a person who's sharing this link, and you will be able to access recordings of this person. If it's private, it's self-explanatory. It's private container. You can upload. You can upload your files like from the computer, or you can edit file right away, like SIGMF configurations files. So yeah, and it's pretty much useful tool because let's say you wanna analyze the signal, and when you do the signal analyzing, you just pick in this file from your storage directly. So this is the Bluetooth low energy signal. And here's the different parameters you can tweak. You can look at the signal. Also, you can decode the signal. You can highlight like specific area, change the modulation type. Some tweaking stuff here, and the decoder. Yeah, and as you can see, there's an information of decoded signal right here from the stream. So yeah, also the great feature of the platform, since like it's web-based, I mean you can upgrade your like firmware directly from the platform. So this is as simple. Unfortunately, I unplugged my device and I can show you, but believe me, it works. Yeah. So the other part I want to add that. So all the tests, all the development has been done on our own SDR. However, we're working toward to get Lime SDR and XTX Revision 4 and 5 supported by our platform. And I believe most of the people here have either devices. So basically, I encourage you guys to sign up for an updates at the website or the Twitter, because once we officially release this platform, you'll be able to use your device to test it out and send us feedback and let us know how it goes. So, and anyone, if interested in learning how we made a different application, also please go to Twitter. There's going to be a link for all of these updates with the greater details, how we create 2G cellular network based on ASMACOM stack, how we use machine learning to detect the signal, etc. So yeah, thank you so much. This is the platform. Any questions, guys?
We've got time for a couple questions.
Yeah, great talk and demo. My question would be, as you suggested, it's for 2G. Can the similar platform be used for like 4G, LTE, or above? Thank you.
Sorry, say again, please.
Yeah, my question was, like as you mentioned, it's for 2G.
Yeah.
The platform, can the same setup and platform be used for 4G, LTE, or above, or even 5G?
So basically, we use the 2G ASMACOM stack as a proof of concept. So far, we working toward to get LTE in the web, but I mean, like, there's a unforeseen, like, it's an unforeseen future. So, but so far, no, there is no like LTE like implementation in the web browser, at least in our company. And yeah, I forgot to say that we didn't forget about the GNU Radio community. So basically, we have a component GRWSDR that will be released as well as platform, and you'll be able to data stream like directly from the GNU Radio into WSDR. So yeah, just before I forget. Any more questions? But anyway, thank you for your attention. You can catch me in the hallway, and I can give you more details and show something else from our platform. Thank you so much.
All right, next up we have a sponsored talk from Analog Devices.
Is the clicker? Or see if this works. Yeah. All right, good morning, everyone. It's great to be back at GRCon. Great to see so many familiar faces. My name is Travis Collins. I'm a software manager at Analog Devices. My team focuses on transceiver-based systems, high-speed converter systems, as well as a lot of other components that ADI makes. If you're familiar with like the Pluto SDR, my team helps support products like that. Today, I'll be talking about some direct RF solutions that we have coming out. We'll have some corporate slides, but then we'll kind of get into some new interesting products that we have coming out. Now, if you're not familiar with analog devices, we're probably most known for our converter technology, our RF products, amplifiers, LNAs, mixers, and we've really grown our portfolio over the years through a number of acquisitions such as like Hittite technologies, where we've really grown our high-end RF space, with linear technology, gaining more converters, as well as power products, and most recently with the Maxim Integrated acquisition to even push our portfolio even wider. And we're really providing full, we say like RF to bits solutions, and we're really a one-stop shop for that at ADI now. Right now we're a pretty large company, around 25,000 employees. We make 45,000 or more products, depending on how you count them, will determine what a SKU is or not. I feel usually sorry for the FAEs who have to deal with all these products and keep track of what they are. But it allows us to help you solve your most challenging problems and look at things from a true system level, where we can go from that front end, from your antenna, all the way back to your digitizers and getting data into your processing units. Now, I would say ADI does a few things really, really well. First of all, we integrate pretty heavily. So we'll take algorithms, we'll take new technology, new features, and put them inside ASICs that we design so that you don't have to kind of implement things like IQ correction or automatic gain control, and we'll put those inside chips and allow kind of easier use and simpler, much simpler systems that you have, or more capable systems. And the second thing that we do really well is we really push the boundaries of technology. We're always pushing things to be more power efficient, faster, smaller, to make your systems much more capable. And this is really what I want to talk about kind of in the remaining of the presentation, is a product that is really pushing the boundaries of receiver and transmitter technology, and is going to be really disruptive in the marketplace. So if we just kind of start off first and talk about receiver technology over the years, typically, we have three common architectures when we're looking at receivers. So in the top left here, we'll have a superhead design. And this is your real traditional radio, real high performance, but a superhead will require multiple mixing stages. So we'll have an IF that will bring a signal down to of interest, and then we'll bring that down again to baseband to do our final channel selection. And these systems are really high performance, but they typically require a lot of power and a lot of board space because you just have so many discrete components. In the kind of the center bottom here, we remove a mixer stage, and we have what we call a zero IF or no IF receiver design. And a lot of the radios that you likely use today in your classroom or at work are likely this technology, because we're at a point where the performance is good enough, the power advantage is there, that just using this technology makes sense for a lot of the applications that you have. So the third one is kind of this new evolution or new frontier that we've been seeing and that we're enabling, I would say, now. I remember being a grad student and people were talking about direct RF or direct sampling and using radios of that architecture. And at this point, we are really here. We can do this, and we can go up to things like directly sampling X-band with our latest generation of converters. So with direct RF, you don't have any mixing stages. You directly sample from the antenna. You'll likely have some gain stages in there, but we're not mixing. We're doing everything digitally now. Now, this has a lot of advantages. The good thing is that it really decreases the complexity of your front end. You don't need multiple mixers. If you have a phase array system, typically with a superhead or a zero IF architecture, you would have to synchronize all of those front end pieces. When you remove them, we just need to make sure that the converters are synchronized. So you have fewer kind of components that are in your system. You can physically have a smaller PCB footprint because you're removing those components. simpler to synchronize, and you get access to all this, like a large degree of instantaneous bandwidth now, since you can look simultaneously at, from DC to whatever frequency that you need to operate at. Now, unfortunately, this does come at a cost. One, you have to deal with that data. So when we're talking about like gigahertz or tens of gigahertz of bandwidth, you have to process that, and you have to be able to deal with that. And that's what we'll kind of focus on. Now, the second aspect you need to be aware of is that when you have direct RF systems or direct sampling systems, dynamic range is really important, because if you have, say, a strong interferer, that's really going to affect the sensitivity of your system. So you cannot, if you have a very strong signal somewhere in, say, like a low band, and you don't really care about that, you need to filter that out some way, or have a very high performance converter that can give you the dynamic range that you need to handle signals like that. So ADI has been building such converters, direct sampling converters, for almost a decade at this point. We started off with wideband DACs in 2014. We added on the ADCs soon after that, and more recently we've been provided more integrated components. So in 2019 we introduced what we call an MXFE, or mixed signal front-end component, and this includes DACs and ADCs in one chip. And most recently, what we'll kind of spend most of the slides on is our latest generation called Apollo MXFE. And this is an ultra-wideband part that comes in two variants, a 4-transmit 4-receive and an 8-transmit 8-receive part, but at very, very wide bandwidths. So let's talk about Apollo. Apollo is, we don't typically release code names of parts, but this is kind of the exception to the rule here. The actual name of the part is Apollo MXFE. This is an extremely wideband part. It has 20 gigasample ADCs, 28 gigasample DACs inside. So there are 4 of those, 4 ADCs, 4 DACs inside the chip. And the laminate allows you to go up to around 18 gigahertz in actual RF bandwidth on the chip itself. So going beyond that, you'll just see further degradation of the signals that you have. But an extreme amount of bandwidth. So we're truly sampling X-band directly with this ASIC. So just to give you a little bit more detail, it's not just converters inside this part. So we do have those really high-speed converters in the front of it, but on the right of this diagram, we can see there's lots and lots of digital that is inside the chip. So we're adding filters, decimation stages, NCOs. There's actually an FFT sniffer inside, so you can run an FFT at 20 gigahertz inside the chip. So you can look at the front end and actually trigger pins on the outside of the chip if you need to react to signals that are coming in. But we're adding this DSP so you can deal with that 20 gigahertz, that 28 gigahertz of bandwidth that's moving in and out of the device. So pretty kind of extreme bandwidth that we're talking about here. Now, this kind of brings up a little bit of a conundrum. How do you really deal with a gigahertz or 20 gigahertz back in something like GNU radio or any processing that you're doing? With even kind of standard transceiver-like devices that we have, where we're dealing with like tens or 20 or hundreds of megahertz, that is still challenging to do. Can we just hook up like 8 100 gig Ethernet connections to this thing and deal with that in GNU radio? You could try, but the chip is really not meant to be used like that. It's meant to be used with the DSP that's inside of it. So this is really what I want to kind of focus on here, is how the chip is meant to be used, how these direct RF parts are designed, and how you would want to use that with something like GNU radio. So I just here have it zoomed in on the 1/2 of Apollo. So it's just kind of mirrored the chip itself. We call it east and west sides. But on the top of the diagram is the DAC side. So we're coming in over GESD. We're going through different interpolation stages with NCOs, and then streaming out the DACs. And the receive side on the bottom is really just the same in reverse. So we'll have similar filtering capability, we'll have the FFT sniffer, we'll have decimation stages, and that will go to our SerDes lines over GSD, back to our ASIC or processing unit or whatever you want to put on the back end. So now, if you kind of look at this in a traditional use case or use mode that a lot of our customers would take from our older generations of data converters, you would kind of like think of it like, well, I'll just take the converter and then route the data all back to my processing unit. I know how to program an FPGA, I know how to program a GPU or whatever, let me just deal with that. And you're sucking in that full 20 gigahertz of bandwidth, which is, if you're used to doing multi-sample processing on an FPGA, 20 gigahertz is pretty extreme. So we would not really recommend using the part this way, but you can do that if you want that large bandwidth that's coming into the device. So really what you want to do is think of Apollo and the general MXFE family as a large channelizer. You want to use the decimation stages so we can pull out signals of interest and then just feed back the signals that we care about back to our processing units. So you don't want to suck back that 20 gigahertz. You want to enable as much decimation as you can, reduce the data rate, and just pull out the signals that you care about. Now, the nice thing about Apollo is that the internal decimations can all be uniquely configured. There are some rules around this, but you can independently set different channels. So if you want like a 20 megahertz channel, a 40 megahertz channel, a 60 megahertz channel, you can set up the part to do that all simultaneously. And you don't have to kind of have it completely fixed. You can actually change things so adaptively you can move and look and scan and then pull out the signal of interest that you want later on during runtime. So the chip is highly dynamic, is highly meant to be used in a way that adapts to your signal conditions for your environment. So, this is how you kind of need to think about these parts. It's not just a giant converter I need to deal with. It's a giant channelizer that I can use and selectively pull out the signals over that very large bandwidth that's coming into the converters. Now, to help with this, to help use the part directly, we've expanded out the configuration controls of the device. So here we just have kind of a system view where on the far left is the data converter, which will be might be on the same board or on an FMC card that you have. We'll have the FPGA in the middle, and then we'll have something like GNU Radio on the far right where we're doing our processing or we're doing our kind of control layers in the system. And the chip has been expanded to include more configuration control. So if you're familiar with like SPI, that will maybe go up at most like 100 megahertz. It has a similar interface that runs at 1.6 gig. That is a very high-speed control. So it's like really high-speed SPI. Think of it that way. There are 32 GPIO pins, so we can do lots and lots of dynamic changes that are deterministic, that map to over 120 functions on the chip. And finally, we have lots and lots of I/O. So if you really need to get that 20 gigahertz, or maybe a lot of different channels off the device, you have the capability to do that with the 24 SerDes lanes. So that's kind of a brief introduction to Apollo, the capabilities of it, and hopefully it gives you some understanding on these direct RF parts, how they're used, and how you need to think about them from a system level. They're not just a converter. You want to leverage the DSP and control them correctly in your system. Okay, so if you found this interesting, ADI is hiring. We have locations across the world. And if you're looking to learn more about Apollo or other parts, if you have more questions, please come by the booth. We'd be happy to talk with you about it. Thank you very much.
All right, we have time for one quick question if anybody has one. All right, I don't see any hands, so let's thank the speaker one more time. And next up, we're going into our lightning talks, and I actually don't have a list of those, so if you're the first lightning talk, please come up.
Maybe it's not me.
Hello, everyone. I'm Philip, and this is a talk about an SDR-based feedback system that we use to control spill in an accelerator. So this is an accelerator in a nutshell, bird's eye view. Lots of stuff there, but let's keep it simple. Basic principle, we inject a beam into our accelerator, we store it in the ring, and then we accelerate it, because that's what the thing is made for. And now we want to extract our particle beam, send it to experiments. And in order to do that, we need two very important devices. One is an RF exciter. That is a device where a radio frequent electromagnetic field acts on the beam and controls it. And then down there we have what we call septum, and that separates the circulating beam from the beam that we extract. So if we use an RF signal, send it to the exciter, and excite the beam, then we get some of it out, and this is what we call a spill. Now we also have particle detector there in the extraction beamline, a spill detector, so that we can measure how many particles we extract from the ring. And so in order for this whole system to work, there are basically three things that we need. We need to generate RF signals, that is kilohertz to megahertz range. We have that detector that produces pulses for each particle. We need to process and record these detector signals, that is pulses in a few nanoseconds. And then the third thing, we want to have a feedback system that controls the RF signals for the excitation based on the measured detector signals, so that we can maintain a constant extraction rate. And we chose here an SDR-based implementation, because not only it can do all this in a single portable system, but also it gives the flexibility that I need to study how different RF excitations influence the particle dynamics in the accelerator. So how does this look like? We produce the excitation signal with GNU Radio on a computer. And as a front end, we use the USRP X310 that generates our RF signals. They are amplified, sent to our beam exciter. The beam is excited, part of it is extracted. We have the spill detector there. That detector produces a pulse for each particle it detects, and we feed that signal back into our SDR. An RF knock plug here discriminates the pulses and counts them, so that gives us a particle rate, a spill rate. And then we close the loop by inserting here a feedback controller that compares the measured signal versus a target rate that we want to have. And in this case, it just adjusts the excitation level or the amplitude of our excitation signal. Now, in order for this to work, very important that the loop delay is kept as low as possible. So as you know, in the signal processing, there are lots of buffers involved. There's transmission delay between the radio and the host, and so on. And especially when the flow curve is started the first time, that can be quite significant. We also operate that thing in a triggered mode. So we're sending out bursts of signals for excitation once every couple of seconds, and then the machine cycle repeats. So a few measures that we did to reduce the system delay. We're using these breaks in between our excitation signals to flush all the buffers and reduce the delay. We're using things like real-time scheduling, PCI connection, etc. And overall, we achieved a delay, just considering the SDR system, of 1.3 milliseconds, which is already very good for our purpose. So how does that actually look like? This is a measurement recorded with this SDR. So you can see a typical spill here over an extraction period of 20 seconds. In the upper plot, this is the spill rate, so number of particles per second. And typically, without a feedback system, there's a huge drift. But we want to have that flat and a constant extraction rate. And if we switch on the SDR-based feedback, that is actually achieved. And this looks all flat and smooth. And that's what we want to have. You can find the flow graphs and the out-of-tree module for this application on our Git repository. And if you're interested, I'll be happy to talk to you about it and to learn from your expertise in the field. Thanks.
Questions?
Hi. What, in your experience, was the biggest contributor to lowering latency out of the things that you tried?
It was definitely this flushing of the buffers in between the bursts that we send out.
Thank you.
A huge difference, yeah.
All right, let's thank our speaker. And the next talk should be coming up. Yes.
All right, second time's a charm. So my name is Lauren Sandler. I'm Director of Applications Engineering for Epic Solutions. And today we're doing our lightning talk on a new system called the NV800. It is basically a multi-channel Vita 49 streaming SDR platform. Okay, push hard. There you go. All right, so a little history on Epic Solutions. Basically, we started in 2009. We actually started in the living room of one of our founders, and that's that first picture there. Over the years, we've done many different SDR, embedded SDR designs, as well as SDR platforms. A whole line of very low swap embeddable SDRs, and then moved on to multi-channel wider bandwidth SDRs, as well as a variety of both platform and hardened open standard sort of designs like VPX and such. We have a 20,000 square foot facility outside of Chicago, but we have a lot of our staff just distributed all over the place. So we have a lot of remote engineers and sales staff and such. The team is north of 65 people. I think it's like 68 or 69 now within Epic Solutions. And we've delivered since 2014 our first embeddable design. We've delivered over 20,000 of these SDRs to over 400 customers. And just recently, actually beginning of this year, we acquired another company. This added another, I think, 35 or so employees. And this company is called Xiphos Solutions. They're based in Montreal, and they are focused on LEO. So they do rad tolerant, both SBCs, compute platforms, as well as SDRs. NV800, what we want to talk about here briefly is basically a platform with 8 receive channels. The 8 receive channels can operate independently, or there is circuitry within the platform such that you can run the channels coherently, or any mix of coherent channels and independent channels. They have a 50 meg bandwidth per channel with basically a 16-bit converters on them, and they cover a 10 meg to 6 gig tuning range, with one channel optionally going up to 18 gig. All of that IQ data essentially gets streamed off the back of the box. So we have a 10 gig Ethernet SFP plus port there, so you can run it out fiber or coax. We also have another 1 gig for control, command and control, and another SFP port for timing. So we use White Rabbit timing on this. So then you can distribute multiple NV800s across a very large area, and you can essentially time them within a nanosecond of each other, which is a very useful feature. This is an example. We actually have one of these running at our booth. So if anyone's interested, please come by our booth. What we're doing here is we're running an NV800. We're taking one of those channels we're receiving. We tune it to 750 meg, which gives you a nice LTE signal. We receive that. We pump it out Vita 49 over to, in our demo, it's an Intel NUC. On that Intel NUC, we're running an application called Scepter from a company called 3DB Labs. And it displays a beautiful picture of that LTE signal along with a waterfall of it over time. We do also use open source applications a lot. And this is again another capture of that 750 meg signal on an application called InSpectrum. And then I think this is the last slide. This is showing you how we do this White Rabbit timing. So again, we have IP built into the platform, and then we have a separate port to bring in that timing. The timing comes from a White Rabbit distribution unit, which is the unit there labeled WRZ16. In this case, we're running a 1 meter fiber to one unit, a 10 meter fiber to the other unit. We're bringing back a PPS out of each platform, and we're showing you the display there, and you can see it's within, if you want to take a look there, it's within a nanosecond of each other. And we've done these trials over different distances, and we've now shipped platforms to customers that are using that White Rabbit capability. And again, come see us at our booth. We're glad to answer any questions and show you our other products as well. That's it.
Any quick questions?
Have you ever been able to synchronize them wirelessly by any chance?
So we have not actually had a discussion about that just a week or two ago, and it is something that is interesting. The initial customer didn't have a desire to do that. Actually, quite the opposite. They're basically using it more as essentially in-place monitoring, where they're looking for spectrum, right? That shouldn't necessarily be in an area, and so they're trying to avoid that. But there are certainly applications for that, and we are interested in it. So potentially in the future, but not right now.
All right, let's thank our speaker one more time.
Thank you.
I think we have one more talk before lunch.
All right, let's see if I can get my display going here. There we go. All right, so I just ran over from the CTF room and wanted to give an update on the scoreboard. We're about 23 hours into the competition, and it'll continue to run until Friday at 4 p.m. You can see people have been working all hours of the day and night, and our top 10 teams right now, in first place we have Andro Computational Solutions with 1,320 points. Aerospace Team Platypus, 1054. There's no I in Idiot, 736. Flame Wires, 571. Real D, 496. 1 point behind is Caliola Engineering LLC with 495. 509 with 476 points. Not the FCC with 421 points. Fringe Reception, 1 point behind at 420. And Kilo Mega Psychos with 385. There's still plenty of time to join in on the action, so if you want to try out some challenges and get yourself onto the scoreboard, go to ctf.gnuradio.org, and I hope to see you on the scoreboard. You can also join us in the room just outside and to the right. It's room 210. So see you in the CTF.
Great. Thank you, Clayton. So we are breaking for lunch now. It's the same 1 hour break that we had yesterday. Just a quick logistical point. So again, there's plenty of food. There was a little bit of a line yesterday, so if you kind of want to stage yourselves going out, you won't be standing in the line quite so much. The other piece is if you are vegan or gluten-free, we have set aside the food today to make sure that you do get a plate. So just ask any of the serving staff there, any of the catering staff, and they'll be able to help you out. And again, if there's any concerns about any of the food, do let us know. I believe that was all the points I was supposed to mention, so thank you very much, and we'll see you in an hour.
seats as we're about to start again. Welcome back to the afternoon session, everyone. Our first speaker will be about the Allen Telescope Array, so I'm very interested to hear that. It's Luigi Cruz, who's going to tell us about the accelerator system that they've built. Take it away, please.
Oh, okay. Okay, awesome. Hello, everyone. Thanks for coming. Let me start with apology. Sorry for the elevated number of Blade Runner references throughout this presentation. So today I'm going to talk about Blade, our Allen Telescope Array GPU accelerated beamformer that we are currently using in production at the Allen Telescope Array. So let's start by having a very quick recap from what is the Allen Telescope Array. So it was originally built from 2002 to 2007, and it was designed with astronomy purposes and also SETI, that is also astronomy, but more fine-tuned for finding search for extraterrestrial intelligence throughout the galaxy or galaxies. It's named after Microsoft co-founder Paul Allen that contributed in the beginning of the project. And recently it was refurbished for better system and reliabilities, thanks from the donations of lots of private donors, in special Frank Ling Antonio, that developed the new feeds that we are currently using. So here you can see the telescope in its whole extent. Here we have 42 antennas randomly distributed with a 350 diameter radius. Here, that house over there with the green roof is the signal processing center of the Allen Telescope Array. That's where all the signals goes with fiber, RF over fiber, and the signals are digitized and processed with our in-house data center that I will talk more about. Zooming in to the antenna level of the Allen Telescope Array, we have offset Gregorian dishes that are funny shaped dishes. Each one has 20 feet in diameter, or 6.2 if you're not Freedom Unit, and produce 1.5 gigahertz of bandwidth for each polarization. And we currently have true polarizations totaling 3 gigahertz, around 3 gigahertz per antenna. And that results, if you are sampling in 8 beats per sample, a data rate of close to 1 terabit per second for the whole 20 antennas that are currently operational. And one good thing about the Allen Telescope Array that we have a very large ultra wideband reception area from 900 megahertz to 12 gigahertz. So that's a very wide band and very useful for multiple purposes. Now, where all this data is processed, so we have currently 8 dual socket EPIC servers. Each one has 200 gigabits Mellanox fiber links, and also RTX 3090 or A6000 NVIDIA GPUs running CUDA. And also a relatively small NVMe cache, also working with PCIe X16. So we can buffer some data. So we are at a radio conference. I believe most of you know how Beamformer works, but a quick introduction. If you have lots of elements distributed in an area and you have a point source in the sky, the signal will arrive at each antenna at different pointing times. So you need to account for that if you are summing up all the signals for all the antennas. And that's what Beamformer, our beamforming is doing. It's accounting for this difference and also trying to steer away from RFI and also other unwanted signals that can leak through our antenna. So that's where Blade runs. So let's talk about Blade. So Blade is a short for Breakthrough Listen Accelerated DSP Engine. Yeah, I tried there. And it's responsible for most of the digital signal processing of the ATA for the beamformer. And it's currently being used to process the data from the 20 antennas. And each antenna represents 3 gigahertz, as I said before, with 8-bit samples. And that equates to around 960 gigabits per second. Divided by 16 instances, we have 60 gigabits per second per instance to be processed. And that needs to be done in real time. So we don't store the data to be processed after the fact from raw data. We need to do this in real time, otherwise the data pool would be fairly large for some while. It's currently implemented 8 processing modules, ranging from beamformer channelization, that is basically a very large FFT, and I will talk more about later. And we followed some rules while designing Blade. That is, it needs to be performant while hackable, because you don't need you don't want a monolithic system that is very specialized on your target, but you also can't alter that without breaking everything, and no one knows other than the original person who wrote the thing how to modify that. So it needs to be modular and hackable at the same time. And also not to be afraid to use new technologies like C++20 and just-in-time compilation for GPU kernels. These are just examples, but if you are over traditional on the technologies you are choosing to build your application, you will find hardship where the new facilities can improve your quality of life. And also the low number of dependencies. You don't want your software to become unreliable in the future because some maintainer stopped maintaining your piece of software. Yeah. So this is a pipeline diagram, very simplified pipeline diagram. So the antennas communicate with the analog clusters that is composed of RF SOC boards, that is Xilinx FPGA, with internal ADC that gets the signal from each antenna and digitizes that with the ADC and sends to all our clusters using 100 gig networking. Once it's in the cluster, we use HBGuppy. There's a legacy piece of software that will take the raw UDP buffers from the RF SOC boards and upload them to the GPU. When the data is on the GPU, Blade will assume and do most of the DSP available for us there, and if necessary, return a pointer, the process data to HBGuppy for later processing. The overall architecture of Blade is very simple. We have 3 main divisions. The first one is a module where all the GPU kernels are. That's where the DSP happens. And once you are trying to deploy this, you need a bunch of modules. For example, your data comes into a complex integer 8 from the antennas, and then you need to convert them to float 32 or float 16, so you can use ready-to-go FFT libraries like QFFT to do channelization and stuff. So you need a cast modules. So you have a cast module, and then you need the beamformer module, so you can aggregate the antennas and reduce the data rate. You do this. We do this currently in float 32. The idea is to minimize that to float 16, so we get 2 times less memory and 2 times, ideally, less compute. So a factor of 4x improvement from float 32 to 16 that we are trying to implement in the future. And last, we have the Blade Runner that will take the pipeline and run it. So you need to have some assertions when you're working with a discrete graphics card, because 90% of our problems are data management and where the data is and where it needs to be. So you need to come up with clever ways to how to transfer data around, and Blade Runner was one of these ways that we developed. So once one pipeline is processing the data with the GPU hardware, the other pipeline is transferring the data to the GPU using the fairly slow speed PCIe 4 x16. That's our main bottleneck, and this segregated pipe runner with one processing, one transferring makes us around twice as more efficient, and our GPU utilization remains high throughout the execution of the program. Here is a Blade module. So you can see it's a very simple module interface. You have the input struct and output struct. These input and output structs will define your pointers for your raw data. And also you have the generic config struct. So Blade was originally built to run on built with running it on multiple telescopes. So you don't want to reconfigure your hardware, your software every time you need to change your telescope. So one of the design capabilities of Blade is to have a generic config struct for a channelization module, so it doesn't vary between telescopes. So you can use the same code on multiple telescopes. We're trying to use Blade on the VLA right now, other than the ATA for our SETI resources there. So this is an example of the config struct. It's just C++ with some flags there, and also numbers. We have the phaser. The phaser configuration module is very has like 20 parameters. It's very large because you need to specify where each antenna is and other configurations for the phaser. But this is one example of this. And then we have the input-output vectors. So we have a wrapper over a pointer, a GPU pointer, and a CPU pointer to facilitate our lives and make it less likely that we will crash the thing. So all the memory allocation and initialization is done when we start a program. After the Blade will process the first sample, no allocations, dynamic allocations are made. So we know that we won't have memory leaks or be inefficient by allocating memory that we already know that we need. So we just allocate it ahead of time and just run it, because remember, Blade can run with several days in each time, and it needs to be predictable on memory usage and also performance. So this is, for example, array tensor, and it's a templated, so you can send a device CUDA or device CPU and allocate CUDA or CPU memory using that. The newer version also has shapes, so you can modify the multi-dimensionality of the array using this API. Another good thing about Blade is that we do just-in-time compilation, because our kernels are very specialized. And we use templates and static parameters wherever we can to take the compute from runtime to compile time. So for example, if we are running with a sample of 10 antennas, we need to change the parameters, the number of antennas of the beamformer module. And since the number won't change during the execution of the program, we can do this in compile time and have a kernel compiled with just 10 antennas and optimize the register usage and other resources to run with the best performance possible. And we can't do this without just in time because we would have to either compile all the possible combinations of parameters ahead of time. That would result in a very large binary, or we just need to recompile whole blade again and again and again every time we change the parameters, which was not acceptable. So we used this just-in-time technology from NVIDIA, the NVIDIA runtime compiler. It's basically like NVCC, but it runs in runtime, gives you PTX. You can run that PTX whatever you want. Going in more details about beamformer, this is an example diagram of our current beamformer. So you have basically the dot product here that will do all the computations, and also the phaser module that will plug into the dot product module that will give all the spicy array to multiply with your data and give you the beamform data that you are seeking. The phaser will take some time parameters like the Julian time and sidereal time where the position of the object is, and we'll spit out the right phasers for the beamformer to be multiplied with. So here, another good one in Blade is the channelizer. So before Blade, we did this in a post-processing step. So we would do the beamformer and store all the data produced by beamformer, and then convert the data from time domain, pseudo time domain, to frequency domain in a post-process. And right now we implement that in Blade, so we can't do this in real time. What we do here is basically taking all the pre-channelized data from the telescope that is around. Each block has 192 frequency channels and 8,000 time samples. So the end result needs to be all frequency domains, so 192 times 8,000. But then you need to do this over 300 seconds of data. You need to do this 64 times, so it's 64 times 192 times 8,000. So you are gonna every 96 megahertz. So expanding this with 3 gigahertz, 96 that calculations times 96 divided 3 gigahertz divided by 96. So you have a very large FFT. So 3 million beans FFT every second need to be calculated for this to be run in real time. So we just need to accumulate, or people need, accumulate. People sometimes think about integrations. Not integrations, concatenation. So we concatenate 64 blocks of 8,000 samples and do a very, very large FFT in the end. And we do this in every GPU, and every GPU has 96 megahertz. So in the end, we have a 3 million being FFT. So that's a very large number, and we use lots of RAM, VRAM for this. And we also have other modules like GUPI file reader and the polarizer that will synthesize right-hand and left-hand circular polarizations from our horizontal and vertical polarizations, bending calibration, and also correlator that we will hopefully have soon, and also a detector that will do the Stokes eye calculations from the data. and also a phaser that I just talked about. So this is an example of a pipeline. So you have a cast module, channelizer, beamformer, circular polarization, a detector, and a cast. This is one of the modes run by the Allen Telescope Array for generic science. And you can see that you can either take the input HP-GUPPy or another pipeline. So you can change pipelines together if you want. Next versions of the Blade will have a single pipeline. So modules that will change the ratio of input and output ratio can be stuck together. So this will be greatly simplified in the future. So you can have a concatenation module in line with another channelizer module, for example. It doesn't having to create a new pipeline. So that will be interesting, maybe next year here. And that's an example of a pipeline. Is just basically a connect, and you send a module and it will connect. So here it's the main takeaways. It's fundamental to design the instruments to accommodate incremental changes without impacting the sky time. Otherwise, you're gonna end up taking the equipment down just to change the software, and that's not something that you want. So something with modularity in mind, we recommend doing that way. And also, real-time processing will increase your efficiency, because if you think about this, if you are saving the data you are producing, you need to write that to your NVMe storage, and that write will pass through PCIe, and then you have the bottleneck of the NVMe itself. And then when you need to read that again, you need to do the opposite. So you're trying to read that PCIe again. So if you quantize that in energy used by just storing the data to process again, you're gonna see that first you are murdering your NVMe, second you are spending more energy and time to process the same amount of energy. So a real-time process can give you more abilities. For example, if you need to observe something for a long amount of time, and you can't because you're limited by the storage size, you can use the beamformer with the integrator that will time integrate your observation and run that in real time for as long as you want. And your gains will be the factor of the integration. So you can run by several more time than if you're running just you're saving the data. So this is what I have for you, and if you have questions, you can contact me or ask right now. We have lots of time for questions. And also, Blade is an open source project, so you can go into this repository and look with all the code we have. And if you want, you can do PRs. We really like community helping you. You can also use Blade if you want. Just contact me or use it by yourself. And thank you.
Thank you very much. That was a very interesting talk. Are there any questions for Luigi? There's a question over there. Do we have more microphones, or do you need to come your way? If you wait, then
I don't know if this is out of your expertise, but the antennas look like they were randomly placed. Are they?
Yeah, they are randomly distributed within like 300 meters of each other, and that's there's a good explanation why. If you have a very long baseline between antennas, you have very large precision like the pixels of your phone. The pixels are smaller, you have more resolution, spatial resolution. But then you are very specific to one place, so you lose your focus, your lens will have a more narrow field of view. So it's a balanced approach. So we do this because we are doing SETI and also others. If you like, I think Weil can answer your question offline better, but the gist of it is this.
Yeah, this is super cool. I had a quick question. How do you define the DAG of processing? Is that done in code, or do you have a configuration file that you then sort of jit out a graph? I'm just really curious how you organize these like components.
Yeah, so currently we do this in C++ files. Each module is instantiated in line. So the moment you connect the module into the pipeline, it will be instanced. And taking into account the inputs of the module, it will create the outputs with the same shape as in relation with the input. So currently it's C++, but I have another project called CyberEther that does that in a YOM file fashion, and they are very similar. Currently it's very static. We have bundles to bundle together multiple modules. So when we have modes, we call modes. It was a temporary name, but it stick around. It's called Mode B. That is everything that you need to do Beamformer, and we have a collection of modules pre-assembled for the user, so you don't need to wire together every time you do Beamformer. That is a very common operation.
Are there any more questions? Oh, next please, yes.
I'm at your GitHub page, and I don't see the license that you're distributed under. It's screaming at me. Could you just touch on that?
Is TBD, but will be open source very, probably around some BSD MIT stuff. Thank you. Yeah. This was a trick question.
Is our next speaker already in the room, Bailey? Okay, that's good. Any more questions? I saw one over there. Probably lost one.
Hi. You mentioned you use quite a bit of VRAM. I was curious if you had a minimum recommended amount for your GPU to use this.
Yeah. We have a very homogeneous system currently with RTX 3090s, and as you know, that comes with 24 gigabytes. And we are trying to make Blade reduce the number of gigabytes used by using in-place memory, so that will take like 2x less. But currently use 24. We are quite happy with 24 gigabytes. In the future, we will try to switch to a heterogeneous system where we have multiple generations of GPU in production at the same time. And for that, we will need to account for differences in VRAM sizes for 16 and to allow 48, or if NVIDIA releases something with good cost benefit, better, more graphics. In essence, with more VRAM, you can form more beams in the own sky. So it depends on your usage, but for us, 24 currently is enough.
Okay, thank you very much. Let's thank him again. Very good talk. Can I invite Bailey, come over, please? So our next talk is also going to be about Beamformer by Bailey Campbell. It's about beamforming for volumetric arrays. And you actually have a minute extra. Go ahead.
Okay, yeah, so my name is Bailey Campbell. I'm up at Penn State, and I'm going to be talking about this monstrosity. The previous speaker mentioned, yes, we are at a radio conference, and hopefully a lot of people know about beamforming, but if you bear with me, for the lowly undergrad that is watching this on YouTube, maybe some other time in the future, I am going to give a brief bit of background into antenna arrays and beamforming. So what is an antenna array? Well, Well, it's two or more antennas doing something together, right? They can be arranged linearly in a plane, in a circle, on a sphere, conformal to whatever. But primarily you see a lot of linear, like one-dimensional, two-dimensional configurations of arrays. We're interested in looking at volumetric distributions, particularly like randomly distributed elements in a volume. I'm pushing hard. I'm trying. Did I go too far? Okay, so how do you analyze an antenna array? Well, you just sum all of the electrical fields together, right? The electric fields together. Now, if you do this, you can notice that you can make some assumptions, like if all of your elements are the same type of element, you can pull that out of your summation, and then you do this thing called pattern multiplication, which is where you multiply the element pattern times the array factor, which is that bit on the right side of that equation. And the array factor is purely a function of the geometry of your array. And then if you look in there, that K and the R are just like properties of the wave and the position of those elements. Now, if you introduce a complex weight into this equation, you can do things like beam steering. You can direct your beam into any kind of a direction. And this weight is just a complex number that you apply to each individual element, and you can get it to do cool things like beam steering. Now, if we extend into 3 dimensions, this is kind of the application that we're looking at, right? If we want to develop a signal model, you can talk about the output of your array, y in this equation, is equal to the weight of each element, that complex number, times the output of each element, okay? And that output of each element is some signal of interest that you're looking at, times the steering vector, plus the noise at each element, and then plus the response at each element from a bunch of interferers. Now, these steering vectors, again, are just properties of the geometry of your array. And so it's some e to the minus jkr term, and that's the phase term based on the position. And I think that's it. Okay, so with this kind of established, you can do fancy math, and you can do beam forming. You can basically, let's say we have some desired signal, and that is S of t, and then you look at the actual output of your array. That is this weight, some weight times your response from your elements, and then you get the error, and then you can find the mean squared error. This is a term that I'm sure a lot of us are familiar with, and that's just the expectation value of the error squared. And then you can take the gradient of this, and then going back to early calculus, you can optimize this, set it equal to 0, solve for some terms, and then you end up with this solution where you can find your optimal weights is equal to your autocorrelation matrix times some other stuff. And you can, if you know information about your signal of interest, about your interferers, like the direction of your signal, you can do this optimization, calculate your weights, and boom, there you go. You've steered a beam in a direction that you want to. But what about for 3 dimensions? What if you have a 3-dimensional distribution of elements? Well, there's nothing in that set of equations that really makes a difference. It still works. The math still maths. And so you can, given some distribution of elements, generate your steering vectors, this v of ks term, and then you can just plug it in and you can do beam steering. And so this is an example that we did with 32 randomly distributed elements. This contour plot might look a little weird. You're unwrapping spherical coordinates onto a plane. But you can see that if we have some signal of interest at the green dot, we can steer towards that and then ignore these other 2 interference sources. This was cool because we're doing it with a 3-dimensional randomly distributed bunch of elements. Beyond this minimum mean squared error, there are endless different beamforming algorithms, least mean squares, recursive least squares, particle swarm, on and on and on, all these kinds of optimization methods. But this is just an example of doing, I think, least squares, and that is an iterative algorithm, whereas MSE is these are the solution, right? And so now we get to this thing. We call it Medusa for obvious reasons. It looks ridiculous. But this is kind of my PhD project, right? We are trying to develop this system where we can kind of simulate something like swarming UAVs. And then how can we develop different kinds of beamforming algorithms with these like randomly distributed elements to do interesting things, beamform, do adaptive nulling, things like this. And so how is it constructed? It's 2 layers of this thing you see on the left. We've got 2 of these analog devices, large SDRs, and then kind of that other diagonal, we've got these like modules to do. It's on the next slide. First, I'm going to talk about this patch antenna. So this patch antenna is just for demonstration. You can put whatever antenna that you want on the end of it, but these are stacked patch, dual band patch antennas. One frequency is RHCP, the other frequency is LHCP. And so the only reason that we did that is to see what kind of interesting things that we can do with these different polarizations and these different frequencies. But on the front of it, there's this QR code looking thing. That's what's called an Aruco tag, and that is able to be utilized in OpenCV, which is a computer vision library. They are designed to be kind of asymmetric, and so using computer vision, each of those tags has, like, each of those small squares within the big square is kind of a bit, and then using those bits, you can determine the ID of that tag, as well as, because they're asymmetric, the pose of that element. First, I'm going to talk about this analog module. It's very simple. It's an LNA going into a phase shifter. There's a typo on the slide. It says it's a 7-bit phase shifter. The attenuator is 7-bit. I don't remember the bit resolution of that phase shifter, but the antenna into the LNA into a phase shifter into the attenuator. And those are all controlled by a Teensy. We've got 4 of these modules, and then we put just a Teensy microcontroller just to do, we can send commands to that Teensy, and then it will set weights after we've done some calibration and then generated a lookup table for all of the kinds of like weights that we want to be able to generate, these phases and these attenuations. And then altogether, we've got, 4 of those modules. So in total, 32 antennas. And then we're also doing clock distribution so that we can have a synchronized clock across those 4 SDRs. Okay, so more about the Aruco. This is kind of an example of how it works. First, we have this step where we do detect markers, and it goes through this image. It finds candidate markers, and then it, generates an array of IDs that were detected. It generates the pixel locations of the corners of those markers. And then you can take those corner positions, and then knowing some characteristics about your camera, you can plug it into the solve PNP function, and it will generate a rotation matrix and a translation matrix. And you can see on the bottom right, we have an example. We're actually able to detect the pose of those markers. These are not the antennas. This is just some thing that I had in my house, some printouts that I put on cardboard. So a lot of fun things that I did was trying to put all of this into GNU Radio in an interesting way. I'm going to say this in a gentle way. There's a lot of room for potential optimization. That's how I'll say that. So basically, things that I tried to do, OpenCV has some functionality to, get frames from a webcam and then do this detection and all of this stuff. And so I just tried to take those functions from OpenCV and then put them into GNU Radio. And so here you can see a very simple flow graph to do, open up a webcam, do this corner detection, and then it shows the image of those corners on one frame, and then it does the pose estimation, and then you can see that on the right side. And it's actually able to, in GNU Radio, at a pretty good frame rate, detect the poses of these markers. So back to this background that I was talking about, where we have arrays. The antenna output, there's a typo in that formula, bonus points to who can see where the typo is in that. You've got the outputs of each of your elements, then you've got the output of your arrays, the sum of that times some weight, and then steering vectors. Why are we using OpenCV? Well, using OpenCV, doing this computer vision, we get this pose information, and we can get the position information, and now we can generate those steering vectors to do this kind of like minimum mean squared error algorithm, as well as some other algorithms that we would like to do in the future. But you can see these are all of the markers on Medusa detected and then displayed in a three-dimensional plot. Both of those are actually in GNU Radio using some of the blocks that I made, but I thought that was very interesting. I think PyQt graph is a dependency of GNU Radio, but it's very underutilized, and so I think there's a lot of potential for doing more stuff with PyQt graph, like 3D plots. This, I don't know how difficult this is to see, but just to give some brief overview from left to right. I've gone through several iterations of doing this like corner detection and then the best ways to kind of get this data back and forth between blocks, what is fastest. Struggling a little bit. I'm sure I've got many people that can help me make these blocks more optimized. But doing this corner detection with OpenCV, displaying it in this like video widget, taking that, passing it to another block to determine the steering vectors, and then passing that into some beamforming block. And what I would like this block to be able to do is just have a drop down and say, well, I want to do MMSE, I want to do LMS, or LSE. I want to do different kinds of beamforming algorithms. Right now it's just MMSE, but hopefully down the line we can do some interesting things. On the top right, just generating just very like random QPSK samples, and then passing that into kind of some like simulation block that emulates like propagation through space, and then hitting these elements. But you can see using OpenCV and detecting these Aruco markers on the left side, passing that into the beamformer, and then having that determine the weights, sending that into the simulation block, and then plotting the array factor from that. I was able to generate this. This is a tiny little movie. It's like a minute long. I don't know if we can play that. Yeah. And so you can see on the right side is the contour map, contour plot of the array factor. And so you can see as I move this signal of interest, you can see the weights adapting to kind of point towards that signal of interest. It's not very fast. Like I said, there's a lot of room for optimization, but I thought it was interesting seeing before it has a chance to update the weights, you can see the impact on the constellation, and you can see how it kind of like hits a null and all these samples go away, and then once it's able to recalculate it, it corrects itself. Yeah, this is just showing some steering of the SOI and then the interference, seeing how it adapts to that, which I thought was pretty neat. Some other things that I would like to do that I have done a little bit of work on is previously, I know GRIO was brought into upstream a little bit ago. There are blocks for the FM Comms 2, the Pluto, I think that's about it. But because we're using these ADRV 9009s, I'd like to have a block for those to do as a source and a sink in GNU Radio. And so I did fork GNU Radio. I would like to do a pull request soon. I'm not just going to leave it hanging. But I was able to just like get samples in and out of the that radio. And so this is just a demonstration of doing, like getting samples in and out of this radio. Other work that I would like to do, I need to validate and test those little analog modules to actually generate those lookup tables that I was talking about. I would like to do a full over-the-air test. This test that I showed was just showing the array factor based on the positions of those elements. There wasn't actually any like samples going back and forth, and that's kind of the next step that I would like to do, is actually generate samples, transmit them over the air, do beamforming, see if I can get some kind of like bit error rate generated, do testing like that. Also, I need to do the clock synchronization between those radios. That's another thing that I'm probably going to go talk to Travis about here in a little bit. And then do some additional beamforming algorithms. Not listed on here, but I think there's also a lot of other very cool things that we can do. Now that we've kind of moved into this third dimension, how can we utilize the different circular polarizations to do cool things? How can we choose, based on knowledge of the pose of these elements, if we should turn elements off or on to do interesting things? There's another thing that I wanted to mention that I can't think of. I'm sure folks will have questions. If you want to know more about this, you can see me on GitHub there. And then this project is not fully up to date up there because the code's kind of embarrassing, and I would like to clean it up a little bit. And so it will be at GitHub at this location. And I apologize for taking a full 30-minute block when I finished so quickly. But if folks would like to ask a lot of questions, please feel free. I know we have a lot of time for questions.
Thank you for a very, very interesting talk. I was very impressed with the ongoing animations of all your beam patterns while you were talking. That was, yeah, next level presentation, I would say. Are there any questions? There's one over there. Yeah, you go first, please.
Yeah, this was a super cool talk. Can you talk more about the drone swarming inspiration? Just very interested in drones, and
yeah,
I'm curious how that came about.
So this is kind of, you saw it's Medusa 2.0. The first iteration was using an Xbox Kinect camera, and that like concept of having swarming UAVs with antennas on them, can we make them do interesting things? And that kind of developed into using this as like a test bed. If we have swarming UAVs, they're just in some volumetric distribution. How can we like investigate that and do cool things? Well, this is what we came up with. And the first iteration was using a Kinect camera with like red, blue, green, and white LEDs on the corners. And that was okay, but then computer vision progressed a lot, and so we're able to do this and get pose information much easier. And so we did this second iteration. And then we also have somebody else that, not on this project, but on another project, is doing something similar, but using like true time delay units instead of these like phase shifters and attenuators to get like a wider band capability out of it. Is there a follow-up? Yeah.
Is the idea that you're able to focus on like one drone in the swarm? I'm just like, so if you have the swarm of drones and you have these antennas, are you trying to just like isolate one drone in the swarm? Or I guess I'm very curious what you mean by like investigate the swarm.
So more like, say we have a swarm of antennas and we, have someone that we want to communicate with over there. Well, how can we make each of these individual drones operate collaboratively to direct energy over here, to null energy over here, things like that. And then I eventually would like to investigate applications to space-based communications. If we have just like antennas floating around in space, can we like make them do cool things?
I also really enjoyed the talk, thanks. And I'm sure the ADI guys are happy to help you upstream the IIO improvements. I have a question on the location of the antennas. So you said they were randomly distributed, so did you just like twiddle them around? Is there an optimal distribution, or is it actually sensible to just randomly distribute them and then once you know where they are, you do the math from there? Or is there also a value in putting them into a certain location to achieve, I don't know, certain beam patterns or anything like that?
I would think that you can do like more mathematically rigorous like beamforming based on like pre-existing knowledge. So like I think this is the thing that I wanted to expand on further work. So we have like the pose information of each of these elements. We know they're randomly distributed. When we look at I talked about pattern multiplication. We've got the element pattern and the array factor. The only reason that we were able to pull out that element pattern is because they're all the same. But if we're in this like three-dimensional case, they're all pointing different directions, so that kind of like breaks that like symmetry. And I think additionally doing like randomly distributed kind of breaks the symmetry, and so you can't do like these simplifications that you would be able to do with a more like regular distribution of elements. And so I think just our use case, we're really just interested in if we have some random distribution, and also looking at that like varying in time. So if we perturb the location of each of those elements randomly, maybe doing some kind of like random walk, how does that affect? Can we like continue to keep up doing beamforming as each of these is just like randomly perturbed?
Have you looked at stochastic geometry for that? Like,
I think that's in the pipeline of things to investigate.
All right.
Thank you. What about calibration, phase and delay calibration across your antennas? Is that something you adaptively do, or maybe you can say a few words about that?
Just calibration of. So right now, the way that we are planning to do the generate these weights, right? We've got each of these like modules. We're trying to put them in situ and then do measurements and generate a lookup table for each of the like discrete cases that we want. And so each of those cables that are running from those analog modules to the antenna, those are all phase matched cables. And so if we measure kind of from the end of one of those cables all the way through this whole chain, and then iterate through all of the different states hooked up to a VNA, and then using that generate just a table of, well, if I want to set my attenuation to this, and I want to set my phase to this, what's the nearest approximation I can do to that? Well, this is in my lookup table, this is the closest thing, so I'm just going to set it to this.
Any more questions?
Hello.
Where? Yeah, go ahead.
Thank you for the interesting talk. I wanted to ask about the synchronization between two different devices. Like how do you do it? And in case of, let's say, drones, how do you like synchronize while they are not connected by wire, right?
Good question. I'm not sure. I think my advisor might have more ideas about doing this with like drones, them not being connected. With these SDRs, they actually have a device that does like clock distribution, and so using that, we can do clock synchronization. In one of my slides, I mentioned it's called the HMC 7044, which is another like ADI part, and it just does this like clock distribution. I think it's the GESD 2048 framework does this like clock synchronization. So we're going to use that to do this thing.
I would like to ask a question myself, if I can. So you have a volumetric array of receptors, swarming or whatever, trying to focus on a target, and then I'm assuming the target is going to be relatively nearby, and you end up with curvature of your incoming signal. So you're no longer just beamforming, but you're trying to sort of focus the whole thing. And to what extent does the algorithm handle the fact that the beam is no longer that the incoming signal is no longer a plane wave?
I think our assumption is that it's a plane wave, and we haven't really done much to investigate the case where it's not. We just assume that we're in the far field. Now, what kind of distribution you have that would like violate that? I don't think we've done a lot of investigation into that. I think that's like an interesting problem, especially given this calibration question. Like, how do we, address this? I don't know.
Thank you. Any more questions? Oh yeah, over there.
I left too much time for questions.
So just for general information, Thursday, tomorrow, a student from our group is going to be talking about time synchronization of drones. So there's that.
And I was wondering as well, have you looked at cases where not using all of the antennas may actually provide a better result than using all of them? I don't know if that is ever true. I'm curious.
That is one of the things that we would like to look at. So talking about different like distributions? If we make it more regular, can we do interesting things with that? Knowing the positions of all of these and the poses, if the like pose and position are in such a way that they might destructively interfere, can we do kind of like thinning adaptively to improve performance is part of the rest of this project.
It's very, very cool. And yeah, with the GNU Radio hat on, yes, please do let us know about the fork and definitely try and get that in.
I was going to talk to you about it. So many things.
Excellent. I would love to chat.
Yeah. I think we have 5 minutes, but if folks, you know. I know, I signed up for 30 minutes and I gave a 15-minute talk.
It's not really a question, but we're having such a good conversation right now that, so like we've already had several questions about wireless synchronization. Are you going to talk about wireless synchronization of sure, but so like, okay, in absence of like a 10 megahertz and PPS, etc. Is okay, fair enough. Yeah, cool. That's good. I'm just want to make sure that we get all those people connected. There was a question about that during the Epic Solutions lightning talk earlier. So looks like that's something. Yeah, multiple people interested.
Output was a very interesting problem. And then whether or not to make that, like the information generated from the Aruco like detection, to add that as a tag to those frames or to make it a message was a very difficult problem. And I will say translating back and forth from PMTs was a lot. I think motivated me kind of making things into like mono block. And I know there's a talk, I think, later about PMTs, so I'd be very interested to hear about the work being done around there.
Well, I think it's time to let you off the hook. I would like a big hand for Bailey. And my next question is going to be, is Dr. Michael Rahim in the room? So you can take all your time to set up. Do we need to wait for the clock to take over, or can we just go on? I don't know if this if this needs to be timestamped exactly. No? Okay, then you get 2 minutes extra. Take it away.
Oh boy, extra time. Let's see. I'll run long so I don't get any questions at the end. Okay, perfect. It's already up, and then push hard to go to next slide. Perfect. All right, great. Hi, everybody. My name is Michael Ram. I'm an assistant professor at University of Massachusetts, Boston. This work is in collaboration with colleagues at University of Oklahoma and the Advanced Radar Research Center there. Talk title is Implementation of a Software-Defined Antenna and Radio Test System for Congested Spectral Environments. But really, the focus is on that test system. So developing a multi-node kind of test configuration in this collaboration. Groups bringing our background in GNU Radio and some of the SDR concepts. Oklahoma's got a lot of this background in these reconfigurable antennas, and the idea is to bring it all together and just come up with some stuff that we can do some interesting testing in the future. So just a little bit about the colleagues and people working on this project. Rosalind Elliott, colleagues at Oklahoma. These are my students here and myself from UCAN Lab at UMass Boston. Big picture is that they're doing a lot of the cool antenna stuff, very different scales and size of antennas, reconfigurable antennas, dynamic antennas, et cetera. Our background is non-conventional SDR stuff. Probably familiar, or you might have seen Christopher's talk yesterday on our work with optical wireless communications. And with that in mind, that kind of highlights the fact that my background is optical wireless communications, so I'm probably the last person you want talking about an antenna because my antenna is a LED transmitter and a photosensor receiver. So just kind of merging these two things together. But the big idea is kind of benefits of GNU Radio and some of these conferences and collaborations kind of bringing concepts together. So, quick outline, motivations and background concepts, a little bit about what they're doing in Oklahoma, the reconfigurable antennas, some of the hardware that they've built up and are developing, and the software that they use to control that, some of our work with GNU Radio and the tools we're using within the GNU Radio framework, primarily XML-RPC and ZMQ, and GRCon, which I'll point out is not an out-of-tree library, it's just our open source GitHub repository with some of the scripts and code tied to this project. And we'll talk a little bit about the integration and how we're bringing these two things together to build up a test system. So background motivation, common here, RF spectrum environments are congested. We have a lot of stuff, particularly sub-6 gigahertz, what's going on there. Important concept to consider is noise interference mitigation in the analog domain so we don't run into aliasing issues and stuff that have a harder time getting rid of after sampling. And then the benefits of frequency reconfigurable antennas, which is the concept we're talking about here. Tunable antennas, basically applying a unique solution to this problem, giving us this flexibility, allows for change in operating frequency on the fly, so some of that dynamic control. Tunability in this concept then gives us this larger operating bandwidth while also providing some narrowband filtering, so moving the center point around the range of interest and giving us this frequency of agility to intentionally avoid some interference or other characteristics that come up. For my side, it's more of a SDR software motivations. The point and the interest in this collaboration led to this idea that, okay, tunable antennas are there, you got some extra control over there. What eventually or essentially it does is it gives us this extra dimension of software control to impact our front-end hardware. And then kind of following some of the analog and to digital process over the years. So analog signal processing, full RF, analog RF side, adding DSP and kind of the benefits of what led us to software-defined radio, configuration of front-end hardware, your mixer, your amplifiers, and all these kind of characteristics in here. But all of these things have that static antenna at the front. That's kind of the limiting factor at the end. What this goal of this project is working on is adding that reconfiguration to the antenna piece, ultimately linked to software control throughout the entire framework of the software-defined radio. Right? And again, why are reconfigurable antennas important? Why do we actually care about this part? Well, that antenna is ultimately the first point of contact between the system or the signal out there and the system that we're building and coming up with. So the concerns and the characteristics of what happens there ultimately propagates through our system. I also point out this image because my colleagues working on antennas primarily look at the system this way. You have your antenna, you have your RF front end, and then there's the rest of the system. So rest of the system actually is where I'm kind of our focus is and kind of building up this stuff here. So antenna research often focuses on those analog characteristics and isolation, and then passes us off and says, this is great, go build up the rest of the system. Our intention here is that integrating the tools and the stuff that they're developing in university research in basically lab settings with the antennas is to then integrate SDR software characteristics and capabilities that we're all familiar with here with these reconfigurable antennas to do improved testing, broader scale testing on the higher level impacts of things through modulated data streams. And ultimately, goal is to come up with more of an automated test environment, multi-node system, where we can look at the impacts of different interferers, interference conditions, and then tying signal processing characteristics to the antenna's actual parameters. So basic antennas, right, horn antenna, vert antenna, the stuff we commonly use with our SDRs, right, static antennas. Goal is, can we come up with something that's more reconfigurable, tuning this around? And as I mentioned, this is not my expertise. If you want to talk about optical wireless transmitters and receivers, you can come talk to me, but this is background from Oklahoma, some of the tools and the equipment that they built up. Long story short, with this antenna, you basically move that conductive disc up and down using the actuator that they have in there, so the control on that to essentially tune the center frequency. And then they have some other interesting hardware with, framed as filtennas, so you get filtering and filtering flexibility with that as well. All right. At the end of the day, they noted that the center frequency, basically that tunability and where you tune it, also impacts the antenna's response. So kind of in conjunction, jointly modifying your signal processing characteristics or your signals characteristics is something we want to do together in this concept. The software that they work with, again, this is some mechanical actuators to kind of move that thing around, that disk around. So what they're working with is this NewScale Technologies software called Pathways. Basically, it's the control software for these small scale components. There's a manual control mode. That's primarily what they were working with for their initial testing. And then there's a scripting mode that gives you kind of basically generates an XML code that highlights their script, load and repeat and replay a bunch of script scenarios. Ultimately, this ended up being the brains of this whole system where we can interact with some of the GNU Radio tools and add the SDR into the loop. But I'll come back to that in a minute. From there, in the hardware-software interface, ultimately that separation with the disk is what tunes the center frequency. The motion is operated with that NuScale pathway software, and there's sort of this calibration step. So they come up with the calibration to tune figure out the gap size that leads to the specific tuning. They use that calibration script from their prior testing to generate the values that go into this pathway script, execute it, and then move the actuator to the target position, which ultimately tunes the antenna. All right, tying back to GNU Radio and some of the SDR applications. So now we're looking at creating this test environment, so interferers, your transmitters, your receiver with this antenna, tying it all together in this multi-node system. So that's where XML RPC and ZMQ comes into play. Essentially, if you're not familiar with these tools, XML RPC basically is your remote parameter control for distributed GNU Radio flow graphs. So you drop this XML RPC server into your flow graph, and you can control the parameters nice and easy from a Python code and some other node. ZMQ, same idea in the reverse. So now you get your remote access to values or measurements within GNU Radio. So we're using the publish subscribe model for that. And then the other tool that is sort of a tool, not really a tool, GRCon, is just this open source repository that we have that's basically the starting point for all the code and the software that we're putting into this. A lot of it is simulation right now, and then the GNU Radio flow graphs that are integrating, that we're using integrating with that pathway scripts that are also posted for this joint configuration. And this is what we'll be building on in the future as well. So to start off, just kind of thinking of a simulation to show the basic idea. This is a relatively naive model in GNU Radio, but modeling sort of the analog front end in some ways to recognize the potential impacts of these filters. So we have a simple carrier modulator, kind of very naive, as I mentioned, but the takeaway from this is that we're using simulation sample rates. So a nice benefit of DSP or SDR or GNU Radio tools is that the value in that block is just a number, so we can slow it down in what we're actually looking at, but we can see some impacts by applying to our different filters and different characteristics. So we model the antenna responses in two different paths. We model basically your analog to digital conversion with decimating filters there. And then we have XML RPC and ZMQ, as I mentioned, to kind of push values to change from an external script and pull those values out with ZMQ. And then initially configured with localhost, we can move this to something that's remote, and then decouple the two parts of this to have our full configuration. So, initial script, relatively simple to start. I'll start running this, and you can kind of see the basic idea of the script. We have the terminal there, ran the external program, communicating through localhost into GNU Radio. All we're doing is taking the top two blocks, or sort of the full RF view or simulated view. We're sweeping a tone through, very naive, as I mentioned, but the idea is sweeping this tone through, seeing where you run into what is essentially aliasing, right? So the broadband antenna response of a simple basic antenna versus the narrowband response with more filtering capabilities, and they're just coming up with some simulations that sweep either tones or sweep an interfering signal across the band in some way. Skip through this to show the next one. Main point we're trying to show here is then the frequency agility. So now if we take that signal of interest, and when the interfering signal comes into our range, we can actually move or change where our component is. So just jumping around the spectrum and more intelligently. Main difference is that as we move through things, right, we can somewhere around here, switch the carrier, jump things around. You're moving your carrier and your signal around with the basic antenna, but the broad response of the antenna still shows up with some of that aliasing. Moving the filtenna's response around, cut some of that without even considering any of your filters on the actual RF front end. I'm going to come back to this in a second. I want to describe the architecture first, so how we sort of scaled this up. and what we set up with the team at Oklahoma. So I mentioned NuScale Pathways as the software that configures their reconfigurable antenna. You can see down in the control PC at the bottom, that's where their Pathway software is running. Essentially, that can talk to that reconfigurable antenna via network connectivity there. In any way there. It also incorporates within that control script or that control computer Python script that essentially talks out to the transmitter and receiver to change your signal processing characteristics and modify or update the SDRs, the USRPs up there. Putting this all together in Pathways, you can call out those external scripts. So you're essentially creating the script in Pathways that does your reconfigurable antenna configuration setting, modifies and changes the signal processing characteristics, and then loops through that for all the different test scenarios of interest, adding interference, removing interference, all these characteristics. Going forward, this is sort of the direction we're scaling it to, trying to get us to a broader testing environment, and again, coming up with a bunch of different test scenarios to observe how this might actually impact the modulated data performance, a full kind of communication link performance in a system like this, comparing your basic antennas to some of the different reconfigurable antenna hardware that they have. I'm trying to think what my timing is here. I've got good time. Okay, so I'll go back to this one for a second. This is basically our setup before we have access to those reconfigurable antennas. This is our setup at UMass, basically before we hand off the software to them. So, oops, I don't know if that video is going to play going backwards. So in this case, we just have two Linux boxes running GNU Radio on those sides, the Windows PC running Python script out to control those, and we're just cycling through a couple different characteristics to test presence of interference, absence of interference, presence of interference in signal, and look at those scenarios. The idea is now handing off this script to the team at Oklahoma. They build it up into their system, incorporate this into that Pathways software, and come up with something where we are here, which is the outcome of last week, kind of merging all this together to get it to actually do something, but we haven't done a ton of actual testing yet, but I'll give you the basic outcome here after I start this video. Basically, they're starting that Pathways script in the software, showing that it's running GNU Radio or the Python script to call out and configure, and you can't really see it in the video here, it looks like, but running that flow graph on the left, or changing the parameters in that flow graph on the left remotely. And then as it goes through the script, it's basically changing the interference characteristics. Ultimately, what it comes down to the bottom, and you'll see in a very brief second, if you watch that antenna right around now, or shortly, it will change that location. There it goes. Yeah, so that's kind of merging it all together, demonstrating the connectivity of these two different tools, bringing it together, and now this opens up the testing capabilities for what we want to do going forward to actually see how this impacts some of the signal characteristics and ultimately the signal chain characteristics. All right, so main outcomes from this work so far, again, early stage collaboration, kind of bringing these two groups together, starting with GNU Radio simulation just to see and demonstrate what they wanted to work with, integrating GNU Radio with that NuScale Pathways software to get the combined or joint configuration of the front end antenna and the signal processing characteristics, and then where we're going from here is to improve some of these testing scenarios, extend the script scenarios within Pathways to come through a bunch more test scenarios, implement modulated data stream stuff we've done with the optical wireless setup and system before within their system, and then ultimately look at how your packet error rate and other higher level performance measurements show up in this system. That's it. All I got there. Thank you so much, and thanks to all the GNU Radio folks for organizing and for all this conference stuff. Thanks.
We've got another 15 grueling minutes of questions. Who's got a question for our speaker?
I think I only got 2 minutes, right? Hopefully I only had a 15-minute talk, because my block was only 15 minutes. But
are there any questions?
Well, just kind of how did you happen to get hooked up with folks in Oklahoma? Was this like
It was, it was an interesting connection through a colleague of mine who does antennas work at UMass, new colleague, Dr. Rule at Oklahoma. So we started, they were talking about wanting to get beyond just looking at the signal characteristics and do more performance measurements up there at the higher layer. So they were trying to figure it out, and I had worked with Dr. Patel at UMass previously with some of this SDR stuff introduced, and kind of went back and forth. She said, hey, the other guys over in this group are actually doing this with the optical system. You guys have some non-conventional front-end hardware too. Maybe it merges together nicely.
Great. And then they just put it in a box and send it to you? And
they haven't sent the antenna at all. The idea is
okay.
we're
You're
developing the
sending
software, kind of shipping it over and posting everything on the repositories, and then they pull and see how it works on their end, and going back and forth with that.
Okay, great. Thanks.
Okay, any more questions for our speaker? I did have to remark, I was impressed that we're now doing non-traditional SDR, given the, I don't know how long this conference has been running, but it used to be that SDR is non-traditional, and now we have non-traditional SDR. Okay, thank you very much for the talk. So now we have a bit of a dilemma. We can already ask our next speakers, I think it's two of them, John Kraft and Mark Thoren, to come over here from Analog Devices. But that's a little bit early. I don't know if they are expecting people to... Sorry? You are scheduled for... Yeah, sorry, I'm doing this for the first time. Apologies. Please take the stage. Don't let me waste any more of your time.
Yeah, is it okay if I use this HDMI? Okay.
So our next speakers are John Kraft and Mark Thoren from Analog Devices, talking about phased array FMCW radar using a phaser and GNU Radio Companion. Please start.
Yeah, thank you. Yeah, so my name is John Kraft. I'm joined here by Mark Thoren. We both work for Analog Devices, and we've heard some great talks, especially in the last couple hours on phased array stuff. Luigi and Bailey gave very inspiring talks, and you may have heard those talks and said, how can I get started in phased array beamformer? And how can I learn something? Or I've got an idea that I want to prototype something with, but how do I get started with it? How can I do something physically with real hardware? And so that's what we want to talk to you about today, this new kit that Analog Devices has released called the Phaser. And we're going to talk about how to use that with GNU Radio. So we'll do a little bit about like what is beamforming. Luigi did that, Bailey did that, and we also have to do it. It's obligatory. Anytime you talk about phased arrays, you always have to say what it is. And then we'll talk a little bit about the this phaser kit that we have, and it's actually demoed at our booth as well. And then we're going to talk about how to control it with Python, because then next we're going to talk about how to control it with the GNU Radio, but we're just going to use the Python block in GNU Radio, and I'll explain why I chose to do it that way and kind of the advantages of using GNU Radio with that Python embedded module block. And then hopefully we're going to do a live demo. You never know if a live demo is going to work or not, but we'll give it a try. So obligatory stuff, right? It feels redundant, but we got to do it. Normal antenna, right? You point the antenna where it's pointed. That's where you get the greatest gain. Phased array antennas, we're also pointing the antennas, but we're steering it electronically. Generally, it's a flat array, although not in Bailey's case. And so you can't tell what direction the antenna is pointed just by looking at it. It's all done by electronically steering it. And here's a nifty little animation on how that comes together. So you have some RF source, it's shining down its RF goodness onto your array, and depending on the angle that source is, right, it's going to hit one element in the array before the other elements, and some very small amount of time later, like picoseconds later, tens of picoseconds later, it strikes the next element, and so on until it's shined across, this planar wave is shined across the entire array. And our goal is we want to pick some kind of a delay such that we can align all of these waves, all these signals for a given steering angle, and then we can sum them together coherently to improve our signal-to-noise ratio. That's how we steer the beam, by choosing that delay. And so that's been around for a long time. People have been doing that for a long, long time, but increasingly now we see this growth area in three primary areas, things like mobile communications, like 5G, millimeter wave beamforming, MIMO kinds of things, radar, like automotive radar, and military and aerospace and defense radar systems. And then all these LEO satellites, these communication systems that are being launched. These LEO satellites have a very short orbital period, and so they're constantly zooming across the sky, and so the non-mechanical nature of steering a phased array antenna allows you to lock into one of the satellites, track it as it moves across the sky, and then before you lose that satellite, you can search the sky with another beam and find a new satellite, lock onto that satellite before the other one goes past the horizon. So there's just been a lot of interest in all that kind of stuff in phased arrays, given all the work being done in primarily those three areas. But so to get involved in the phased array kinds of process, it's kind of this merging together of a bunch of disparate skill sets, RF hardware design and software and system design, and of course the algorithms and the coding, to get it to do something that you want it to do. And so putting all that stuff together, especially in some of these larger, more complex systems, can be very overwhelming. And so how can we get started? And with that, I will turn it over to Mr. Thorne.
Yes.
That's a picture of Mark.
Oh, geez. All right, thanks, John. Most of the systems that you've seen here so far consist of a bunch of different boards all cobbled together. And when John first started working on this, his workbench was covered in evaluation boards and Raspberry Pis and a whole bunch of cabling, mess of cables to hold it all together. With that, we decided that we'd take a stab at creating a standalone kit, like a little assembly that allows you to explore beamforming concepts without any cabling, something that's sort of ready to go off the shelf here. And this is the result. It's a phased array education prototyping platform, operates from 10 to 11 gigahertz. It'll do 500 megahertz FMCW chirps for radar applications. The antenna array is 8 controllable channels and 2 transmit channels. All of the software is open source, based on libIO device drivers and Raspberry Pis and ADI Kuiper Linux. The price tag came in at around $2,800 and change, it's released and fully documented. So the goals of the phaser are really an intuitive, hands-on example. Something that allows you to look at the textbook and sort of say to yourself, yes, I understand how that works, but then to really touch it and to see it in action and to see the imperfections of the cruel and unyielding real world, noisy signals and beam patterns that don't quite look exactly as you would expect them to. Okay. Not only that, provide a pathway to prototyping systems and eventually moving on to something that is production worthy. So a quick overview of the hardware. So this is just a photograph of the top of the board. On the right-hand side, that's actually the reverse side of the antenna array. So each row of 4 elements are summed with equal gain with Wilkinson combiners, and each 4 columns feed a single ADAR 1000 beamformer chip. There is a ramping PLL and a mixer for each ADAR 1000. Oh, yeah, there we go. Guess animation here. So the antenna array, LNAs, beamformers, and mixers, the ramping PLL, and then finally the transmit path. Okay, and so with that relatively simple hardware, that opens up possibility to explore a bunch of different concepts in detail. So how do we digitize a signal using a software-defined radio box like the Pluto? Explore antenna impairments, things like grating lobes due to inadequate element spacing, the effects of finite tunability of gain and phase. Steering angles, how do we shape a beam, how do we taper, get rid of side lobes and control the width of our main lobe. Monopulse tracking, how can we track a target as it's moving around in front of our array, and of course radar applications. So just an example of how we would do monopulse tracking here. So in monopulse tracking, we look at the sum of our two channels for the payload data for the information. By looking at the difference between the two channels, we can tell whether our source is a little bit too far to the right or a little bit too far to the left and sort of incrementally steer accordingly. And for a radar application, we set up our local oscillator to do chirps instead of a continuous frequency here. So in the upper left, that's a spectrogram of the output of our ramping PLL, and in the bottom we can see a target moving forward and backward. Okay, as we go through the next couple of slides, keep in mind that all of this is based on open source released device drivers that are production worthy. So any time that you spend learning about the devices on the phaser can carry over to more elaborate prototypes and then on into production with exactly the same code. So how do we control the phaser with Python? So at a system level, the things that we have to control, again, are beamformers, a software-defined radio receiver like the Pluto, and a PLL. The devices on the board themselves are controlled with a serial peripheral interface, or SPI, and of course a standard laptop doesn't have a SPI interface. So a Raspberry Pi was super convenient for this purpose. It has a native SPI interface, it runs Linux, and we run ADI Kuiper Linux on the Raspberry Pi. So that includes all of the device drivers that we need, and we've got that interface handy. To control the Pluto, we just connect it to the Raspberry Pi using one of the USB ports. So again, super convenient, allows us to put it all together in a convenient assembly. Okay, so various ways of controlling the devices. A couple of methods are MATLAB. So we are working on board support package in MATLAB. We've got signs of life and a couple of simple examples posted already. And using Python, using an abstraction layer called PyADI IIO. And we'll talk a bit more about that in a second. And then finally, we can incorporate that Python code into a GNU radio block, and so have the best of all worlds here. So PyADI IIO is it's an abstraction layer that makes native IIO devices easier to use. So it sort of takes away a lot of the boilerplate that's required to talk to the raw IIO API. And so how easy is it? Well, here's an example. So in 5 lines of code, we can open up a connection to a Pluto SDR. We can set our LO frequencies and then finally collect a block of data for further processing here. So 5 lines of code to get up and running with the Pluto. And then controlling some of the devices on the phaser board itself. So this is a single line of PyADI code to set the onboard local oscillator to my signal frequency plus the Pluto's local oscillator, and basically set up the local oscillator, and then finally putting the pieces together, we capture the signal, and then at the end of this slide, we've got data captured in an array, and we can move on from there and do further processing. How do we, just an example of controlling the elements in the array here. So here's an example of steering the array towards mechanical bore sight or 0 degrees, and then applying a Blackman taper. So in the little gain list array there, we've got our 2 center elements set to maximum gain, and then we taper down from there. So that has the effect of suppressing side lobes and widening up our main beam. So that's enough of a toolkit to, that's all the software pieces that we need to start building more elaborate examples in GNU Radio.
Well, let's see if we can do that live demo here now. Well, and yeah. Before we do the live demo, I'll show you. This is what the little kit looks like. A nice little mounted little tripod guy here, and the nice thing about, so we have a lot of examples in Python, we have several examples in MATLAB, but the nice thing about using GNU Radio, so I'll show you how I did it here, and I fully realize I'm not using all of the power that GNU Radio has, but I'll tell you the advantages of what I like about it, and that is, I think a great advantage of it is GNU Radio has a great GUI kind of interface. It's non-blocking, it's automatically multi-threaded. It makes for a much nicer GUI interface than something you build out of Python, like tkinter, or even using Qt in Python. It's a lot of work, and it adds a lot of clutter to your code that is extraneous. And so it's super nice to be able to drag and drop these GUI blocks down on GNU Radio Companion and have that work with a Python module. And it's also very fast, like the waterfall plots, the spectrogram plots and stuff like that. They update like very rapidly, and it's just, that's really hard to do with other Python kind of implementations. And so I'll show you how we did it here. It's basically just to use an embedded Python block. I didn't use an outer tree module because I don't know how to do that, although I think there are classes this week on how to do that. But it also kind of seems like outer tree modules, they just kind of fall out of sync with GNU Radio versions and stuff. There's a bit of a graveyard of some nicely named outer tree modules that we can't use anymore. And then being able to import Python code into the Python block kind of allows us to reuse a lot of the Python examples that we already have, and we can port those over into GNU Radio. So let me try it. So I'm going to set this up down on the floor here, so you guys probably can't see it very well, but. And then we use this little, Mark showed this in some of his slides, it's this little HB100. It's a little guy you can get on DigiKey or eBay or whatever. It's like $3, and it's an X-band 10 gigahertz signal source. That's what we use it for. What it's actually meant for is an occupancy sensor. So like if you walk through a convenience store or go into a store and the door opens for you automatically, it's probably using one of these little HB100 little modules. But what's cool about it is it's battery powered. It's this nice little wireless signal source, so we can walk around, we can do some things, and then we can plot the array pattern and watch that update real time. So this also will go on the floor. Oh, that may help. Yeah, thank you. All right, so let me switch over here. I'm just going to VNC into the Raspberry Pi here. Type my super secret analog password. Okay, so here's what the flow graph looks like in GNU Radio Companion. I'm using 3.8 because that's what seemed to run best on this distribution of Linux that we're using on this Raspberry Pi. But so there's a Python block here, which is where everything happens. And then all of this other stuff, these other blocks, these are just GUI sliders, tab control. We use the constellation sync. I think in later versions of GNU Radio, they have a better way to plot X and Y. But in 3.8, it's the constellation sync, so you'll see, quadrature and see real and imaginary on the plot. But so everything just happens inside this Python module. So let me open that up. I'll just show you that code here real quick. Editor, use editor. And we choose the best Python IDE ever, this Thonny program, because it's ships with the Raspberry Pi. I think there is a session, maybe tomorrow, that Wiley is doing on these embedded Python blocks and how to, Friday? Okay, yeah, so I actually need to go to that session. I was asking Wiley some questions earlier. I don't know if I did this right. But essentially, so this Python block is great. You just call all your libraries just like you would in regular Python, and then you create this this class, this GRSync block, and then all of the things, the variables, the slider bars, and the GUI objects that you saw on the flow graph, you can just pull into this Python block if you name them the same thing. That's really the key, is you have to name them the same thing. So like, for instance, there's 8 gain blocks that we're going to use to do tapering. So you name them, gain 1 through gain 8, And then down here, when you want to instantiate them, you call them self.gain1 equals gain1. So that's linking inside of Python, you're linking that gain1 thing so that when you update that gain1 slider bar in the GUI, it's going to register a callback function every time you update it, and it's going to use that new updated value within your Python script. So I mean, it works great. I mean, it's very slick. Just don't rename this. Like if I renamed it, self.gain_1 equals gain1, wouldn't work. Or at least that's my understanding of it. So we do that. That's how we pull in all of those things into the script. And then we scroll down. So there's all that stuff. And then like Mark talked about, we just create these objects for the stuff that's on that phased array board. So it's primarily we use the Pluto software-defined radio, which maybe some of you are familiar with. Where is that? So we instantiate an object for Pluto, which we just call SDR. And then we instantiate the two 8R1000 objects, and we form them into an array, and we call that just receive array. And you can structure that array however you want, actually. There's actually ports on here. If you didn't want to use the built-in receive antenna on this phaser board, you can, with SMP connectors, you can go out to your own receive antenna. So you could construct this in a different way, even in a two-dimensional array, like a 2x4 matrix or something like that, or you could use your own antenna. And so you just organize those elements right here, as in this array. And then once you've created those objects, it's just you just do whatever you would want to do, like in a normal Python program. And that's all done after we define different functions and stuff. We go down to this work function here, and in the work function, I have it doing some loops where we're going to scan through all the different steering angles. Yes. Question? 5 minutes left. Oh, okay. Okay, yeah, 9 minutes left? Okay. Okay, so we better run the program. Okay. That's the other curse of the live demo. Yeah. Sort of. So here's our array factor pattern here on this device, and you can see that as we move this guy around, the peak here will track, and so now the peak is over at, say, plus 45 degrees or so. If we move back to mechanical bore site, we'll see this array factor pattern here. And then from this we can do it's not quite working. My batteries might be running low. And so like we can do like array tapering here. We can control the amplitude of each of these elements, and it's super easy with the GNU Radio GUI, right? And so now those side lobes that you saw, those are now greatly attenuated, and now we just see our main lobe there. Or we can go set these all back. We can save one of these traces here. So we can then do a little overlay. And so you can see, I think Bailey was talking a little bit about some adaptive beamforming and null steering and stuff like that. And actually tomorrow, Robin Getz is going to be giving a talk on using this null steering and monitoring the EVM performance improvement with it. But so like right here, you can see, say we have a null, say at 33. I mean, we have a peak at 33 degrees, and if we want to place a null there, we can see how that impacts our array pattern. And click null enable. So now, where we did have a peak in our side lobe response from our array factor, we now have a null there. This isn't really the true way that you'd want to measure the impact of how you're doing your null steering. Really, you'd want some kind of signal performance metrics like EVM, and so we're going to do that tomorrow. We'll place some jammers and see the impact on EVM with null steering. But anyway, so that's it. That's kind of the overview. You can check out our booth if you want to play around with the phaser a little bit more. And any information like this flow graph we'll put on wiki.analog.com/phaser. So thank you.
An actual live demo. That is very nice to see. Floor is open for questions to John and or Mark.
$2,800. Is there academic pricing available for that, or is that it?
Yeah, that's the academic price. So we tried our best to get the cost down as much as possible, and that's how it turned out.
Any more questions? I noticed that your Pluto is a bit different than mine. It has 3 ports. How did that happen?
Yeah, so the new Pluto Rev C will be called Rev C or Rev D on the back of your Pluto. If you crack open the case of it, there's 2 little U.FL connectors in there, one for the second transmitter, one for the second receiver. And so, yeah, you can expose those and get 2 channels transmit, 2 channels receive. Yeah, it's pretty cool.
I'm going to open my Pluto now. Thank you. Any more questions? Because if not, we have a lot of chaos awaiting us, apparently, in the form of a number of lightning talks. So let's thank both of our speakers again, and get ready for the lightning talks. So who is the first speaker? Because I don't have a list.
So yeah, next up we have Tom Wallace from Vesprix. Is going to do a lightning talk.
I'm reading the instructions, I'm sorry. Slide advance. Oh, do we have, we have a green button works. Okay, good. So I am Tom Wallace from Vesprix. Those of you who are in Charlotte will remember someone who looks very much like me standing up in Charlotte talking about microwave SDRs. And I am here to apologize to those of you who are interested in that. We came to Charlotte to kick off our exploration of whether there was a commercial interest in a microwave SDR that we had built. And I did not know it as I was standing up there talking about what a wonderful little gadget it was, but the microwave synthesizers that we needed to build it were out of stock at that point. They had just gone out of stock, and they stayed out of stock for 2 years. So they are now back. However, we did not waste our time. Happily, we did not intend to make a business out of selling microwave SDRs immediately, so we went ahead and continued with our usual R&D work. So we're a government R&D company, and we continued to develop the design. So now we have 2 microwave SDRs, only one of which we're actually looking at potentially selling commercially, but they're basically twins, except that one is bigger and stronger than the other. We have the original 160 megahertz version, and we have the extra large size 600 megasample version. As you can see here, the specs are basically the same. The analog sections are essentially identical. The 600 has an improved analog section, and we are backporting that to the 160 now. It's got several improvements that would be beneficial for folks who are concerned about spur levels and such like. These are fairly straightforward SDRs. If they were 6 gigahertz SDRs, they wouldn't be anything different from a variety of other gadgets. But because we needed to work in a higher frequency range, we went ahead and built them. The one interesting thing that also makes them not twins is the option for the 600 to take an attached processor, and in this case, that's an NVIDIA Orin, which has a reasonable amount of GPU capability, and the Orin talks to the FPGA over PCIe, so there's no network involved. Those are sort of the new features on the 600. External LO inputs for synchronizing multiple devices, which the original one will get. The faster converters, which the original one will not get. 40 gigabit Ethernet, and the NVIDIA Orin are going to be unique to the 600. But basically, the 2 years were not a wasted time in terms of the performance of the device. We're happy that we were able to add some more performance benefits to the analog design, and then we'll backport them to the new 160 board. And for those of you who are interested, we've got the host software, which is the host side library that talks to the device over the network. That's on GitHub right now. We have the documents on Read the Docs. There are links to those on the next graph. And once we have the changes backported, which will happen very shortly, we're looking at opening the VXDR2160 for orders on crowd supply. We need to work through the crowd supply process, but that will be an easy way for people who are interested to show their interest by putting an order down. And then based, of course, on the results of that, we will decide whether to go ahead and produce it. And there's also on the next page, or on the next page, that's our software-defined radio website. And if you were to go there and look on the far right, you'd find a links section. And under the links section, you would find links to all of the stuff that I've talked about. So for those of you who have interest, and especially for those of you who have had interest for 2 years and have been denied any real progress, I hope this will be beneficial for you. And for those of you who are new to it, if you are interested in an SDR with capabilities similar to the other sort of high-performance SDRs that you see with 100 to 200 megasample bandwidth, but that works in a higher frequency range, this is an option that, as far as we're aware, is unique in its price range. And I have plenty of time here, so if there are any questions, I'd be happy to answer them. I didn't mention the price, and well, yeah, and that's a fair comment. So we have not set the price, right? That happens when we open things on crowd supply. But if you're familiar with other gadgets, the Signal Hound is a very nice spectrum analyzer that goes to 20 gigahertz. Signal Hound has a very nice spectrum analyzer that goes to 20 gigahertz with a 10 gigabit Ethernet interface. And the price that we see for the 160 is in that ballpark. So if that's familiar to you, then that shouldn't be a shock. Microwave devices are inherently going to be more expensive per channel than other devices. All right. No other questions? Well, thank you very much.
You're right ahead. Or I can't introduce you because I have no idea.
Got a last minute lightning talk. Yep. So my name is Mark, and I'm going to be throwing out an idea that myself and some of the SIG-MF maintainers have been throwing around. So I love SIG-ID Wiki. Who here has used SIG-ID Wiki? I know the CTF folks tend to use it a lot. So this idea is sort of like a SIG-ID Wiki on steroids. So if you're not familiar, SIG-ID Wiki has information about almost any signal you can think of. Some of them have recordings of the signal, but only some. So in imagining a perfect SIG-ID Wiki, you would have a recording for every signal, ideally like one clean recording that could represent that signal. It would be nice to be based on SIG-MF, of course, for interoperability's sake. You could link out to adder tree modules for demodulating that signal. SIG-ID Wiki already has a decent system for community input. It uses a wiki, and you can make an account. But I can imagine even adding to that, like having an ability to comment or star recordings, just so it's convenient for people checking it out to look at what's common, or trophies to help incentivize contributors of recordings and metadata and annotations. The idea for voting on desired signals that are missing, and maybe even having a bounty, like a little donation thing for a specific high-value signal that the community wants. So if you were at my talk yesterday, you can probably make a connection that IQ Engine could be used to host this list of the SIG-ID Wiki on steroids, if you will. That the benefit there would be being able to view and sort of play around with the signals in the browser, in addition to what SIG-ID Wiki already offers. But the main point would be using SIG-MF and having a recording for every signal. So how do we get there? Well, obviously we would need a lot of folks to help contribute and collect signals, ideally clean recordings. And then I think the harder part would be figuring out, another tough part is figuring out how to store all of this information in a way where we can keep using SIG-MF for the recordings, but still encapsulate the community provided info. So like you could stuff everything in the global description, but that might not be the most effective approach. And then also having a way to version control, maybe with Git, and an easy submission. So anyone who wants to add to a specific signals entry can submit information, or like add annotations or modify them, and then have a way for maintainers of the site to like approve the diff. So that would take a little bit of tooling. But if you think it's a cool idea, reach out on the SIG-MF channel on Matrix, or if you're not a user of Matrix, you can email me at pysdr@vt.edu. And I'm trying to get like anyone interested in the same place so we can chat about if this is at all possible. And if anyone knows the folks involved with SIG-ID Wiki, definitely let me know, reach out on Matrix. And that's all. Any questions? I think this is the last lightning. Oh, by the way, there's a SIG-MF workshop after the break. So mine is the last lightning talk. We have a break and then SIG-MF workshop in one of the rooms. So if you're interested in recording RF or want to learn more about SIG-MF, definitely check it out. Me and Jacob will be putting that on. All right. Yep.
Yeah, you mentioned having flow graphs to demodulate signals. Would you also consider having flow graphs to generate those signals?
Yeah, I mean, really anything, SIG-ID Wiki, it would be like one page per signal, per protocol or waveform, whatever you want to think about. So anything related to that signal could be put on that page. Yep, transmitters, receivers, anything at all.
Any more questions for Mark? Because I have one. What are the legal ramifications around the world for different countries of putting those kind of signals online?
I don't know.
Hey, that's knowledge is a good.
That's the beauty of doing something under like an open source project or individual, right? It's not going to come back to a bunch of lawyers. The worst case is it could be taken down. I don't know.
Worst case. Okay, thank you.
Yep.
Hi, I just have a quick question.
The signal samples that you have there, is that only for the US or is it for other countries around the world?
Well, SIG-ID Wiki, that's not me. Only some of the signals have recordings, and I'm not sure about that. For IQ Engine, the current signals are taken all over the world. We've got some contributors in France and UK, and a lot from the US. So there's like you saw FM France. That was just FM radio in France, right? Did that answer the question? All right. Yeah, thank you.
Okay, thanks. Are those all the lightning talks for today? Okay, that means it's break time. Thank you very much. I think we resume at, what is it again? 3:20 in this room. Thank you.
And first up, we've got Marius Shechulis, and I know I massacred at least one vowel in the name, but you can correct it when you get up here, talking about ultra-wideband SDR architecture for AMD RF SOCs. So welcome to GNU Radio.
So, hi everyone. I'm Marius Churchilis. Really weird surname, I know. I'm here from Scotland. I'm from University of Strathclyde in Glasgow. Hopefully everybody understands my weird mix of accents. And I'm also still a bit jet-lagged. But I'm here representing our group, Strath SDR, and my personal work on kind of using GNU Radio with Xilinx Ping framework for FPGA accelerated GNU Radio applications. So I'm just gonna kind of show my current work and my future work, hopefully. I put using Ping-based GNU Radio blocks in quotes because I'm not actually using them, but I'm gonna give a small sneak peek to what's coming. Oh, there's a clicker. Great success. So content slide, everybody likes one, but you better look at the pretty logos. So I'm going to give a short introduction on Ping and RFSoC. So can I get a hand who knows of Ping or has used Ping? Okay, there's people who know it. Hands who have used RFSoC? Okay, yeah, that's pretty okay. I'll give a quick introduction on both of these anyway, so everybody's on the same page. I'll talk about my hardware setup. I'll talk about my hardware architecture, and hardware architecture here I mean the FPGA architecture. I'll talk about software architecture, so both the Jupyter notebooks running on the RFSoC as well as GNU Radio transmitter flow graph and my GNU Radio receiver flow graph. I'll give a short sneak peek to my GNU Radio out of tree module of GNU Radio Ping blocks. And then, of course, a conclusion. So, introduction. I just saw this. So modern software-defined radios are now capable of massive data throughputs, massive multi-gigabit per sample rates, as we've seen from analog devices, as well as Xilinx, or AMD Xilinx or FSoCs. But it can be quite difficult developing these really high rate systems, especially for people not super used to FPGA development. So sometimes it's very convenient to use software tools such as GNU Radio or Simulink that are block-based, and people with DSP knowledge but not necessarily programming knowledge can kind of build their flow graphs for testing purposes until they decide what they actually want to build and if their algorithms are working, and then potentially transfer them to either hardware or use other acceleration methods. And we present an open source RFSoC design that uses the QSFP 100 gigabits per second network interface to offload samples generated by GNU Radio on a just general PC to RFSoC, transmit them, receive them, and get them back into our PC as kind of a loop back. So a quick introduction to Ping. So it's an open source project by AMD that aims to simplify development for SoC systems. So you have your processing system, which is usually ARM-based, running Linux, and it runs on that processing system and allows you to kind of interact and control your FPGA logic. So things like loading and managing your bit streams. It does automatic detection of memory mapped interfaces, and instead of you having to go to your Vivado and look at all your register maps, it kind of does that automatically for you, so you can just invoke certain interfaces in a very Pythonic way. It allows you to handle programmable logic interrupts through a sync.io library in Python. Also gives you drivers for most commonly used IPs, such as DMA for large data transfers between PL and PS. as well as things like GPIO blocks, video blocks that are available in Vivado. And it also makes creating your own Python drivers for your own IPs very easy because of the available templates and kind of available resources. And now, since the release of RFSoC Pink, it also has Python drivers for RFSoC specific functionality to configure your external RF reference clocks, to control the RF data sampling units, and as well as the soft decision forward correction hardened blocks inside the RFSoCs. So this is the kind of second generation board from AMD Pink team that's kind of targeted towards academia mostly. So it comes with a reasonable price tag as well as like a lot of functionality that's again geared towards academia. The board is fully open source, including the hardware and the software stack that it's running. So you can, it's actually developed by a company called Real Digital. So if you go onto their page and you ask them for the Gerber files, they will give them to you. Things like schematics are available fully. So if you want to develop your own hardware design or like actual PCB with RFSoC on it, you can use this as like a starting point and then modify it to your needs. So just some specifications. So although there's more channels on the board that are made external, there's more channels on the chip that are made external on the board. It has 2 ADC channels, both running at 5 gigasamples per second, which gives you about 2.5 gigahertz instantaneous bandwidth. Sorry, it has 8 channels of ADCs and then 2 channels of DACs with 10 gigasamples per second approximately. It also has the 100 gigabit per second QSFP network interface. So that's the big spiky cage on the right-hand side. That is right-hand side. Also the PS, which is a 64-bit ARC architecture, ARM core, that's running like a slightly customized Ubuntu-based Pink Linux distribution that comes with a lot of just really nice features that allows you to kind of plug and play, including Jupyter Notebook setup, or Jupyter Lab setup, I should say, as well as the whole Pink framework in there. And of course, has a massive PL or FPGA fabric. So my hardware setup overview. I use GNU Radio to generate arbitrary signals. In this case, I chose OFDM. I'm generating them at 61.44 megasamples per second. Again, on the PC, I'm transferring them over a UDP-based network layer over the QSFP network into my RFSoC. And then I'm interpolating those samples by AT inside the RF digital up converters. So I'm not actually using the RF SOC fabric. I'm just using the hardened IPs. I'm transmitting them over DAC, receiving them over ADC, which has, one of them has 40 times down conversion, and another channel for debug purposes has a variable decimation rate from 2 to 16 times as kind of a wide bandwidth thing to check my spectrum. And then the Ethernet connection is used to access the Jupyter server and the Jupyter Notebook that's running on the board to kind of control various RF ADC and RF DAC parameters through GNU Radio. So this is the hardware architecture. Again, the kind of network layer, the QSFP network layer, is made completely in programmable logic, but configured from the PS. It's using the hardened CMAC IP as well as an open source network layer IP by the AMD XUP team. It's a bidirectional network. I'm now looking at the... So there are certain things that that took a bit longer than I expected. So apparently GNU Radio UDP sync block, anytime you run on runtime, it chooses a random UDP port, which I was not aware, which caused me some problems because the net layer IAP inside the hardware design needs to know the IP before runtime so it can configure its network socket table. So that caused me some issues with connections, but I've made a custom IP to kind of pull the senders and receivers IP and port addresses from the network stream and then kind of update that network table later on, as well as if I really needed to, I can just drive the tvalid high and override my, my network stream. So that's the net layer T user IP, which is kind of a bit of a hack, but it works. And then, as you can see, I have an AXI for stream switch, which takes both of the ADCs, and I can select at runtime which of the ADCs I want to see on my receiving end on the PC. And I'm, again, using the internal hardened digital up converters and digital down converters inside the RFDC to kind of achieve decimation and interpolation rates. So this is kind of a software architecture. On the board, as of now, I'm still using Jupyter notebooks. It's a Python script that does a bunch of setup for the network layer, including the socket table setup, as well as it does the initial configuration for RFADCs and DACs. It also starts an XML RPC server, which then allows me to use GNU Radio to do remote calls, to do like remote changes on the sampling rate and the center frequency as well. So it's just a, I'm assuming everybody has seen at least Jupyter before. So this is my GNU Radio transmitter flow graph. It's based on the GR digital example of OFDM transmitter. I've just modified it for my needs. The reuse is great. I've tried using the kind of integrated hierarchical block, but I was getting way worse performance, about 3 times worse than just the example multi-block flow graph. I'm not sure why. If anybody knows, please contact me. I would love to know. But this one is working quite well. It's giving me stable 61.44 megasamples per second. Even I can push it even more if I really wanted to. And it's, again, running in real time. The receiver flow graph, one of them is, again, I should have mentioned, I'm running them as 2 separate kind of flow graphs. Again, I was having performance issues if I put them all into a single flow graph. But the receiver flow graph is just a UDP source block that's receiving a bunch of data from my RFSoC board, then doing some data conversions, and I'm using a GPU accelerated GR phosphor to do the spectrum analysis and just kind of checking how my transmission looks like. So this is my current result. It doesn't look the prettiest. There's still things I need to tweak, but at least it looks like OFDM, hopefully. Again, I'm using, this is captured with one of the ADCs that's set up as like a flexible bandwidth sampler with 16 times down, digital down conversion. I can go to a lot higher bandwidths, but then I can start seeing weird things on the spectrum. Now the GR ping blocks, I really hope to actually kind of transfer this design and similar designs to using GNU Radio and generating the actual signals on the RFSoC. Again, the PS is ARM64 based, and with things like Mamba and Radio Conda, I can install GNU Radio on the board itself and actually interact with it. Even things like the companion work fine, albeit a little bit buggy because the board doesn't have a GPU. But what I'm trying to build is these kind of ping-based Python blocks for GNU Radio that would allow me to, again, kind of easily interact with the hardware. So things like loading my overlay bit stream, having DMA sinks and sources for large data transfers, as well as all the RFSoC functionality, and then use not necessarily XML RPC, which is very well supported in GNU Radio, but potentially other ways to kind of achieve remote talk between two GNU Radio instances, one on the board, one on the PC. And this is just, again, a sneak peek with some status updates on how the development is working. There's some things I'm learning. There seems to be some undocumented YAML hacks that one can do to achieve certain things. So I need to stop suffering in silence and start reporting, actually, and maybe contributing to Wikipedia on the things I'm finding out. Okay, so yeah, summary and conclusions. Again, this design will be soon open source when I've cleaned it up, but the previous design that this one is based on, which was just doing a downlink from our FSoC in the 100 gigabit channel, is open source, and it's on our GitHub. So you can download it and try it yourself. It's using standard UDP network layers, so it's not necessarily just for radio data. It can be used for instrumentation. And again, with increasing capabilities of SDR tech, it's going to be quite important to have these very high-speed data links between our boards and our PCs. Yeah, and thanks for listening. Engage with us. We have a lot of RFSoC targeted designs as well as resources, even a free book that's actually really popular apparently. So you're welcome to scan the QR code. I promise it's safe. It actually links just to the GitHub StrathSDR, where you can again find a lot of resources. And all of it is open source. Yeah, thank you. And if anybody has any questions, I'll take them.
Thank you, Marius. I think we'll take questions on the side so we can get the next group up here. Okay. Making the long commute from Arizona State University and talking about employing GNU Radio for robust testing of novel Dash system on chip. Gentlemen, welcome.
Hi. You guys hear me in the back? Cool. Hi, good afternoon. So I'm Saqib Siddiqui, a fourth-year PhD student at Bliss Labs in Wisca, and I have my co-presenters here, Alex, Trake, and Prithvi. Right? So we're part of the Wisca group, and today we're presenting our work on employing GNU Radio for robust testing of the novel Dash SoC. So just a breakdown of what you'll see today. I'll be introducing some of the general topics and some motivation, and then going into relevant details of the Dash SoC, and then talking about the LDPC, encode, decode, and then the GNU Radio setup with the results. All right. So what's a common trend right now with wireless systems is that the current systems and future systems have this requirement of having they require very high flexibility, and there is this need to do more in a smaller area, right? So you want to have higher functionality, and then you also want to be flexible. So if you think about this trade-off, there is this high computation performance extreme, and then you have flexibility or ease of reprogrammability extreme, right? So an example is an ASIC, which is really good in terms of their computational performance. And then on the other extreme, where you have a high reprogrammability or flexible system, you could think of an FPGA or a scalar processor. So what Dash SoC wants to do is to bridge this gap, because it's useful in a lot of ways, right? So that's the fundamental thing that dash SOC brings in terms of eliminating this trade-off and then just bridging this gap, right? So you can essentially do, you can decrease the amount of expert programmability required and then also enable a lot more higher performance and flexibility. So what we're doing today, or what we're presenting today, is the use of GNU Radio to test the dash SOC with over-the-air data. And the reason why this is important is that the initial claim that we're making is that the dash SOC is trying to resolve a lot of requirements in terms of we can test a lot of novel hardware, and then we can also actually inspect performance. So by running an actual application or an end-to-end system, this gives us an opportunity to actually exercise the framework and then test it in like real time, right? So in that direction, we've also developed GRCeater. So this was a talk that happened last year, where we have tried to integrate GNU Radio into our framework such that GNU Radio can leverage blocks that are present in dash SOC and then accelerate them on the SOC, right? So just a quick background on what the dash SOC is. So it's, the acronym is Domain Specific Coarse Scale Heterogeneous Processor System on Chip. And like I said, it's trying to attempt to get close to the compute efficiency and performance of a custom ASIC, while also being as flexible and reprogrammable as of FPGA, right? So to that effect, we have developed SoC emulation on the HTG960 FPGA, where we have kind of put together most of the components of the dash SoC. And this has given us an opportunity to rapidly prototype and test things out, right? And to that effect, to use the dash framework, we have a runtime environment. And that runtime has two tasks. So it deals with the front end in terms of generating cross-compiled binaries that can execute on the dash SoC. And then it also has an inbuilt scheduler that helps you schedule different functions to the chip, right? And then, like I said, GNU Radio has GRCeater. Our work for GRCeater is trying to break this limitation of accelerator selection at design time, right? So previously, there's this constraint where the hardware resource is decided at design time. We want to make that possible at runtime, right? So that's what we're also attempting to do. So the rest of the stuff will be presented by Prithvi, right?
Hello, I'm Prithvi again. So the part of the dash SoC that was decided to run the over-the-air data was the LDPC encoder and the LDPC decoder. The LDPC encoder runs on the CPU, and the LDPC decoder has a custom FEC accelerator that it runs on. So yeah, so I will be going into the details of the LDPC encoder, and my colleague Drake will be going over the details of the LDPC decoder. So as LDPC, it's there in the name. So as LDPC suggests, LDPC stands for Low Density Parity Check Matrix. That means the number of ones in the parity check matrix is comparatively low to the number of zeros that's there. So what's the advantage of this? It means that the computational complexity of using this parity check matrix is small, and that makes it compatible to execute it in real-time systems. The LDPC encoding algorithm that was used to encode the information bits was the Gaussian elimination algorithm. So it basically has 3 steps. So the first step is to form the parity check matrix from the prototype matrix. So you can see on the right-hand side of the slide, you have a matrix A. And each individual component of that matrix A is a column-wise permutation number. So this number is used to permute the identity matrix, and it has a certain lifting size. And this matrix is placed in the parity check matrix. And this is how the parity check matrix is constructed. Suppose you have a -1 as a permutation, the way to construct that is to put an all-zero matrix instead of a permuted identity matrix. So that's the first step. The second step is to bring the parity check matrix to an equivalent form using Gaussian elimination. And this equivalent form has a parity matrix and an identity matrix. And from this, we extract the parity matrix, transpose that, and then use that to form the generator matrix. So generator matrix has the identity matrix and the transpose of the parity matrix. So this is the second step of forming of this algorithm. That's forming the generator matrix. Now the third step is a simple vector matrix multiplication. So you multiply your information bits with the generator matrix, and then you get your encoded bits. So the function signatures that we are using over here is given. So we have developed an API which runs the algorithms on the board. So the first function signature, it takes the prototype matrix, and then it is used to it's used to form the generator matrix and the parity check matrix. So this is where the Gaussian elimination technique is used. And the second function signature is just to do the matrix multiplication. I'll hand it over to Drake to explain the decoder.
Hello, everybody. My name is Drake Silbernagel. I am going to go over the decoding process. As Prithvi stated, we have a specific FEC accelerator. It can do decoding for these three types up here: turbo, LDPC, and polar. This is the current stable version, but we are continuously iterating upon the chip and all the accelerators on it. So this is the API call for the decoder. It gives some requirements: your message bits, your encoded bits, your lifting size, the shift matrix itself, and some fixed point LLRs with a pointer to give you your output. The algorithm that we use on the actual accelerator is the min-sum algorithm. This was chosen for its efficiency and hardware implementation. And as I said, again, the unified FEC accelerator that we have can go between these three, so it was important to pick something hardware efficient to get all three of those codes on there. And then, yeah, we're going to go through just some testing and validation of the LDPC decoder. We did some internal tests, and I'm going to juxtapose that with testing it on GNU Radio. So this is a very simple flow graph compared to what some people have up here, and that's okay. We have a nice little random signal. It is being encoded from an A-list. That A-list was actually generated from the generator matrix that Prithvi discussed, and then fed back into this in the compatible format. And then we have a BPSK modulation, keep things simple, to a binary file. We'll actually take that binary file into our -SOC framework, run soft decoding, or soft demodulation, and then finally run those LLRs into our FEC decoder. And these are the results that we actually get. So this is pretty standard BER versus SNR for an LDPC and an additive white Gaussian noise channel. We have some limitations on how fast I can run a Monte Carlo. So these are 5 instantations of the actual running on the chip. Continuous development between this and GNU Radio will allow us to run a really long Monte Carlo and get those nice BER plots for those higher SNRs. All right. And then now we're going to discuss the over-the-air component, and Prithvi will go about that.
So for the over-the-air experiment, we have the following experimental setup. So we used a B210, where we have the transmitter and the receiver on the same B210. So the antenna used is a 3 dBi omnidirectional antenna with a center frequency of 2.4 gigahertz and a bandwidth of 1 megahertz. So in the GNU Radio environment, we set the transmit gain to be 70 dB and the receive gain to be 50 dB. We also have a 30 dB physical attenuator on the receiver, the receiver antenna. And this is the setup. And for the LDPC parameters, we use a rate 1/2 LDPC parity check matrix, where the number of information bits is 324 bits and the number of encoded bits is 648 bits. Like in the previous situation, we form our generator matrix on the dash SOC, and we form an A-list which is compatible to the GNU radio environment, and we use that as the generator matrix. So the block diagram here describes the transmit and the receive chain, which was employed to carry out this over-the-air experiment. So in the transmit chain, the entire transmit chain was carried out in GNU radio. So, and the receive chain was employed in, it was carried out in 3 parts. So the first part to receive, we use GNU radio. Then we do some kind of post-processing on MATLAB. And then we we send that data to the dash SOC where the LDPC decoder runs on the accelerator. So this is the flow graph that we used. So in the flow graph, we have a vector source that transmits a known sequence of data periodically, and this is encoded by the FEC extended encoder. This encoder uses the .alist generator matrix that was derived from the dash SOC. Then we pack these bits into bytes and send it to the constellation modulator. The constellation modulator uses a BPSK scheme to modulate the bits to symbols. And these symbols are also pulse-shaped with at 4 samples per symbol so that they can be transmitted over the air. Then the data is transmitted over the air through the B210 and received again at the B210. So at the receiver chain, we have a correlation estimator so that the Costas loop gets a phase estimate, and it corrects for the phase of the channel relatively easily. And the Costas loop is enough to equalize for the channel because it's a line of sight channel, and we need to correct only for the phase. So the next thing after the Costas loop we use is another correlation estimator. This is used to find where the data packets are there within the received signal. And then we write the correlation peaks to the MATLAB file. And in MATLAB, we use this correlation information to extract where the data is and then extract the symbol information. And this symbol information is written to a file, and this file is read off on the HTG, and then it runs on the system. So if we go back, in the dash SOC, we can see that there's a soft demodulation done. So the soft demodulation computes the LLR values, and these LLR values are in fixed points, so are in floating points. Since the accelerator does not accept floating point, we convert it to fixed point, and then it goes through the accelerator, and the accelerator gives us the decoded bits. So these decoded bits are still in byte format. To get it in bit format, we unpack the bits. So this is the setup, and these are the results of the over-the-air experiment. So the first waveform shows the received waveform, which we observe at the receiver. And the 2 constellation plots show the data before the Costas loop and after the Costas loop. And the small black box at the bottom shows the decoded information bits that's after unpacking it. And then it has like a bit error rate of 0, which is displayed there. I'm not sure if you guys can see it, but it's a 0-bit error rate. So this successfully demonstrates that we can run over-the-air data through, simulate over-the-air data through GNU radio and then use it on our dash SOC. So this is like a naive interpretation of what is yet to come. There can be like more full-scale, more complex integration with the dash SOC. Yeah, thank you. I'll hand it over to Drake.
So just to conclude, obviously we use GNU radio in a lesser capacity, but it could definitely be expanded upon. we can maybe take out some of those blocks and use our other accelerators on the dash SoC to perform other computationally expensive RF algorithms. And so last year with GR if we were able to compile GNU Radio to work within the chip, we can access our libdash, which is our library used on the chip, and then use our full-fledged APIs and actually get an over-the-air, real-time running environment set up. So lots of cool things to come. Thank you so much for your time. If anybody has any questions, we're open to them.
Great, thank you very much, gentlemen. Again, I think I'll let you take questions on the side if people have them, and thanks for the presentation. Our next presentation, Paul Boven. Really interesting stuff about using wide baseline interferometry and the timing required to do that, and using GNU Radio with it too.
Hi, good afternoon everyone. My name is Paul Boven, and some of the people today have said I'm a radio astronomer. I'm almost a radio astronomer. As you can see, I'm wearing at least 3 hats today. One of them is that I'm currently an external PhD candidate at the University of Leiden. But my day job is also in radio astronomy, is at the Joint Institute for VLBI in Europe. And I'm also a volunteer at the 25-meter radio telescope in Dwingelo in the Netherlands. And all of those 3 things will come together in this presentation. So a quick outline of what we're talking about, a little introduction in radio astronomy and why it is so interesting, why we need interferometry in particular, and then how White Rabbit can be used as a distribution for clock signals for interferometry, and then try and measure the performance using the equipment at hand, including GNU Radio. So on the left you see a nice picture of a spiral galaxy face on, seen in the optical light. And with a radio telescope, you can see that the hydrogen radiation at 21 centimeter in blue is actually going much further out from this galaxy than you would think from just the optical image. So you learn something new by looking at new wavelengths. You see that there's much more cold neutral gas in this galaxy than you would expect from just looking at it. And it's that kind of science that you can do with it that makes radio astronomy interesting. You see different things than you see with an optical telescope. But there's a bit of an issue here. I'm just presenting 2 images next to each other. The one is optical. It wasn't actually taken by the Hubble Space Telescope, but let's just compare the resolution of an optical radio telescope against a radio telescope. So the Hubble Space Telescope, if you run the formula at the top of the slide, you get a resolution of what we call smaller than an arc second, a 20th of an arc second. An arc second is, you have a degree, you divide it in 60 arc minutes, and those you divide in 60 arc seconds, and then a 20th of that. A radio telescope, and this is a 25-meter radio telescope in the Netherlands, which is being run by volunteers. This particular dish is a lot larger than the Hubble. It's a 25-meter dish, but the wavelength that we observe at is only 21 centimeters. So our primary beam is about half a degree. So that if you were to make a picture of the sky, the full moon would be a single pixel. So the resolution of this radio telescope is like 36,000 times worse than of the optical telescope. And how can you improve this? Well, you make a bigger telescope. There's radio telescopes that are 100 meters in diameter, like in Greenbank or Effelsberg. There's a 500, so it can basically only look up and a little bit sideways. But it becomes difficult to make them larger than that. But there's a trick, and that's called interferometry, where you combine the signals of many radio telescopes at the same time. And the H1 image I showed earlier was made with this radio telescope, also in the Netherlands. It's called the Westerbork Synthesis Radio Telescope. It consists of 14 dishes of each 25 meter, but what gives it resolution is that the dishes are 2.7 kilometers at the furthest apart from each other. So that gives you a factor of more than 100 improvement in resolution. Of course, if you want more resolution, you take your telescopes further apart from each other, and you can do that even on a global scale. And my day job is with the JIVE, the Joint Institute for VLBI in Europe, and we run a worldwide network, despite the Europe in the name, a worldwide network of radio telescopes where we process their data, where they all observe a particular patch of the sky at the same time, all send their data to us. We correlate it, which is basically calculating the cross correlation from all these noisy signals, and then make images out of that, or help scientists make images out of that. So I hope that this gives you an understanding that timing becomes very important between all those radio telescopes, because to get the resolution you need to measure the phase, the time delay, or the phase difference between the incoming signals at the different telescopes. So you need to have a very good clock at every telescope. And traditionally, for VLBI at least, that is just done by putting an atomic clock at every telescope. It doesn't scale very well if you go for more telescopes. And the interesting thing is that for shorter distances, we can actually distribute this clock signal over fiber using White Rabbit. And White Rabbit is an open source, open hardware system for distributing time and frequency over fiber. It originated at CERN, where they designed it basically to run the timing for the Large Hadron Collider, and they made it open, and many more people in all kinds of observatories and particle accelerators are now using White Rabbit. And it makes use of many commercial off-the-shelf parts, which makes things easy, and it uses many existing networking standards. It is basically a more accurate version of PTP, and it gets this accuracy in part by using synchronous Ethernet. That is, that the carrier of the Ethernet signal, the 1.25 gigahertz clock, is actually locked to the input 10 megahertz that the thing gets. It uses bidirectional communication over a single fiber. So you go out in one wavelength and you come back on the other one. And that's very important, because the only thing you can actually measure is a round trip time, but you want a one-way delay. And if you used two different fibers, and especially if we're talking about kilometers or tens or hundreds of kilometers of fiber, you're not guaranteed that your two strands of fibers have the same length. And then you cannot divide by 2 anymore, because that might be the wrong value. Because it's based on actual Ethernet, it can also just carry Ethernet traffic. And it's actually been standardized and is now part of the latest version of PTP, as in the high accuracy protocol. And you see a little setup of the boxes that you would need for a White Rabbit link. On the left, you have the White Rabbit switch, and then a optical transceiver, basically an SFP transceiver for people that know them. But this one is slightly special because it has only one fiber port and not two. And then a single fiber, not a pair of fibers as you might be used to, and then an endpoint that gives you out your 10 megahertz and your 1 PPS again. So if you look under the hood, how does this work? On the left, your 10 megahertz and your 1 PPS signal go into the White Rabbit box, go into an FPGA, and they basically modulate an Ethernet signal, and then there's an SFP, makes it optical, it goes over the fiber, and goes to the other SFP, and it goes out again. And what you can do is you can, first of all, calibrate all the fixed delays, the delays in the PCB, the delays in the SFP. And once you've calibrated all those out, you can just take two White Rabbit boards, and connect a random piece of fiber in between it and the 10 megahertz and the 1 PPS. They will be completely synchronized with an accuracy of better than a nanosecond out of the box. So how it does is, you do the measurement of the static delay, then it calculates the round trip time, and normally you would divide by 2 and you would be done. But because we want to use one fiber in 2 directions, we have to do it at different wavelengths, and that means that the propagation speed of light is slightly different, and there's a calibration factor for that, which in White Rabbit is simply called alpha. So you need to measure that for your particular fiber, and then you input that into the White Rabbit system, and it will take that into account. So that fixes your dispersion. And that's basically all there is to a White Rabbit system, just very much in a nutshell. When we want to do interferometry, we want to look at, we want to have the phases of all the observing telescopes. We want to have them perfectly aligned, because what we want to measure is that as time passes, how the phase changes of the object that we're observing. And in order to do that, we need to integrate over a little bit of time, and what we want to make sure of is that the phase is stable during this observation time of 1 or 2 seconds. Because if it isn't, if the phases are actually, if you've got 2 phase vectors and they're like jittering a little bit, you lose sensitivity. And if they're jittering a lot, you lose a lot of sensitivity. And this is called the coherence loss. Imagine you have 2 telescopes, one has perfect timing, that is on the left, voltage signal A, and then voltage signal B gets its timing through a White Rabbit link, for instance, and so there's a little bit of phase noise on it on the right. And then you can calculate the coherence, and coherence goes basically from 100% or 1, then you're perfectly happy, and it goes down as you have more phase noise. And like if you have a coherence of 50%, that means that basically you're losing 50% of your sensitivity. So that is a bad thing. And the coherence loss is then 1 minus the expected coherence. For instance, for the SKA-1 radio telescope, where I was involved in the design of the time and frequency distribution, we set a design limit, or I should actually say we were given a design limit. They didn't want to have more than 2% coherence loss over 1 second integration time due to the clock distribution. And we actually wrote a paper about that, listed on the bottom. So how do you measure this without doing it directly by taking 2 telescopes and having all the confounding problems that you have with steering those telescopes and all the equipment that's in between? Is you want a slightly simpler way to measure it. And to do that, you use something called the Allen deviation. The Allen deviation is a measure of the fractional frequency stability of a signal. So if you have an Allen deviation, say, of 10 minus 12, that means that just the RMS fluctuation over an averaging time of 1 second is such a small fraction of your observing frequency. So the horizontal axis is not so much in time, but in how long you've averaged over. And the vertical axis on the left is in Allen deviation, and the vertical axis on the right is in Allen variance, which is basically just the square of that. This is just from the statistics that make up this whole thing. And you can see this is a sort of a typical Allen deviation chart for a free-running atomic clock. First of all, it goes down with a slope of -1, which means the longer you average, the smaller your frequency noise. And the noise in this case can be down to what we call white phase noise or flicker phase noise, and both of those have a slope of -1 on the Allen deviation plot. Now, at some point, the white frequency noise starts to dominate, and then the slope becomes flatter at -0.5. And then eventually you get a flicker frequency noise floor, and then it doesn't matter how long you integrate, your phase noise doesn't get any better, your fractional frequency stability doesn't get any better. And then if you integrate even longer, you start to be affected by effects like random walk and frequency drift of your frequency standard, and then actually your coherence goes up again. But now we're talking about averaging times of thousands, 10,000s of seconds. So I took a White Rabbit link and I measured it, the Allen deviation, and the first thing you notice is it doesn't quite look like the previous graph, because it doesn't go up anymore. And the reason for that is if you've got 2 atomic clocks, they're basically doing their own thing, and they're going to be in agreement for some time, and they're going to drift apart a little bit. But a White Rabbit link is a phase loop in essence, and as long as it stays properly locked, then the phase cannot deviate more and more. So the longer your average, the lower your phase noise, the lower your fractional frequency error becomes. So that's a good thing. We also see that the slope is -1, so that is probably white frequency noise or white phase noise. And that possibly allows us, if it is white phase noise, then it allows us to predict the coherence loss that we are going to get, the number that we're after. If it's if it's flicker phase noise, sorry, too many noise types, it becomes a little bit harder to predict. So the prediction looks like this, and this is the point where I tell you that there's actually 2 flavors of White Rabbit here. There's the original White Rabbit, and there's a newer version of White Rabbit, or an expanded version, which is the low jitter version. It has a White Rabbit switch with a low jitter daughter board built into it. And what you see here is a graph of the expected coherence loss, and also you see this 2% line where we sort of draw the line. We don't want it to be more than that. So if you follow the purple one, you see it reaches the 2% loss at a frequency, an observing frequency of about 2.5 gigahertz. And then if you have the improved low jitter version, you can actually go up to 25 gigahertz before you hit the 2% coherence loss. So that's quite an improvement. The phase noise or the fractional frequency noise is down a factor of 100, and that gives you a factor of 10 in higher frequency. But there's two important words in the title of this slide, and the first one is predicted, and the other is assuming. And those are, of course, very dangerous words, so I set out to actually measure this. And how you do it? Well, you take a USRP, in this case a B210, and you pretend that that is your radio telescope that gets a signal from a signal generator. The signal generator itself gets its clock from a rubidium. The B210, as if it were at the end of a white rabbit link, gets its clock from a white rabbit. And the white rabbit, the other end of the link, of course, gets its clock again from the rubidium, so that we have a closed system and we can start measuring this. And then what I did is I just went 1 gigahertz, 2 gigahertz, 3, 4, 5, 6 gigahertz, because the B210 doesn't go higher than 6 gigahertz. And of course, there's an RF attenuator at the input of my B210, because I don't want to kill the thing. And then the processing should be fairly simple. I use a frequency offset of, in this case, minus 260 kilohertz, just to get away from the DC spike and get away from all kinds of nasty spikes. And I need to remove that frequency offset in the GNU Radio flowchart. And I also want to only measure the phase changes. Amplitude changes are not important, so I remove that. And then I just basically sum the cosines of all the values, just like I showed in the formula a few slides back. And that should give me my coherence or my coherence loss. Should be easy, right? Of course not. Issues, many issues. First of all, the signal generator that we're using is a very nice one, but it uses a direct digital synthesis and maybe also fractional frequency synthesizer. It means it's not exact. The output frequency has an accuracy to the order of 5 microhertz, and that doesn't seem very much, but in 2 days you get almost a phase rotation. So if you measure for a few hours, that might already start to affect you. The B210 LO frequency is also not very exact. I have no accuracy numbers for that, but I'm expecting it to be a little bit worse. And the other thing is, in my flowchart, I want to remove this 260 kilohertz offset, but the actual signal generator block in GNU Radio also has a limited frequency resolution. I mean, it's numerical, so it's very precise, but the frequency steps that you can make are limited. So it turned out that actually stopping the phase from rotating so that I can actually do the measurement was more complicated than expected. And I ended up building a block, just a Python embedded block that I feed a ramp, so that increases with every sample. And I give the block an offset in frequency, sorry, an offset in phase and on phase slope, which is a frequency offset, and it just very precisely calculates the phase rotation that it needs to take out to actually make the signals, the long-term trend disappear. And to make the long-term trend disappear, I actually read in the data, I fit a linear to it, and the linear gives me the offset, and it gives me the frequency offset, the phase offset, and I give those as inputs to the flow chart so that the long-term trends are out and I can just measure the coherence loss. And then I ran into a bug in GNU Radio, as it happens. I made a flowchart. It doesn't even have a GUI. It just has 3 parameters: the name of the input file, the name of the output file. There I need to write into it, and then the offset and the slope. And it turns out that if you do, so these are just command line parameters, and it turns out that if any of them were negative, then the minus would be interpreted as, oh, here comes another parameter, instead of being used as the value that it should represent. So that was a little bit annoying, and the workaround here was to instead just write all the fit parameters to a file, and for every test, just read in that file. So the block then looks like this, or the flowchart. At the left top, you start with your file source, which just contains your samples of your data, and then below it is a signal source that generates minus 260 kilohertz, which is my offset tuning. So I remove that, and then I turn out to still have a huge, well, it's not huge, but it's clearly rotating the phase still in a few seconds. So I tried to take that out with a second frequency block, and then I ran into the fact that the frequency resolution of White Rabbit, of GNU Radio is kind of limited. So I could have a value that was too low or a value that was too high, but not the value that I wanted. And that's why I built a new block at the bottom, the slow phase called this block. And it gets this ramp from a signal source, which is just a very slow 300-second ramp because it's a 5-minute recording. And that gives me the final phase tuning in another multiply conjugate block. And now that I've completely centered my signal on DC basically and shifted the DC peak away and all that, I can start decimating the signal down and down and down because I don't actually need to process this at the full megahertz. The next thing that happens is at the bottom is complex to arc, which means that I take the signal and I only care about the phase term and not the amplitude, and then I make it into a complex signal again by setting the amplitude to 1, and we're now going up in the flow chart on that long block. So I make a new signal where the amplitude does not change between signals. And then I wanted the cosine. And to get the cosine, in this case, I simply take the real value of the complex signal because I've now completely aligned it to be upright, so to say, and it should always be 1. Sorry, I've completely aligned it to be in this direction, I should have said. And then I just integrate all those values, and then I divide it by the number of integrations I did so that I normalize it, and out of this comes my coherence value, or so if it's 0, then there is no coherence, and if it's 1, there is no loss in coherence. And it's going to be anywhere in between those two numbers. So let's see what comes out of it. The yellow line might be a little bit hard to see because they're hidden by the green line. The yellow line is what I expect from the numbers for the coherence loss due to White Rabbit, and the green line is what I measure. And they are very nicely in agreement, which tells me that the nature of the phase noise is indeed white phase noise, and that the measurement method in itself is a little bit sound at least. The red line at the bottom is the coherence loss that I expect for the White Rabbit equipped with a low jitter daughter board. And as you can see, the measurements in blue are a little bit higher. So things are not going as well over there. And then as a basic system check, I also ran an observation or a measurement where there was no White Rabbit in the system at all, just both the receiver and the signal generator connected to the same rubidium, and that is the purple line. And like I said, spot the issue. What really shouldn't happen is that if I'm not using White Rabbit, that I'm having worse coherence loss than when I am using White Rabbit. And that's where I had to do some head scratching, like what's going on here? This is very strange. Quite a bit of head scratching actually, and eventually I figured out what the issue was. White Rabbit happily takes the signal from the rubidium, which is at 7 dBm. But if I directly put the 7 dBm into the B210, it's not very happy. And I can show that in these two graphs. I've really zoomed in on the carrier. And in the first case, the B210 is simply running without locking to the reference input. And you see a nice clean spike, which is slightly offset from where it should be. I think I'm observing this at 1 gigahertz, and I'm getting like a 1 kilohertz offset or so. And then I lock the thing to the rubidium input, and that is simply flipping a switch in the flowchart. You don't change any of the hardware. And you see that the spike is completely centered now, but there's an enormous amount of drift around it. And that is affecting, and that basically means that the phase is doing this. It is, the average is good, but it's flipping all back and forth. So I ended up building a little square, just get it, and the idea here is that the White Rabbit output is actually a rectangular, almost 5-volt signal, which is a lot stronger than the 7 dBm that comes out of the rubidium. So yes, just two inverters, self-biasing due to the capacitor in the input. And then I tried again. And as you can see, we now have a new line, which is the green line, which is the White Rabbit, which is without White Rabbit, but now using a buffer stage for the rubidium into the B210, and at least now most of the measurements are lower than when you are actually using White Rabbit. But also the improvement is not as much as I had hoped for, and we're still much higher than the expected value, which is the red line completely at the bottom. The other thing about White Rabbit is it was originally designed to have a range of about, well, the size of the LHC, the Large Hadron Collider. And it uses optics that have a range of 10 kilometers by using a wavelength of 1310 nanometers in one direction, 1490 in the other directions. And you can actually extend that by cascading multiple links by putting more White Rabbit switches in it, but that is cumbersome and not very good for your signal quality. So people have started using bidirectional optics with longer range, like 80-kilometer ones are available off the shelf. They work fine with White Rabbit, but then you run into all kinds of other stuff. Your fiber is now so long that if the wavelength of your laser changes just a little bit, then the delay of your fiber changes. The propagation speed at every wavelength is slightly different, and the changes in wavelength actually cause all kinds of unmodeled and uncorrected changes in delay, because basically this calibration factor alpha that you measured doesn't work for any other temperature, so it's no good. The solution to that is to use optics that have a very stable laser wavelength. These optics are also available commercially off the shelf. They are used when you're using many wavelengths close together in what we call dense wavelength division multiplexing systems. And they are stable to like a tenth of a nanometers. And with that, we can actually build links that are 80 kilometers, 169 kilometers even. And we are still getting well less than a nanosecond timing accuracy, and we're getting very good frequency stability over the links. So we built a link that was 169 kilometers. And the nice thing about this link is that it uses a stabilized wavelength frequency that is outside of the regular range that is used for datacom. And the advantage here is that you can piggyback on somebody else's fiber, because you can think, oh, this White Rabbit stuff must be equipment must be expensive, and all these atomic clocks, etc. All of that pales in comparison to running your own fiber. That is extremely expensive. So if you can piggyback on someone else's fiber, you have definitely made a big improvement in your ability to build out a system. And in this case, we were piggybacking on the Dutch National Research and Education Network, and we're actually running on a fiber that has multiple wavelengths with 100 gigabit data traffic on it as well. And the network looks like this. On the right, you have the Westerbork Synthesis Radio Telescope again, which has its own hydrogen maser. And then we go to a city called Groningen, for anyone who happens to be from Holland, probably nobody else. That's 67 kilometers, and then we do optical amplification of the signal. We go back to the radio telescope, we do more optical amplification, and then we go all the way to what is marked as cameras, which is the radio telescope in Dwingelo, which is being used by volunteers. So we built up this whole network, and then we actually started to do proper VLBI between these two telescopes, and also other telescopes. So we now have a VLBI station that doesn't have its own atomic clock, because we get to borrow the signal from somebody else. And I'm not going to go into all of the astronomy, but what we're showing here is we're observing a source called 3C84, which is very nice and bright and compact, so it gives us very good fringes. We're observing at 1330 megahertz, and this again is done in GNU Radio, actually, all of it. We're using the Westerbork hydrogen maser, and at the other end of the White Rabbit link is an ATIS X310, and we're using GNU Radio to capture the data, turn it into standardized VLBI data, run it to the production correlator. We get a very nice signal, over 200 for the signal-to-noise ratio. And what we see is we have a direct link of only 35 kilometer dark fiber, and we have this engineered link that's 169 kilometers back and forth, including optical amplification, and there is not much difference in performance, as you can see in the Allen deviation. The line in blue is when we just measure the link back and forth without any radio telescopes in the loop. Then that is sort of our noise floor, and we're about a factor 2 to 3 above it, not more than that. And that's probably due to a lack of sensitivity of the hobbyist run telescope. The other thing you see is that after about 300 seconds, the graphs start to diverge a bit, and that is because at that time scale, the fluctuations in the density of the ionosphere start to have an impact on the phase of your signal. So at that time scale, it no longer becomes important what the performance of your link is, because you need to recalibrate it every 15 minutes anyway. So this basically showed that this is completely suitable for doing VLBI. And that brings me to the conclusions to this talk. White Rabbit is definitely useful for distributing a reference clock and timing for radio telescopes. And the limits are, well, probably 2.5 gigahertz if you're using the regular White Rabbit. And from these measurements, I'm thinking about 10 gigahertz if you're using the low jitter daughter board. But I have to say it is unclear at the moment whether the limitation here was in the B210 or in the White Rabbit part of the links. I need to figure that out. And we don't link distances up to 169 kilometers, and there is no indication we can't make it much longer than that. It coexisted with other uses on the fiber, and yeah, we did successful VLBI observations using a White Rabbit link. And that means that we actually transfer phase accuracy, a small fraction of a phase in phase noise, enabled to do that, just using White Rabbit. So thank you, and any questions, please?
This is probably my ignorance in this space, but why can't you use GPS to get that kind of accuracy? Is that not available through GPS?
No, GPS, the accuracy, or I should say the stability of GPS is not nearly good enough for this. We're talking about picosecond stability, and GPS is much higher. GPS is in the few nanosecond stability. And what we need is I mean, imagine you're observing at the gigahertz, then you want a stability in the order of a small fraction of a nanosecond. And so GPS is completely out for this. For very low frequencies it might work, but for the frequencies that we use for this kind of radio telescope, it's just not suitable.
Hey, Paul. Why in your setup, like the VLBI setup, like why did you go to Groningen back? Like what was the point of that extra? Was it 67 kilometers or something?
It was basically to demonstrate that we could do this over an existing production network that somebody else. The whole point was to show that we could do this on somebody else's fiber, and we even did it without interrupting the production traffic on that fiber for even a second, because we're using wavelengths that are completely outside of the data traffic, and we're using our own optical amplifiers instead of the ones that they use, because the signal has to travel back and forth through the amplifier. So it was basically to make it more interesting and to show that we could do this, that we had the technology. And I mean, just being able to transport your clock over fiber is nice for smaller arrays, but for VLBI skills, it becomes very important that you can use existing fiber.
Okay, one more question, and then we'll wrap this.
Thanks. So, similar to the first question, is there a middle ground between GPS and this White Rabbit? So if you don't want to get exactly the sort of exact timing, but you can't lay fiber everywhere, and you want better than GPS, are you aware of sort of something in the middle?
So there is a whole stratum of different solutions that you have. I mean, we all know about NTP, and then the next level would be PTP, and that might give you microsecond accuracy. And then GPS gives you on the order of nanoseconds on a good day. I think they officially guarantee 200 nanoseconds, but in practice I think it's 20. And then below that you end up with White Rabbit. So that is sort of the ordering.
Great, thank you very much, Paul. Very interesting talk.
Thank you.
Okay, and we've got one last talk of the day. Simon Steele, Deputy Director of the Carl Sagan Research Center at the SETI Institute.
Okay, it's my first time up here. I didn't know if this... Oh, there it is. There's a TV screen. That's brilliant. Thank you very much. This is the last talk of the day, so it's always a privilege that the people are still here listening to me. My name is Simon Steele. I'm, as was said, Deputy Director of the Carl Sagan Center for Research at the SETI Institute, which is based in Mountain View, California. And you've heard a few talks today about one of the main components, the SETI component of the SETI Institute, from Wael and Luigi. And what I'd like to do is just give more of a broad overview of what the SETI Institute is doing now, a little bit of history, and a little bit of the broad range of the science that is going on. So we start off with the beautiful Allen Telescope Array up in Northern California, and you've heard a little bit about that. But I'm going to talk a little bit more about the fact that this institute is much, much more at the moment than radio SETI observations. So if this is the clicker, and it is. Just a little bit of a background to the SETI Institute. It was founded in 1984, so we're coming up to our 40th anniversary. That's a view of actually our old building, because we moved about 3 months ago, but only 2 doors down, so you can still find it. 3 of the key players in the early days of the Institute, Jill Tarter, Frank Drake, and Carl Sagan. Of those 3, Jill is still very active on our board of trustees. And Frank, unfortunately, we lost last year, and everybody knows Carl Sagan. Those 3, amongst others, founded the SETI Institute as a non-profit research organization, and we've been a non-profit research organization since then. Most of our funding is NASA funding, but our SETI component has been primarily non-governmental, either through foundations or through private donations. I'm going to go a little bit back in time further and talk about Frank Drake and one of the founders of SETI as a scientific discipline. His first observations were back in 1960 of 2 G-type stars, that's sun-like stars, and looking at the 21 centimeter and the 18 centimeter line in the waterhole region of the radio spectrum, and did observations. Apparently there was one false positive, which was not being confirmed as a high altitude, probably military plane, but otherwise it was a null result. Nevertheless, this was the start of SETI as a scientific research discipline. Government funding for SETI as search for technosignatures, search for intelligent life in the universe, ended in 1993. And so the SETI Institute had to push forward with its research into SETI using private donations. And one of the biggest programs post-1993 was the aptly named Project Phoenix. And this was led by Jill Tarter using the Arecibo Observatory, the lovely 300-meter radio telescope that, alas, is no more. And this program involved looking at 800 stars within a 200 light-year range, frequency range between 1,000 and 3,000 megahertz. And again, this much, much larger scale, much more comprehensive scale of search than the original Project Ozma that Frank Drake was involved with. Arecibo, as you probably know, is a transmitter as well as a receiver. Most radio telescopes are passive, they're receivers. Arecibo is a transmitter, it's a radar instrument. And so it was also used for the transmission, as we'll mention in a second, of what is called METI, messaging extraterrestrial intelligence. Whereas the observatories such as the ATA is just a passive receiver. It's also used for, or was used for, radar mapping of asteroid shapes, near-Earth asteroids, as part of a planetary defense program. You probably saw the wonderful results from the DART mission last year. And planetary defense is one of the research components of the SETI Institute. And just mention that because it's not in the rest of the slides. Frank Drake and Carl Sagan just have to mention something about the concept of METI, that is messaging extraterrestrial intelligence. These are 3 famous examples of that. We have the Pioneer plaques and the Voyager record. And also, as I mentioned, the Arecibo message from 1974, which was a beamed message to Messier 13, a globular cluster, 13,000 light years away. So we're not expecting a response anytime soon. It's not a good target from a possibility of detection. M13 is a, as I say, a globular cluster, and those stars are very, very low metallicity, very, very low heavy element content, and probably don't have much in the way of planetary formation. And they're all very, very old. But nevertheless, as a proof of concept, that message was sent out in '74. As I say, the SETI Institute doesn't engage in messaging. It's a passive receiving science, but it was done in the past. Now, of course, with the Voyager spacecraft going out, that's another example, an interesting way of thinking about contacting extraterrestrial intelligence, and this is artifact searches. We are not expecting, although Voyager spacecraft is now out around, I think, 130 astronomical units, but it's going to take a long, long time before it runs into another planetary system. Nevertheless, you have a system here that, if picked up, becomes, in fact, an artifact of our civilization. And there's possibly a reason to look out for that from other civilizations as well. Frank Drake's probably best known for what's been called the second most famous equation in history. This is the Drake equation, and this was laid out in 1961 as a roadmap for conversation, a roadmap for the search for extraterrestrial intelligence. And we have a whole set of terms here, and rather than just looking at this actually very beautiful piece of artwork, I'm just going to run through the terms of the Drake equation, because each one of these terms is an active research center for the SETI Institute, except perhaps the last one, but that's going to change soon. So what is the Drake equation? It's asking how many advanced communicating alien civilizations exist in our galaxy at this moment in time. Such a question is impossible to answer, and we still don't know. N is at least 1, but that's sort of, although sometimes you can dispute that one. And the rest of the terms are an attempt to break down an impossible question into manageable research components. And that's what the Drake equation does. It is an equation, it's balanced, but it was never actually meant to be having numbers plugged in, although it's always fun to plug in the numbers and see what you get. So I'm just going to run through the terms of the Drake equation, and that'll give us an idea of the type of research that the SETI Institute does at the moment. When we're talking, of course, about SETI, we are talking about the last couple of terms, and so the radio telescopes reappear at the very end of this story. But in fact, it's only a quarter of a century ago that the only term that we could actually address accurately is the first term, which is the rate of star formation in our Milky Way galaxy. The values vary depending on the models, but roughly, let's say, around 5 stars or 5 solar masses of star is born every year in our galaxy. And that's reasonably obvious. You can get an estimate from the star formation rate using various sort of optical and infrared observations. And this is a lovely view of the Milky Way galaxy. So that's a good one. We're off to a good start. We a few more minutes and we've actually answered the question n equals. But then, of course, it becomes trickier. And as I said, until about 1996, none of the other terms we had any idea of at all. Because the next term is actually what fraction of these stars have planets going around them. And this only began to take shape with observations back in the late 90s, but much more importantly from a couple of space missions. That was the Kepler mission and one called TESS, which stands for Transiting Exoplanet Survey Satellite. And those two space telescopes have really revolutionized our knowledge of how many planets and what type of planets are out there. Currently, we're sitting at over 5,000 planets around other stars, exoplanets, and 822 of those systems are multiple planet systems. And if you run the statistics on these discoveries, most of these planets are discovered by what's called a transit method. That is a mini eclipse of the planet passing in front of the star from our perspective, which leads to a very, very small percent at most, a couple of percent for the big planets drop in the brightness. If you run that as a statistic for randomly oriented planetary systems, it turns out that pretty much every star in our galaxy has at least one planet. And when you're talking about 300 billion stars, that starts to get a sort of rather statistically significant number. Now, some of them we're not going to discover from that method because you don't get the transit, you don't get the mini eclipse. And there are exceptions to that. That's a generalization. Some of the larger stars, what are called the type OB stars, are never going to form planets simply because the winds from those stars, all stars have solar or stellar winds, is enough to blow away the material from those stars and stop planets from developing. But most other stars have planets going around, which is quite amazing. There was a thought to be a little bit of an issue with that because over half the stars in a galaxy are multiple systems. They're binary stars going around each other. The sun's a bit weird and it's a bit of a loner. Most stars have multiples and binary systems. And it was thought that the dynamics of that, of two stars orbiting each other, would be a real problem for planets trying to get a nice stable orbit. It now turns out that binary star systems can have planets as well. And one of the SETI scientists who is researching using the TESS satellite made the first determination of a planet orbiting a binary star system. And this is an artist's impression because, of course, all exoplanet observations are 1 pixel in size. But this is an example. This is called TOI 1338, is the binary star system. And there are two stars orbiting, two planets rather, orbiting those two stars, which is quite amazing. The stars are locked in very, very close. They're at about 0.1 astronomical unit apart. So a tenth of the distance that the sun is from the Earth. And the planet is way out there. I think it's about 4 or 5 AU, so out to roughly where the Jupiter is in our system. So you're a long way away, and so that planet actually sees the binary star system almost as a single gravitational unit. But of course, this one of them is sort of sun-like, and the other one is a red dwarf, as from that illustration. And of course, this one is now known as Tatooine, because as we know, of course you can have a planet going around two stars, although TOI 1338b is actually more like Neptune than it is like Tunisia. So a lot of our scientists are involved in exoplanet research, discovering exoplanets and looking at the conditions on those, because we assume, maybe rightly, maybe wrongly, that you need a planetary system and a planet as a nucleation point for life developing. And that seems like an obvious way to start. The next term, N sub E, is the number of Earth-like planets. Now, this is an interesting term because if you think about a planet in terms of mass, in terms of density, and in terms of distance from its parent star, Venus is the most Earth-like planet out there apart from the Earth. And Venus is the most distant, in property-wise, planet you can get from the Earth, with incredible, I think it's about 90 atmospheres of pressure. So it's like the surface of Venus, the atmosphere is pushing down as if you were 3 kilometers under the ocean in terms of pressure. And it's at incredible high temperatures where lead would actually melt on the surface if you happen to, nobody has lead pipes anymore, so unfortunately lead is still a very good analogy for temperature. So it's not a great place. So what do we mean by an Earth-like planet? Our definition of Earth-like has to be expanded. And when we get these NASA announcements, oh, the second Earth has been discovered out there, well, it might be a second Venus, and we need more information. Kepler 452b is an Earth-sized planet orbiting a Sun-sized star at roughly the same distance. We don't know, because even with the JWST, we don't know the conditions on that atmosphere to suggest whether it's an Earth or whether it's a Venus. What's interesting, though, is if you look at places in our solar system that had the best conditions for life, and for life to emerge on Earth, it takes water, mainly. You need a solvent. You need something to be able to move your molecules around to actually build long-chain molecules and life. Mars fails quite dismally in that. It's very, very dry. The two best places to look are two ocean worlds of our gas giant planets. That's Europa, going around Jupiter, and Enceladus, going around Saturn. These are icy moons, but due to the gravitational interaction with the planets, there's tidal heating from Jupiter and from Saturn that means that they have liquid oceans underneath their icy surfaces. And in a sense, those are possibly the best places to look for life or life conditions in our solar system. And that really changes the whole aspect of what we mean by Earth-like. Because in our solar system, the three most Earth-like planets are Earth and two moons of gas giants. And so that really changes our idea of where we should be looking for habitability in the universe, and not just things that look like Earth in terms of size and density. Europa is quite an interesting moon. There's going to be a mission launched to Europa called Europa Clipper next year. It's not a lander, but it's going to do very, very detailed chemical analyses of the material that actually rises up from the interior liquid ocean. You can see those sort of brown lines. That's sort of like, it's been described as sort of bathtub scum, which is just wonderful. Stuff that organics that have been lifted up from the interior ocean. What you really want to do is actually get into the ocean. And one of our scientists, Pablo Sobron, is part of an engineering team that is sending robotic craft to the plate boundaries underneath the ocean to look at these things called black smokers, where you've got organics rising up through thermal vents under the sea, either the Atlantic ridge or where there's a meeting of the Pacific and the North American plate. Here's a device called Invader, which stands for, and I need to read this one, In Situ Vent Analysis Divebot for Exobiology Research. It's basically a Raman spectrometer. That means it shines lasers at the molecules rising from those vents and can do a chemical analysis. This is the type of device built and tested on Earth, because you don't want to build it and then test it on Europa, that will ultimately fly to both Europa and Enceladus, get down into the ocean part of those moons, and do a chemical analysis and seeing what sort of organics are down there. So again, this is looking for habitability in our solar system to see exactly where life can potentially emerge. Biosignature detection, the search for biological signs of life rather than technosignature, the search of technology, is the bread and butter at the Institute at the moment. About 80% of our money comes from NASA, and a lot of that is involved in exoplanet studies and looking for biosignatures on places like Europa and, of course, on Mars. And most of the Mars lander and rover missions have had a SETI Institute scientist involved. This is a full-color image of Jezero crater which shows a delta, a dry delta system of water. It's been dry for about 3 billion years. But it's quite possible that in that delta system, if life emerged on Mars, then you will be able to find fossilized life that, of course, no longer exists, but is no longer alive. Very difficult to do that using a rover. You want to bring that stuff back. And Perseverance rover is, as it drives around this old dried water seafloor and delta system, is caching samples that will then be returned to Earth in the mid-2030s. And so SETI Institute scientists are involved in these, looking at the structure of Mars and where to direct the rovers to actually pick up the best samples. But we're also involved in the subject of planetary protection. If you are collecting material from an alien world that may contain organisms, because we don't know, and then stick them in a spacecraft and fly them back to the Earth, you need to be very, very careful with how you deal with those samples. It's also important, if you fly rovers to Mars, you don't bring a lot of Earthlings of very small size with you, because they know what you're going to be doing when you're collecting Mars samples is you're picking up the stuff that you brought in the first place. And so the concept of planetary protection, preventing cross-contamination of planets, is very, very important, and we have a scientific team working for NASA in that particular area as well. We still don't actually know what life is in terms of a definition. Where do we go from geochemistry to biochemistry? That transition is still not very clear. Darwin thought that life emerged in hot pools in the primordial Earth, just like this one from Yellowstone. And it sounds as though he got it pretty right, although we still don't know. In the SETI Institute facility in Mountain View, California, there is an experiment running that is trying to make life. It's wonderfully Frankensteinian in the concept. The idea is, in order to make life, it's not just a matter of having all of the organics milling around in a pool, because that pool is full of organics, but it's just going everywhere. What you need to do is concentrate those organics down. And so your pool needs to dry out, all your organics come together, do their reaction, the pool fills up again, out it goes and spreads around. This wet-dry cycle in thermal pools is thought to be one of the best possible locations that you can search for life. And an experiment that's running by Bruce Damer and David Deemer, who are out of UC Santa Cruz, are running this experiment in rapid time to see if you can generate the proto-molecules that will ultimately form into cells. And we'll let you know what happens. It's just started and it's very, very exciting. We're up to F sub I. So you've got a planet that has the right conditions, Earth-like, and you've got life emerging on some of those planets, whatever life is. Next stage, how do you go from bacteria and fungi up to intelligence? The question is, what proportion of life turns from what we would call non-intelligent to intelligent? And that leads to the question of what do we mean by intelligence? Humans are intelligent, we claim. Whales are intelligent, dolphins are intelligent. Bees, in their behavior of communication, could be considered intelligent as a cluster of animals. And so we need to figure out how intelligence works, and also how intelligence communicates with other members of its species. We have a scientist at the Institute called Lawrence Doyle who literally does communicate with whales. Their studies of whale behavior, both in terms of whale hunting, whale social behavior, means that there is an ability to identify what the whales are saying to each other. And you can apply standard rules of communication and syntax to whale noises. And it turns out they follow very closely how the syntax of human speech, even whatever language you're talking about, follows. And so you can begin to understand what whales are saying. And in fact, Lawrence has spoken back, and they appear to be willing to talk to him, which is wonderful. Now, when we get a signal, a technosignature from an alien civilization, we may never be able to figure out what that signal says. The important thing in this analysis and the study of whale communication is we can actually understand what whales are saying, but what's important there is we can recognize that something is being said. It's that ability to recognize a structure that is a communication system, even if you never figure out what is being said. And so that will be the next step after identifying an actual signal from another civilization. It may just be a carrier signal, it may be the prime numbers, but somewhere you need to see that there is a syntactic structure to that signal coming in. And that is phase 2. And that will be the pinnacle of that discovery, beyond the actual discovery of that signal itself. There's intelligent life, but how does that then transition to communicating intelligence? Whales, dolphins, as far as we know, have not built radio telescopes. They are not communicating, as far as we know, with species on other planets, whereas humans, by virtue probably of living on land and have other things to do and deal with, have developed an engineering structure that can build devices that communicate through interstellar distances. And so the question is that transition normal? Is that transition common? And again, we're in the range here that we do not have an idea of the sample size. One species has developed interstellar communication on this planet, whereas a lot of species are very, very intelligent. So is that a natural transition? And this is, of course, where SETI comes in. This is where the original work in the radio realm has come in. And you've heard a lot about the Allen Telescope Array. We have a new project called Project Cosmic, which is working with the VLA in New Mexico. And the idea here is that as the VLA goes about its business observing AGNs, observing pulsars, that data can be siphoned off and analyzed independently for narrowband transmissions and looking for technosignatures in that field of view, which is very, very exciting. The Allen Telescope Array, of course, is doing SETI research. The VLA, which has never done SETI research, despite the movie Contact, now has the capability of doing 24/7 SETI work as it's doing other forms of astrophysics, which is very exciting. There's also a possibility to move away from the radio spectrum. And we have a project. Elliot Gillum is a scientist at the SETI Institute who's looking at optical SETI. His program is called Laser SETI, and it's designed to detect laser flashes in the night sky. And the device here, you see it's on the roof of an observatory in Northern California. They're basically standard SLRs with wide-angle fisheye lenses. So you've got an all-sky detector, but you've got a very fast readout on the CCDs, about a 1 kilohertz readout. So what you're doing is you can have a rapid time analysis of the whole sky. Now, if you have one of these in another location, there's now one in Haleakala in Hawaii, it means now you have a parallax system, so that when you detect a monochromatic signal, laser, you can tell whether that's local or not. And of course, the idea, and we heard the very interesting strap-on device that Psyche is taking out to the asteroid, which is a laser communication system that the NASA is setting up. This type of device would potentially be able to detect that and you would recognize it because a monochromatic, very narrowband signal cannot be produced naturally, as far as we know, and therefore would be no signature. And so moving broadly beyond the radio is very, very exciting. Obviously, some wavelength ranges are not useful. Some obviously you need to do in space, but optical SETI is another way that you can look for technosignatures. Either communications lasers, which is great because that's modulating and have a signal, but also possibly pulse lasers that are powering light sails, and those will be visible from a very, very great distance. So again, the radio SETI is the prime component of the SETI Institute research, but optical SETI is another area that we're looking at. The last term of the Drake equation is the fun one or the not fun one, depending on which you look at it, L, which is the average lifespan of a communicating civilization. Humanity has been able to communicate using radio technology for about 60, 80 years. The question is that typical? And with a sample size of 1, we just don't know. We are, of course, running an experiment, a planet-wide experiment at the moment, to see how long we are able to communicate over interstellar distances. There's a lovely, not lovely graph there from NASA of the CO2 content of our atmosphere over the last 800,000 years. And you can see that we are hitting an unfortunate spike that is going to continue to go up. How that will affect us, climate change, climate problems that will emerge from this is obviously very, very important for all of us. And it's also important from a SETI perspective because this is a planet that we know life and communicating life has emerged on. And how would we be visible from a great distance, in terms of what we're doing to the changes in our atmosphere, looking at disequilibrium in an atmospheric signature, high oxygen content, which is a biological byproduct, high methane and CO2 content in an atmosphere, which can be biological, but can be geological. And Earth then becomes a laboratory on how to look for other worlds. And in the top right is a lovely image from the Cassini mission of the Earth just peeking out behind the rings. I mentioned artifact detection. I just want to end on a very interesting note, because once a civilization survived and thrived, as we will ultimately do, there's another answer to L. That's, yeah, Freudian slip there. In terms of communicating civilization, there's the pessimistic side. Well, can a civilization survive before it blows itself up? There's an optimistic answer to that as well. And a civilization gets so far advanced that we would not be able to detect a signal because their technology doesn't tie in with ours. And this is, of course, a problem with SETI, because when you get huge data sets coming down, and ultimately those data sets will be read by AI to look for promising signatures, we don't know really what we're looking for. We assume it's going to be a narrowband, modulated, monochromatic, signature, but we just don't know. And so unfortunately, there could be material in that data, modulations that we really don't understand, and we lose it. But there's very little one can do about that. It's possible that civilizations advance to the point that they can manipulate energy structures much, much greater than we can. They're called Kardashev Type 2 and Type 3 civilizations. An example of an advanced civilization would be what's called a Dyson sphere. That is a way a society can construct a system to utilize the entire energy output of their star by building a megastructure around it. Now, that's very, very interesting, because if one of these megastructures was being built, we now had the ability to measure the light output of stars using these transiting satellites. And there was a discovery of a star that was called Boyajian star, after Tabitha Boyajian, who was the astronomer who discovered it, who noticed this very irregular and very deep dips in the brightness of a star. Now, what can possibly cause that? What could cause a star to have 20% of its light cut out at random points in time? One possibility is that there are very, very large megastructure components being moved into place in front of that star. It turns out that another way you can do it is through cometary debris. And cometary debris, much less exciting, but fits the data much, much better. This does open a way, though, that you can use transiting data to search for advanced artifact structures and megastructures. And one of our scientists, Anne-Marie Cody, actually has got the first NASA grant since the early 90s to do SETI research, but it is analyzing test data that, if you normally analyze it to look for exoplanet transits, but looking for anomalies that could be lots of things, but it could be these advanced structures, which is very, very exciting. And of course, we just don't know what that's going to turn up. So that is just an overview of some of the work that the SETI Institute is doing. I haven't said much about the radio because that's been presented much, much better by Wael and Luigi. But we are an institute that covers a huge range of topics of scientific research, all with the aim of discovering what or where life is in the universe, and are we alone? I'm just going to mention one last program. It's called the Frontier Development Lab, that some people may be interested in. You can talk to Rebecca and myself later on today or tomorrow. It is a summer AI ML accelerator program that runs over a period of 8 weeks, and it brings together early career PhD researchers and machine learning specialists to try and answer problems of big data. And so this can be everything from weather prediction, flood predictions, medical applications, energy applications, and also SETI applications as well, where you're dealing with vast amounts of data. This is a program that runs every year, and it invites any group to propose a challenge using AI ML to address major problems and major challenges in big data. So I just want to mention that is run out of the SETI Institute. Take a look at our website, www.seti.org, and we are here for the rest of the week. Please do ask us about any of these programs. But probably the most important slide of all is that there is a reception this evening with free beer and wine just down the road in the Hilton Tempe downtown. This is hosted by Breakthrough Listen and the SETI Institute, and we would love to see you there to talk more about all things SETI and radio. Thank you very much.
Thank you very much, Simon. Does anyone have a question quickly, or I think probably the better answer is actually to say go to the reception. There is also the SETI Institute booth in the expo hall, so lots of chances to get questions answered. So thank you very much. This is the end of our main track of talks. There is, between now and the reception, a Women Plus event that's meeting here. So we invite anyone who identifies themselves as a woman in any way that is significantly important to themselves to stay and participate in that, as well as allies who are committed to improving the representation of these people who generally are not well represented at this conference and in the workplace. So this is something that's quite important to us as GNU Radio, and I think to many of the organizations in the room. So we'll be holding that event now, and we will start up again tomorrow with our main track at the usual time. So see you here at 9 a.m. Thank you very much, and Have a great evening.